It's on. I think it's on. Test. So someone will come over the microphone for the first
Yeah,
talk. Have a
I can throw it. If there's like sometimes a little bit more. If the discussion are good, like yesterday.
All right. Welcome everyone to the second day of BPF track. And I guess, let's get started. We have lots of wonderful talks packed, so we need all the time we can get. I'll be the first presenter. I have a bit of conflict of interest, but bear with me. All right, so my talk is about advanced BPF profiling techniques, how to escape NMI curse and fetch ELF contents in BPF. Clearly, I was going for the longest talk name, very imaginative. I lost, by the way, but it is what it is. So, but like before we go into advanced BPF techniques, which I hope like with time will become more commonplace and well-known and widely used, I wanted to start with just like general kind of idea of what does it mean to build like a minimal useful profiler using BPF, because I think like nowadays it's actually pretty straightforward. So let's go quickly over that. And I would say that the basic BPF profiler consists of like three components. The first one is like some sort of trigger event that we set up and like we call BPF program on. And so the first one like determines sort of like what kind of resource we are trying to measure and qualify and all that stuff. The second one is the BPF program itself, which is triggered based on like the event triggering. And like for our purposes today, we'll be looking at the perf event and CPU cycles event, perf event program. And the third component, which usually is like the biggest and like more kind of complicated and custom, is the post-processing, which is usually done in user space. That thing has to collect data from BPF, normally using ring buff, then perform like symbolization of stack traces, and usually there is some sort of filtering and aggregation, stuff like that. And it literally is like 300 lines of code to have some useful profiler that can give you like real information about like where the CPU cycles are spent on your system. Like this cat profile is from the libBPF Bootstrap project, which has like a profile example like end to end basically. So go check it out if you haven't seen it. Yeah, I decided to show also snippets of code so that it's like less abstract. And so this part is basically setting up the perf event that I mentioned, right? Like fundamentally, we just say it's a hardware event, CPU cycles. We want to trigger it every 5 million cycles. We call perf event open syscall just to set everything up in the kernel. That thing produces us perf event file descriptor, which we then use to pass it to BPF here, to attach our profile BPF program to a perf event. And that's pretty much it for the setup. The BPF side of things are pretty simple as well, as you can see. I mean, it's a little bit abbreviated, of course, like there are a few more lines of code, but this is the essence of it. Like we get this BPF perf event BPF program called in the context of like whatever process triggered like this like 5th million of events since like last triggering. We reserve some space in the ring buff because that's how we're gonna send data to user space. We collect some sort of kernel context, what process was running, like process ID, the CPU, which we are capturing this on, like maybe the name of the process. And usually, because otherwise the profiler would be like not that useful, we get some stack traces. And like you need to get stack trace like separately for kernel, first line, and then separately for user space with like this extra BPF user stack flag. And that thing stores a collection of U64 addresses in the kstack, ustack fields, which are just like array of integers. Ring buff submit just sends this data, like makes this data available to user space, basically. Doesn't have to send it immediately. And then on the post-processing phase, basically, you just set up ring buff manager or sort of. This is all libBPF API, by the way. You don't have to use libBPF, but I'll just use it as an example, right? So you set up ring buff, you provide your event handler callback, which will be called for like every consumed record produced by BPF side. And then like in endless loop, you basically just poll for new data, which like when the data comes in, will trigger the handler. And the handler itself at the very basic level is just this, like we get the pointer to a data, what its size is, and we can just access it directly. It's just read-only memory for user space. In this case, like I just print like the process ID, CPU ID, and then like each of the kernel and user stack trace, like we do the stack symbolization using those helper show stack trace. And so that's kind of the fundamental part, which is actually quite convoluted if you had to implement it yourself. So I would definitely not recommend it. And instead, you should probably use some good library. And we have that. We have BlazeSym, which handles stack symbolization very well. And like I'll just show like a very brief example how you can do it. In this case, like if PID is non-zero, that means like user space stack. So like we consume it using this like process absolute address requests where we just specify process ID and a set of addresses that we want to symbolize. For kernel, it's like slightly different, but like following the same pattern. And then like you get back like a collection of symbols with some extra information. Like it will have symbol name, offset within that symbol, and then symbol usually will be function, of course, right? So like you will have a function, the offset within the function where exactly like we were. You can also request debug information, so like extra debug information, which will give you like file name, line number, all that stuff. So it's all very easy to use, actually. And that example that I like mentioned, like 300 lines of code, it already includes all of this, like using BlazeSym. So go check it out, like don't re-implement it yourself. And if you can do better, like contribute back so that the entire community can benefit from that. And so once you are done, like if you do a little bit more post-processing, right, like you can produce something like flame graph, right, like which most people probably familiar with by now. I stole this screenshot from Brandon's site, but that's how it looks like, right? And at the bottom, there will be like the common ancestor frames, and like as you go up, like you'll like branch out into like different functions, stuff like this. Go read the blog post if you're not familiar. I think it's a useful concept to know if you are in the kind of tracing community, basically. So like again, links to the projects that I mentioned. Like if you want, like if you're unfamiliar, definitely check it out. But even if you're familiar and just want to experiment with the stuff that I will be mentioning today, this is a good starting point, actually, so you don't have to implement like the boilerplate, basically. And so just like to kind of conceptualize like what goes into the profiler and like what are we doing, is like fundamentally like two different things, right? First is like defining what are we triggering based on, right? Like it could, like in a simple case, it's like CPU cycles, and that means that like we are quantifying CPU cycles being used, right? Like periodically sampling like where in the code we were like as we span CPU cycles, like tells us basically where we spend those cycles. And so the trigger defines like the resource that we are trying to quantify. And then the stack trace like is basically qualifying where in the code we are doing that, like using this resource. Like not just like where in the code, but also how did we get to the code. That's like the call chain part of the stack trace. So yeah, so that's the basics. And like once you're done with that, like almost immediately your users will come to you and say that they need more, because stack traces, as good and as like detailed they are, don't always tell all the story. Like very often, like people will come and say that they have some like RPC service, right, that handles some requests, and they would like to group those stack traces like resource usage based on like logical requests, right? Like they would want like request ID, name, maybe arguments to request, or it could be like especially in an AI training world nowadays, right? Like which phase of the training are we in, like forward pass, backward pass, like, or maybe some like preparatory pass and all that stuff, right? And so like as a separate but kind of like conceptually similar thing is like, how do we handle higher level runtimes like Python or Java, right? Like the stack trace that you are capturing like with the basic BPF get stack call is like native stack trace, right? Like as it's sort of seen by kernel, CPU, low level, but like Python itself has like a higher level concept of the function, and like you won't catch that. And so that's like a very common request also, like, can we get a Python stack trace, right? And see Python function, all this stuff. And in all of those cases, basically the problem is like, how do we augment like the basic data that we already capturing was like something that's like application specific, and it can the data that we are trying to capture will differ depending on like which process you're running. Some processes might not have Python. Like how do we detect whether Python is even present or not? And so I'll be addressing how you can like go about solving those problems in this talk. And just to give kind of like outline how you can do it like conceptually for application context, I think it's a good idea to utilize thread local variables, and like with a little bit of generalized instrumentation of the user space, like using thread local variables, you can achieve like all of the mentioned requirements. Like you can integrate some like special predefined thread local variables to describe like which requests are we in the context of, basically, right? And maybe like some extra parameters about from that. And you can build like higher level abstractions on top of that, doing like request specific metadata or like function frame specific metadata, all sort of stuff. And like this is not theoretical. We actually did that at Meta. We use it like quite extensively. It's great, and like hopefully more people will start like using techniques like that going forward, because I think like it's easier enough like to do this than it used to be like a few years ago. For the Python part, basically same thing. Like thread local variables help because it describes like what the current thread is doing. It's very deterministic. It's very low overhead. And so basically what I'm getting at basically is like if you can capture thread local variables with BPF, like you'll be able to extend the profiling context like significantly. And but like fundamentally, like I'm not gonna show you the code how to do the thread local variables, but I wanted to kind of conceptualize. Like there are two fundamental problems with BPF, like to be able to solve all those like application-specific context capture. The first one is the data discovery problem. Like to capture the context, you first need to know where to get the data, right? Like you need to find some memory location or something like this. And currently, it's quite involved and convoluted and kind of expensive, because in practice, like what you have to do is you do before you start like your profiling session effectively, you have to pre-process every running process on the system. You have to find every process. You have to go through every executable that's linked into the process. You will parse ELF just to find like ELF symbols that describe thread local variables or global variables, whatever you need to find. But like you'll be doing this kind of extensive upfront pre-processing. And it's expensive because you have to go through every process, but in practice, like not every process is actually interesting or like will even trigger the event that you are trying to trace. And so you potentially like pay a lot of overhead for this. You have to probably memorize this, like cache this. And again, like because you don't know which process is interesting, like you have to do it for all the processes. And so that's kind of convoluted. But also the other problem is like it's missing data. It's racy, because if the process of interest starts like right after you finish the discovery process, like you won't basically know any extra information about that process. So that's one of the problems I call data discovery problem. And then like specifically to BPF profiler, as like I define it, like with the CPU cycles or something like that, there is like a data capture problem. Even if you know where to read the data, currently you might not be able to reliably capture this data, because all the common tracing programs like perf event, kprobes, trace points, they all run in the like quite restricted context, and at the worst case they can run in NMI, which is like the most restricted context you can get like in the kernel. And they are always non-sleepable, which means that when you're trying to read the user memory, you won't be able to wait for that memory to be paged in if it was paged out or never paged in from the file. And that actually is not theoretical. That happens quite frequently, especially for like string context. So like you can imagine you have thread local variable which points to a string describing the request name. If that constant was never accessed from the file, it will still be like file backed. Kernel will know where to find it, but like when you are trying to read it from BPF program, like you'll get e-fault because it's not physically present in the memory, right? And like NMI in general, like tracing context has like all those different constraints that like make your life as the builder of a BPF based profilers hard. Like timers don't work in NMI currently, though we are trying to fix it. Like if you need to do some memory allocation, in an MI, it's not so like it's not 100% guaranteed, let's say, right? But again, like this is also something that like we are fixing with scheme-alloc, no alloc. And generally speaking, like if you're in an MI, any sort of locking is best effort. And so that means that like your ring buff reservation might randomly fail, or like hash map lookup can fail, because all of those need to take like very brief but still lock. So NMI is the curse, like, and we want to fix that. And so I'll start with actually how we fix the second problem, then we'll go back to the data discovery problem. So how do we fix the NMI curse? This year we added a set of APIs that allow us to break out of NMI. It's all based on the kernel internal task work add API, which allows you to schedule a synchronous callback, which will be run as kernel returns to user space. And this is important because you get think about like the profiler, right? Like perf event, that's an interrupt. Whatever was going on CPU, you stop that, you freeze it, and like BPF program gets control, right? So at that point, you actually want to know what was going on. And if you do something later, like you're like not at that point, like you run the risk of not capturing the exact state of the application, right? And that's true for the kernel. So like for the kernel stack trace, for example, you cannot really postpone anything. You have to get it there. But like good news, kernel stack traces are reliable. So that's all good. But for user space, that's not the case. Like you actually can postpone some processing a little bit as long as the user space thread that you interrupted is still suspended. And that's the case with task work. Like it schedules callback that will be called on the way from kernel space to user space. But the good thing about that callback is that it will be running in like a much more permissive context. It will be a sleepable context, meaning that you can take page faults. And so this problem of unreliable memory reads is gone with this, because you can wait for some memory to be paged in if you want. There are some complexities in how to make all this work in NMI, because like the kernel API itself is not NMI safe, but with our cube work and some ingenuity, you can solve it, and we did solve it, and so that's great. It works from everywhere, basically. You can call it from NMI. Just to reiterate, I guess, kernel side context that you're trying to capture, you have to capture synchronously. Good thing is it's pretty reliable already, like whether it's NMI or not, so you capture that. But the user space data or state or whatever, stack trace, you can postpone a little bit and capture it asynchronously. It will still be exactly the same state, right? Because the user space application thread, it stays suspended like for that entire time, from like the triggering of the interrupt to like when we are triggering like the synchronous callback. Of course, like a synchronous callback introduces a little bit of complexity, because you need to join the data. You can do it either in BPF or in post-processing in user space, but it's all solvable, doable. It's not that hard. So let's look at the API. This is how it looks like. You have to declare a field. So if you're unfamiliar with like how timer and work queue is used, this will be new for you. But generally speaking, BPF has this approach where like if we need to like postpone some work, we need a little bit of memory to store some context and all this stuff. And like we use user-defined maps for that, but like we ask user to define some special fields. And so task work will uses the same approach. It asks user to define this the field of this special type BPF task work, which is just an opaque 8-byte structure. You just add it as an extra field. You won't have direct access to this because it's used by BPF internals. And so verifier protects it from corruption, all this stuff. But once you have that, you can call this BPF task work schedule resume API. You pass the task. It doesn't have to be current. But like for this use case, like it usually will be current probably. So this is the task in the context of which we want to run the callback asynchronously, like before exiting to user space. The second and third arguments, they basically just like give pointers to this task work field. I'll show an example in a little bit. And then you just pass the callback, which is like BPF subprogram that will be called eventually. And the callback itself is very simple. When it's called, it gets the pointer to the map, which contain this task work field and like the key and value. And so that's very convenient. You can get like you can have like a generic callback which gets like a specific context in which it was called. And so It's pretty nice API, I think. In reality, though, this API right now is a little bit uglier with this like impulse suffix and like one extra argument. Like you have to pass null. That's like implementation details, which we are soon will be eliminating. So, like going forward, I'll assume that this is this form because that's how it will be like very soon. But right now, like if you're using this, you need to use this impl variant and just pass null to the last argument. So nothing conceptually changes. So again, like just as a snippet, like this is how you would do it. So like imagine you have this task state, which is like a user-defined map value description. You just need to add like extra field, task work, like the map definition, and then in your like NMI handler BPF program, you just look up this this value and you pass like the bolded part, right? Like you pass the pointer to the field and you have to specify also pointer to the map and like verify reinforces that they match and all this stuff. And then your callback will eventually be called. You can get this task state struct and work with it. And like you can store whatever extra context you wanted to store. You can eventually delete it or use this element, doesn't matter. So that's all well. That allows you to escape the NMI when you are in like perf event handler, but there is a second variant, and I wanted to touch on that just for completeness because I think it's also solving useful like use case. It's very similar conceptually. It's a different flavor of the same task work thing. Task work actually supports multiple modes. And so like the previous one that I showed is just like so-called resume semantics, where we will be called as we go out from the kernel to user space. But I think like if the user space is already running, then like you won't run it or something like this. So that's useful for perf event handler. But in some cases, you will want to capture some information about the task that you didn't block just yet, right? It might be running in parallel. And why? Because there are alternative ways to build profilers. For example, so-called wall clock profiler, which doesn't use like a CPU cycles, so like hardware resources. It just periodically goes and iterates over all threads in the process, right? And that approach allows you to see what's going on in the system, regardless whether it's being on CPU, using some resources or not. This way allows you to see threads that are deadlocked or blocked in I/O for a long time, and you will be able to see where it happens, like both on the kernel side and user space side. So this is a very useful approach. And for that, you use the task iterator. Like we're not gonna go into details about that, like do look it up though. That thing allows you to iterate like literally every single thread on the system and do something with it. The problem with this is that stack trace capturing is not reliable for that kind of profiler because the task might be running, right? And while for the kernel side stack trace, this BPF get stack API that we normally use for getting stack trace might work, it actually is unreliable. If it detects that the task is running on another CPU as you request the stack trace, it actually will bail and like return you like e-fault or whatever, something. And it's even worse for user space stack trace. Even if you request user stack trace and the thread is like suspended, it's not running on CPU, kernel implementation won't even try to get stack trace. So like basically you are on your own, like if you want to quantify this. And so like what we do in practice, we actually like kind of try to do the stack unwinding using frame pointers opportunistically, which means unreliable stack trace is potentially garbage depending on whether the process is running or not, or like how frequently it actually jumps between the functions, all the stuff. So it's all based on luck. You might get some useful data. Very often it will be some garbage. So that's not great. And so the solution is we have to suspend the task briefly. And this signal variant of the task work is exactly the tool for that. That thing will make sure that whatever task you specify, current or not current, if it's not running, it will be sort of run briefly to execute your callback, sort of like handling signal. That's why the signal but the signal is not sent. So like it's not signal, but it's signal like semantics. So if the task is not running on CPU currently, it will be briefly woken up. Your code will execute in the context of that task, and then like the process will go back to whatever it was doing before. But if the task was running, it will be also interrupted. basically suspended, and your callback will be run in its context. So that means that like with this wall clock profiler approach where you iterate all the tasks, you will be able to deterministically get the stack traces. You still have to implement it like with frame unwinding. Actually, yes, I think you still need to implement it like manually, but it will be reliable. It's actually not a lot of code. I'll show you an example. So this is great. Like it's sort of like a family of task work APIs that we added, like for kind of two different use cases, but like they deal with the same problem basically. How do we get into a sleepable context within the provided task and work with it reliably? And so this is the kind of example of the code how to do stack unwinding. It's very similar to what kernel is doing actually. This BPF copy from user task, that's like a reliable way to get data. It requires sleepable context, but it will, like if for some reason the stack space that you're trying to read was paged out, which technically can happen, it will still wait for it to be paged in, all reliable. I included this slide also like as a follow-up to the first talk of yesterday, where like the BPF review was demonstrated. This was the fix: barrier variable and then like extra check. If anyone remembers, doesn't matter. But the main point is it's actually pretty simple to do stack unwinding using frame pointers with BPF, and with this task work signal thingy. It's reliable. It works well. So let's go back to the data discovery problem. As you remember, right? Like right now we have to do like pre-processing, user space. Like we might lose some processes that end later. So the question is, can we do better with BPF? Because as we all know, everything is better with BPF. So must be better. Fundamentally, right? Like as I mentioned, the problem is like how do we access ELF contents basically? Because that's sort of the source of like the data location, right? Like ELF symbols, relocations, whatever you need to. Usually it will be described, if it's described at all, it will be described in the ELF file. And so the good news is actually we solved this problem like earlier, I don't know, 2 years ago probably or something. BPF gets stack that I mentioned, right? Like that we used to get stack traces using like just normal non-sleepable context. It actually has like a mode where instead of returning absolute addresses, it will try to determine the build ID, which is like a unique identifier that's produced by a compiler that like is supposed to uniquely identify unique binaries. And so BPF get stack can return you build ID and then like a file offset within that file, which is very useful like if you have like a proper symbolization infrastructure set up in your organization where you can offload like kind of expensive symbolization like to a different machine where you can like take more time but produce more detailed stack traces, right? So the main point here though is that build ID is located in the ELF file in the node section, which is never allocatable. It's actually not memory mapped into the memory, and yet like BPF get stack has to work with this. So internally it introduced this file reader abstraction, which works like in NMI, in non-NMI, and it's actually pretty simple. It keeps like one folio reference at a time, folio/page at the time, and like if it needs to read some data that like falls like on the boundary between two pages, it will just use like an additional small temporary buffer to read data into. Internally, like the interface is pretty straightforward. It works well. Mostly like there are some bugs that we will need to fix on the side, but generally speaking, the point is like we already sort of solved the problem of reading the file contents no matter what the context. And so the question is, how do we now expose this to like a normal general purpose programs? And another thing that like over years we added is this BPF then pointer abstraction. And if you're not familiar, go ask your favorite AI model what it is, but it's conceptually just a logical range of n bytes, effectively, right? And we used in pointer to describe both like a memory on the stack, memory in the map, or socket buffer. Like, and so the data doesn't have to be like physically continuous in the memory, but like if it's logically ordered, like from 0 to n-1, BPF then pointer is a good way to work with that, and like it integrates with verifier pretty well. It reduces like amount of like a statically verified restrictions you have to satisfy, and like what's important for this discussion is like it has this BPF then pointer read API, which accepts like a random non-statically known amount of data you need to read, and like the only limitation is like the buffer into which you're reading has to be like predefined up to some maximum size, right? So like this part has to be static, but otherwise you can like specify like random offset and random size. And like if those combinations don't make sense for whatever like the DIN pointer is actually describing, it will be just like a runtime error returned to your program. Like you won't actually read anything, but at least you will know about this. And so the important observation is the file is fundamentally just like a logical set of bytes, right, from 0 to n's. And so that means that DIN pointer is actually a good abstraction to represent file. And that's exactly what we did. And this is like the new APIs that we added, like basically constructor, BPF DIN pointer from file, which takes the file reference, and we'll go to that in a second, some flags, and it produces DIN pointer with which you can work. And you have to call this like destructor file discard because like the constructor actually does like memory allocation. So you need to clean up some resources, and verifier enforces that like this is all like well formed, like every from file will have file discard, all good. And just like as an example, if you're not familiar, this is the API for the DIN pointer read. It accepts destination, buffer, and length. Those two have to be kind of statically known, well formed, like verifier will enforce that. But other than that, like it just takes DIN pointer and offset and just reads it basically. This is actually like the work done by Makita. So if I left the link if you want to go read the patch description and get more details. We don't have time for that, but it's there if you want. And so remember, like the file, right? Like this is the important part. Like where do you get the file? And I think currently, like the most practical way is the task VMA iterator. It's another kind of iterator that we have, like where if you have a task, right, current or not current, doesn't matter, you can go and iterate like every VMA, every like a virtual contiguous memory range, and you can filter it. Like in this case, as you can see, right, I'm filtering based on like whether it's executable or not and whether it's file backed. And so this VM file is exactly the reference to a file that we get. And if it's not null, that means VMA is file backed, and so we can be sure that the file is well formed, and so we can start using it. And that's what we're doing here. We create the DIN pointer from file. Then there will be some code where you will be parsing it, right? Like alpha is not that complicated, and like we'll just do it manually. And once you are done, you'll just discard the DIN pointer itself, not the file. And we're running short on time, but here is the link to the example where I try to use all that for a few different use cases. So what I'm doing there is I use the iterator task program, which is kind of similar to task iterator, open code iterator. Like fundamentally the same thing, like the program is called for every task. And for each task of interest, I have some filter there. We use this schedule signal API to get like a reliable, sleepable context for that task, no matter whether the task is suspended or not. In that, like we manually do the stack unrolling. We'll eventually print it. Besides that, just for the fun of it, like I also go over all VMAs, find all the executable VMAs, and try to find the PyVersion symbol in the file, because that's a good indicator whether the process is using Python. And if it's using Python, we also automatically get the Python version, because in practice, like if you want to do like a Python stack unwinding, it's quite complicated in terms of like the code and also in terms of like different approaches that Python uses for representing stack traces over versions. So it changes over time. And so knowing which version you're working with, like will simplify that. Right now, like we have to kind of guess it like in pre-processing phase. With this, you will actually know this is like the Python version 3.11 point whatever the minor thing. So I wanted to see like whether it will work. It seems to work. It's great. But there's more, right? Like I've been telling you about thread local variables like a lot. And I think it's fundamentally important like for more advanced profilers. And so I built a prototype which takes just like a thread local variable name and tries to find enough information, and like enough information for thread local variable is actually two values, like the module, so-called module ID, and then like offset within that module. Not gonna go into details, like I left links. I think like especially this second link is like super approachable. So if you're curious and you want to make use of thread local variables in practice, like with BPF, go read that for sure as a starting point. But basically that thing just takes the name as an input parameter. It tries to find the ELF symbol representing, like ELF symbol with that name, basically representing this variable. You need to find some ELF relocations related to that symbol. there are like few hoops you jump through, but like eventually you'll arrive at like the values of those module ID and variable offset, and all that is reliable. Like that's the important part, right? And you do that on demand as you get like triggers, right? Like NMI or not NMI, you'll just stop. And it's like, okay, current process is important. Let's go parse out. It's a relatively expensive operation. So obviously, like after you do this once, you want to cache this. But the important thing, you do this on demand. So no matter how many threads you have on the system, thousands, tens of thousands, you will only do this for those that actually matter, that you are interested in. And I think that's like the most important part. And so just to summarize what we covered here, building basic BPF profiler nowadays is pretty straightforward. Usually BPF Bootstrap is like a playground. If you're unfamiliar with this at all, just go read the code. I think it's pretty straightforward. Even if you are familiar, like you can use it as a like jumping off point. BlazeSim saves lots of time when dealing with stack traces, and I feel like stack trace is like the basic building block for any tracing BPF-based tracing tool. So you don't want to re-implement that yourself. BlazeSim is powerful and performant. Go use that. The new sets of APIs that I described, BPF task work, super useful like for different contexts, whether like it's like perf event or like this task iterator based approach that allows you to asynchronously, so that's a little bit more complicated, but it allows you to get reliable context where you can sleep and wait for memory, do whatever you need to do with user memory and like user state overall. And then like nowadays, it becomes possible to do ELF parsing on demand from BPF, which is, I think, pretty liberating. And I'm looking forward to like people making good use of that going forward. And like when we're talking about ELF parsing, like that means we also can parse dwarf, because dwarf is just part of ELF, really. It's fun to think about this. Like I haven't implemented any prototype for that, didn't get time, but it's very doable. I'm pretty sure. With all the like modern BPF, like iterators and all that stuff, like it's there is no limit to what you can do really right now. So that's, I guess, like the main message I want to send. We do need good BPF, solid BPF side libraries to deal with all those like higher level concepts, because it's kind of tricky to do it like in a well-rounded, complete way. So there is no point in like every single user to re-implement it yourself. And hopefully by being able to do this like purely on BPF side, like we will be logistically, it will be much easier to like have a shareable libraries that are easy to just include into your project. So go write them. And that's it. I'm a little bit late. Do we do any questions? Maybe one, if anyone has it. Yeah. There.
So Ayurin is a huge user of task work, at least it was, and specifically about signaling. The problem is, even with Ayurin, when it was a part of the game,
can you keep it close?
Yeah, it interrupts your syscall, and users absolutely hate it. So the signaling, specifically signaling API, should be used with a lot of caution, because
of course,
even when the user space triggers interrupts itself by sending requests, it's annoying. But if someone else sends you a lot of interrupts.
Right. Yeah, no, that's a good point. And like you shouldn't do it like millions of times per second, right? Like this wall clock profiler approach, we do use it internally at Meta. I think like one of the main use cases is like to detect like where we are deadlocked in the threads. And so the frequency at which we iterate every process is like in tens of millisecond period, like not every millisecond even. That's like very frequent. And so yes, there is some impact. There is always some impact with tracing tooling, but like if you're smart about it, it shouldn't be a big problem, I think. One more and we'll be just 10 minutes late. Or maybe not. All right, cool. Thank you very much. Who's next?
Okay. Hello everyone. My name is Menglong Dong, and I'm a kernel engineer major in network and BPF since I work for about 6 years. And I work in China Telecom now. And this is Jerry. He will introduce his recent work on single direct FTS letter. The topic we are going to talk about today is BPF tracing multi-link support, and it has a long history. This is the outline of this topic we are going to talk about today. First of all, let's have a look what's the BPF trap line in case that someone else is not familiar with it. So as far as I think, the BPF trap line is a bridge between the BPF programs and the target functions, and it's a special configuration that generated by the kernel dynamically according to the target functions and the BPF programs, and it's pro-functional. Which means that the trap line for function A can be used on the function B. All the BPF programs are coded directly in the BPF trap line, which makes it efficient. And all the information that we needed is stored directly in the BPF trap line, such as the function argument count, function address, and so on. This is a demonstration of how BPF trap line works. For example, if we want to hook a kernel functions with a F entry, then the kernel will correct a BPF trap line for that kernel functions, and then it will replace the null instructions in the head of the function with a call instruction. And it will call the trap line that is corrected. In the trap line, it will do some preparing works. For example, it will save all the function arguments in the register to the stack, and then it call the BPF programs, and it return. This is a simple demonstration. What the BPF trap line do is much complex than this. So let's have a look. What do we do? What can we do if we want to hook multi-kernel functions with a single BPF programs? My choice is that during loading time we clone the BPF programs. For example, if we want to hook 6 kernel functions, we will clone the BPF programs for 5 times. And then the kernel will correct 6 BPF trap line. Every trap line will have a corresponding FTS oops. So the problems of the tracing is that if we want to trace 20,000 kernel functions, then we need to clone the BPF programs for 20,000 times, and it will correct 20,000 BPF trap line and 20,000 FTS oops. It will consume many memories, and the redundant BPF program instance trap line and FTS oops. Another problem is that it's not convenient to use, as we have to do the clone steps. And it will also make the attachment much slower. According to a test, it will take about 16 seconds if we want to hook 1,000 kernel functions. And it's not acceptable if we want to hook 20,000 kernel functions.
Yeah, hello. My name is Jiří Golša. I work for Isovalent and Cisco. So, yeah, I work at the ftrace level as a base for the work that Mengelong is actually doing. So, how do I move the slide? Okay. So basically, ftrace is what we use to attach the trampoline. So if you have like f-entry, f-exit, f-moderate program, this is all ending up with the trampoline. And the way we attach the trampoline to the function is through the ftrace. And the way we interface with the ftrace is ftrace objects and a few functions on top of that. And basically, ftrace object has inside hash called ftrace hash. And that hash is full of the ftrace func entry objects. And this object actually contains the pair of the IP address that you want to attach and the trampoline. So the way we are using it now for the trampoline is that each trampoline is allocating its own dynamic ftrace object, and it initializes the hash inside just with the IP for the trampoline. So each trampoline is basically specific for each function. And then we call like the register, unregister, and modify interface on that. So that actually works now because we are attaching the trampolines one by one. But if you actually want to attach, like Menglong is doing, like thousands of functions, that's not really convenient because you need to handle thousands of ftrace objects. So instead, the change I did was actually we went to using just single ftrace object and do all the heavy lifting on the hash which is inside. So basically, we have one statically allocated ftrace object, and we do all the modifications on the inside hash. Like we add the functions that we want to attach with the trampolines. It can carry like all the functions in the system. The ftrace is able to handle that. And then basically introduce a new interface, which takes this one ftrace objects, and the second argument is the hash, like the change that you want to do to the ftrace. And not only it's more convenient, like for the future changes, that it's much more comfortable to work just with one ftrace object. It also turned out to be faster on its own. So yeah, there's one example of that. The speed up basically is from the fact that ftrace object is now just one, is single, and it comes from the original code. In the original code, when you want to unregister the trampoline, if the ftrace object is dynamically allocated, the ftrace layer actually needs to do some RCU synchronization calls, and yeah, that might take a time. So if you're attaching more functions, you will actually see the speed up if you use the single ftrace object. So I did it as a base for Menglong changes. Yeah.
So let's have a look at the implement of the transient multi. And all this work is based on Jerry's work. This is the logic of the transient multi-link. As we can see, we introduced the three new attach type: the f-entry multi, f-exit multi, and modify return multi. So in this solution, if we wanted to attach a BPF program to multi-count function, we only need one BPF program instance and one global BPF trampoline and the direct ftrace ops. As we can see, the key of this solution is the global trampoline. So let's have a look at what's the global trampoline. Generally speaking, the global trampoline is a kind of function that write mostly in C and partly in assembly. For the assembly part, it's architecture specific, and for now, only x86 is supported. The logic of the global trampoline is a little similar to the BPF trampoline. First, it will prepare the stack. It will save all the function arguments in a register to the stack. And then it will look up the function metadata from a hash table with the function address, which we get from the stack. We will talk about the function metadata later. The function metadata store all the information we need for the target kind of function. And then we prepare a stack. We save the function argument count to the stack and so on. And then we call the F entry in the function metadata. We call all the BPF. We call all the F entries. And if original call is not needed, we return directly. If it is needed, we will get a perceptual refer of the function metadata to protect it. And we do the original call. And we save the return volume to the stack. And then we will run all the fexit BPF programs and put the perceptual refer. And then we escape the RIP and return to the corner, which is what BPF global call, what BPF trapline do. And this is the entry of the global trapline, which is right in a naked function. And the logic is the same as we said before. We first we will alloc the space in the stack, and we save the function arguments. And then we will call the BPF global corner ring. This is a function that write in C. And in that function, we will do all the stuff. So as we can see, most stuff is done with the C code. According to its return volume, we will decide if we should return to the corner or we skip the corner. If we return to the corner, we will restore the register. So let's have a look at the function metadata. Generally speaking, it's a hash table, and it is implemented by the hash table. The key is the function address, and the volume is the struct kfun MD. The way it manages the BPF programs is similar to what we do in the BPF trapline. It have an array of hash list, which is used to manage the BPF programs. And the kfun MD trap program is added to manage the BPF programs. And the following functions is added to manage the function metadata, including correct, get, and put. And the BPF link unlink is used to add a BPF program to the function metadata or remove it. So let's have a look at the release of function metadata. The function metadata is used in the global trapline, so we can't free it directly. In the global trapline, it is protected by RCU read lock. Depend on if original call is used. In the non-original call case, all the BPF, all the function meta lookup and the use here is within the RCU read lock, as we can see in the diagram. So in this case, we can free the function metadata directly with the carefree RCU. And in the original call case, it's a little complex, as we use both RCU read lock and perceptual refer to protect the function metadata. So first, we will call RCU to make sure that this code path has exit, and then we call the perceptual refer queue in its callback to make sure this code path has exit. And in the callback of the perceptual refer, we can free the function metadata directly, safely. Then let's have a look at what we did to the verify and how we do the attachment. During loading time, we didn't specify a BTF type ID for the tracing multi BPF programs. Therefore, we don't need to. Therefore, the tracing multi programs is not BPF type available, and we can't access the function arguments directly with the context. And if we want to access the function arguments, we need to use the BPF helper, BPF get fun argument. This with this way, the implement will be a little easier, and the use here is a little not even convenient. So I'm thinking maybe we can record the maximum accessed function argument index during loading time, and during attach time we will check that if all the function argument count of all the targets is bigger than that index. Therefore, we can access the function arguments with this way, which looks a little convenient, but it's not a big deal, as we have many other issues to talk about later. So let's have a look at the attachment. We introduced the BPF global link for the global trap line, and it has all the target information, includes the attached cookie, the target IP address, and so on. And the left is the kind of functions that we added to do the attach and the detach works. Then let's have a look at the attachment of trace multi. Generally speaking, the logic is simple, except that we need to check. We need to do the mixture of the global trap line and the BPF trap line. If we hawk a target with tracing and tracing multi together. During attach time, we will iterate all the entries in the link, and we will create the function metadata for the target, and then we will add the BPF programs to the function metadata. Then we will check if a corresponding BPF trap line exists. If it exists, we will fallback the BPF programs to use that trap line directly. And if it's not exist, we will add this IP to a IP array. After all this works, we will call the update ftrace direct add to add all the function address which we didn't fallback to the direct ftrace oops. And this is a function that Jerry added in his series. During the fallback, we will unlock a BPF sham trap link and add it and link it to the BPF trap line. This is the modifying that we did to the tracing as we need to use them together. During link time, we will check if the target is already attached by a global trap line. If it is, then we will look up the function metadata with the function address, and then we will iterate all the BPF programs in the function metadata, and then we fall back all the BPF programs to the current trap line. And then we will update the trap line. During update trap line, in the register F entry function, we will check again if the target is attached by a global trap line to determine the function that we used to do the update. If it is not hooked by the global traffic line, the logic is the same as the current. We call the update abstract direct add. And if it is hooked by the global traffic line, we will call the abstract direct mode to modify the direct call of the target from global traffic line to the current traffic line. The logic to check if it is halted by the global traffic line is simple. We only need to get the direct talk of the target and check it if its address is BPF global corner. This is a use case of how we use the transit multi. The usage is similar to capital multi, and the wildcard is supported. As we said before, we need to assess the function argument with the BPF helper. So let's have a look at the performance and the issues. The performance of the attachment is fast enough, as I think. It takes about 0.3 seconds for 50,000 connections. This solution do have many issues. The first is that we need to maintain the global traffic line and the function meta stuff for the global traffic line. It is partly architecture specific. Another problem is that static argument is not supported, so we can't use the global traffic line for the targets whose argument count is more than 6. And for this case, we can fall back to the BPF traffic line, which I have not do it yet. The fallback logic is the same as we said before. For the IP modify case, we can use the BPF global traffic line too, as the function address we get from the stack is we can use that address to get the function metadata, as it's not the function address that we add the function metadata. And for this case, we can fall back to BPF traffic line too. Another problem is that jump model is not supported by the global traffic line. There is nothing we can do for this point, and the jump model is something to optimize the performance of original core, which is supported by the X6 for now. The biggest problem is that the performance decrease. The overhead of the global traffic line is bigger than BPF traffic line. The main cause is the overhead of the hash table. It's faster, but it is still a little heavier for the traffic line. Other cause may be that we did more extra memory read, such as we read the BPF programs from the function metadata, and we did more condition checks. And this is the bench performance that I did before. As we can see, the FN3 multi, the performance of FN3 multi decreased about 25%. And I'm not sure if it is acceptable. And for the this test is done without the jump mode supported. So in fact, the performance of exit is much better than in this test. It can up to 130 M per second. For the performance of FN3 multi, an idea is that we can optimize it by the function pending based high table. It's totally another stuff, and I think let's not talk about it here. And that's all. Any questions?
Okay, I'll go. How important it is to actually give. So you mentioned that like for multi-F entry, right? Like you keep track of like the maximum argument that's accessed, right?
Yeah.
Why do you need that? Like because you want to give like typed arguments if you have a multi-attachment that like for functions that share the same prototype or something like that?
Do you mean this part?
Yeah.
The thing is that I think it will make it easier to use.
But
As
that's
we
add
can see,
complexity, right?
as we can see, we need 3 line here, and here we need only 1 line.
Yeah, that's.
Of course, we can use we can define some macro to make the write simple, but it's not a big deal.
Yeah, so that's the point. Like I feel like that's just unnecessary complication, probably. Like if you have BPF core cast, like you probably don't need to like worry about determining like which arguments are common between multiple target functions. The point I'm making is like I think I would skip that last part.
Skip this part.
Yeah.
Yeah, I think it's okay. It's not a big deal.
I'm interested in knowing, have you played around? So the one use case that I've always wanted BPF Trace to be able to do, which is BPF let you do for a long time, is to trace everything and get like a full call stack trace. I mean, Red Snoop is great and everything, but it'd be nice if you could have all the programmability of BPF Trace and be able to do just like the I want a call stack with everything, all the information. Have you tried doing that? Is that output with this patch? Is that performant enough now? Because I've tried that like every kernel release, and every kernel release it like locks up my machine when I try it. So with this patch set, is it actually, can you actually do that? Like BPF trace everything and like log, like show the stack trace with that. So basically trace absolutely everything and get actual information out of it.
Sorry, I need some help.
Sorry. I'll say it slower. Sorry. Have you tried, sorry, with this patch set, have you tried like using BPF trace to trace everything and get like an actual stack trace out of it? Because it's something that I've always wanted from BPF trace. Sorry, I mean like a call tree is what I mean. Yeah, like the F trace graph tracer, but with BPF trace.
Do you mean that trace all the kernel functions?
Yes, and logging their executions, entry and exit. I don't think it's about the speed. It's more about safety. Like there are still some functions that you should not be tracing that are not marked as such. And so like if you trace them, you might deadlock or crash the kernel. So you have to be careful about like tracing errors, because otherwise like Redstone can do it. So this thing doesn't make this. Yeah. So this thing doesn't make, as far as I understand, doesn't make the like runtime performance faster. It makes the attachment faster. But it doesn't fundamentally change it. All right.
So
thank you very much.
That's all. So thank you.
Right. Next talk is by Yurji about uprobe optimizations.
Okay, hi again. So yeah, my name is Yurji Olsha, work still at Isabel and at Cisco. This presentation is basically to give an update on uprobe optimization and the new uprobe override feature that went in just recently. Okay, sorry. So I will start with the uprobe optimization. So there's been new changes that actually made it to the kernel. So as of now, we are able to optimize uprobe if it's placed on top of 5-byte NOP instruction. I have a few slides later on, like if we can do some more general case later. All of it that's concerning the optimization is actually just on x86 64 architecture. So before I actually dive in, like what's been in, I understand that not everybody is spending time on the uprobe, so I will take just like quick reminder, so we are on the same page. So uprobe, basically like the user space probe, you can put the probe in your application. When you pick up where you actually want to put it, kernel will install the breakpoint. And when the application goes through that breakpoint, it throws exception that gets you to the kernel. We execute the BPF program. And before we can actually return, we need to execute the original instruction. I will go a bit deeper here because it's helpful for the next slide. So there are two ways we can execute the original instruction. Either we can emulate the instruction. That actually means that we simulate the results of the instruction. So we have the ptrx instruction of the user space application. So we have like all the registers at the state when the application was interrupted. And we just emulate the instruction. So we just change some registers values, whatever the instruction was doing, perhaps also change some memory. So if we can emulate the instruction, we have support just for a few of them. It's like very fast. So if we emulate, it's the good case, and we go back executing the application. Or if we cannot emulate, we need to do the single stepping, and that's the slow part, because we need to take the original instruction, put it to the user space, direct the execution to the user space, single step the instruction, throw exception again, go back to kernel, and finally go back to execute the original code, like to continue in the application. So that's more involving, of course. So yeah, that's slower. So now what we can actually do with the optimization. So if you are lucky enough, and there's a use case for that, so it's not just being lucky. So if you are on top of NOP5 and you want to install the uprobe, what will happen now, kernel will actually detect that, and it will install a user space trampoline to the process and override the NOP5 with the call to the trampoline. The trampoline will execute the user's uprobe syscall. The syscall will execute the BPF program. There's no need to execute the original instruction. It's NOP instructions, not doing anything. And when we do that, we just return to the execution of the application. So basically, and the speed up is basically in executing the uprobe syscall compared to the previous exception, like the breakpoint exception, like on x86. It's basically like three times faster. So what's the use case? So use case for that is it can be used in the USDT. It can optimize the USDT. USDT are sort of static probes inside the application. Basically, the programmer can use one of those two macros. One's coming from SystemTab, the other one from libbpf USDT project. There are probably more. I'm aware of those. And basically what you do, you use that macro in that code somewhere where you want the application to trace. And that macro will emit the NOP instruction at the moment. And then the libbpf or some other library will install the uprobe on top of that. So we can actually change those macros to emit 5-byte NOP instruction. And like that, we have optimized the USDT probes. When we're running on the kernel, that actually allows that. To keep the backward compatibility, like, of course, you can have like new application that emits the NOP5, but it can be run on kernel that doesn't support the optimization, not even the emulation of this instruction of NOP5, which would mean if you triggered the USDT on the way back to the user space, it would actually need to single step the NOP5 instruction. So that would be performance regression. So what we actually do instead, we emit like combo of NOP1 and NOP5 instruction, and libbpf, when it's actually installing the uprobe for the USDT, it detects if the kernel can optimize or not. And based on that, it plays the uprobe on top of NOP1 or NOP5 instruction, and like the other one is just executed. So that's what we can do now. The code is in the kernel. The other code is coming in. I have a few slides on if we can actually go further. That means if we can cover actually more instructions. Like if you put the uprobe on some generic instructions, if you can do the same workflow to actually optimize it. So I did the RFC patch set that actually does that and tries to optimize uprobe on top of emulated instructions. It has problems. I will get to that. So here you have the one of common prologues that you can meet in the user space application. The patch set makes all those three instructions emulatable. Well, push was already there. Now we can emulate mov and sub. And basically, we override those instructions with the call to the trampoline, and the rest is pretty much same as we did before. There's a trampoline, there's a uprobe syscall. We execute the BPF program, and then we emulate those instructions. And when we do that, we return. We need to change the return values on the stack, like not to return after the call of the trampoline, but we need to return after the third instruction that we actually overwritten with the call instruction. So as a scheme, that works nicely, but it has problems. And the most fundamental one is like we need to be able to update, to write the call instruction in an atomic way. So there can be case that actually other threads are executing that place already. It can be executing one of those three instructions. And if you put, if you write the call instruction on top of that, that most likely will crash. Already, like when we do that on top of NOP5 instructions, it's like not easy. We do like this step-by-step optimization. We like need to put the breakpoint first. We update the second half of the instruction. Then after that, we update the call op instruction. So it's been more involving. I didn't get much feedback on that, but I'm assuming that will probably crash. Maybe there's way out of it, but yeah, it's more involving. So at the moment, when we actually do that, when we install the call instruction, we do that at the time when the uprobe is hit, like for the first time. The application is already running. Perhaps if we do that early, when the application is being loaded to the system and nobody's running it, that might be the case. But then, yeah, that would deprive us of the. Well, there's another use case when you want to trace already running application, and that would not be possible. Or perhaps there is a way to stop the process completely, but it has also some problems. So this is an open issue. I'm really not sure how to fix that at the moment. And it's not enough. Another issue is like if we actually manage to solve that, there can be later part in the code that jumps in the middle of those three instructions that you just overwrite with the call instruction. So most likely that would crash. That's probably not problem for the prologue, right? Nobody would jumps in the middle of the prologue, but as uprobe is generic, then it can be placed anywhere. So yeah, my only idea here is to put it behind the CCTL knob, but I understand that's not like favorable solution. Yeah, so that's for the uprobe optimization part. The other part of the presentation is the uprobe override. So basically, the uprobe override is a new feature that allows to control the user space application, the execution of user space application from the uprobe eBPF program. And we have a use case in Tetragon where we basically would like to detect like if application is going through the some CV path, like some security breach path. And well, we can do that, but at the moment we can only just like kill application. And with this uprobe override, we can actually skip over the bad part, we can actually.
There's some question probably about the first part of the presentation. Maybe we should.
We can do it now. Sure.
Yeah.
It's Mathieu. So I was curious about the problem with the call. What's specific about it, and why can't you patch it?
I didn't hear that.
Can you repeat the question but louder?
Yes, of course. Can you hear me better?
Better. Yeah.
Just a touch.
A little.
1 second. So sorry. Okay, is that better now?
Oh, go ahead.
Okay. Sorry. So what's specific about the call that the breakpoint bypass technique cannot do to fix it, to patch it?
Do you get it?
Oh, the call.
Yeah. Sorry,
Which call are you talking about?
So the call instruction. So what is wrong with using a breakpoint bypass to patch the call instruction?
Okay. If I understand correctly, you're asking like, what's the difference to the NOP 5 update? Like,
Yes.
so the difference is that now the call instruction spans over multiple instructions, and yeah, before we were on top of one instruction, right? So we didn't need to care about the rest of the execution. But it's possible that there can be another thread, like not executing the first instructions, but being like on the second, on third instruction. And one thread will actually change that under the second thread. Like,
yes. So there are various techniques to go around that, some of which can use jumps to specific areas of memory, kind of aliasing instructions that follow and everything. So I can give you pointers about this.
So there's a way to override it somehow to do it? Okay.
There are ways to work around that. So I can point you to a paper about this.
That would be great. Thanks. That would help. Thanks a lot. Perfect. Okay, where was I? Okay, all right. So yeah, we have a use case in Tetragon, as I was saying. So we can detect like the security breach in the application, but we would like to do more than just like kill application. Maybe just jump through it or emulate the fix. So that's why we introduced the uprobe override. And basically what it means is that now from uprobe program, you can actually change the registers of user space application. So up to now, up to like 6.18, the context of the kprobe program was like read-only. It still is for kprobes, but for uprobe, like when you have uprobe program, you can actually do what you have in this code. It's as simple as just referencing the context. You pick up the register, you write the value, and application will actually see the new value. There's a bit of the change in the behavior. So up to now, if there was a like uprobe callback handler, not the BPF program because it couldn't write now, but if there was like another uprobe user and it changed the IP address, we still were executing the original instruction, even if like the callback directed the execution someplace else. We stopped doing that. So if you actually decide you want to jump someplace else in the application execution, we will no longer execute the original instruction. So we can do basically with this setup, we can do actually what we are allowed to do in the kernel. Like there's a override helper in the kernel that allows you to override some functions, not all of them, some small subset of functions. And basically now you can do it in the user space for like any function that's being called by call instructions. It's a bit of involving you actually to use it properly. Like you need to study the application, you need to disassemble and make sure that you know what you are doing. So if you have uprobe on top of the function entry, you can override the function just by reading the return pointer from the stack and updating the stack pointer, you might want to also maybe change the return value in the AX register. We are still like starting to use that, and when we were discussing what we might actually need, we came to this case. Like plenty of those CVE fixes is that if you have the fix for the CVE, plenty of that is that it's inside, like deep inside of the function, and you actually check whatever variable, so check some condition, and you just exit that function. So we were wondering maybe we would need to do maybe some helper that helps you unwind the register, so you can end up on the beginning of the function and easily override that function. But so far, actually, we didn't need to do that. It looks like most of the things we can just bypass by jumping over some function or just jumping to some other execution. It's more involving. You need to study the disassembly a lot, but yeah, it looks like whatever we have now is enough for what we are doing. And with that, that's it. If you have any questions.
So you mentioned you need now a special trampoline, right, for uprobes. Who allocates it? Kernel, or does the app need to cooperate?
Yeah, it's allocated by kernel. When it's installing the uprobe, it will put it to the space by itself.
Okay, did you run into any weird apps that care deeply about their address space layout and get confused because of that, or is it mostly okay?
So as I said, so the optimization is happening after the application is executed. So the idea is that the initial layout of the application is already done, and the trampoline is actually installed as another VMA, like one page in the application, which can be used by something else. So for application is just another used memory. It needs to use some other memory. So
okay, thanks.
For the uprobe override thing, actually 2 questions. First one is that hidden behind some config option? Like for kprobe override, you have to enable this kernel option to have it available. Is it the same for uprobes, or is it just like by default enabled?
You mean if you can override the register values just like that? Or?
Yes.
Yeah, there's no option. You can actually do it right away.
The app doesn't have to do anything, so you can just like do it, right?
Yeah. Once you have that change that went in 6.18, it's just read-write now. For uprobe programs, you can write to the context.
Okay, thank you.
Do you know what's the situation when it comes to uprobe performance on ARM today?
Performance of what? Sorry.
Of uprobes on ARM64.
Oh, on ARM. No.
Okay, thanks.
Sorry about that. Yeah, the work was
what exactly
directly
you asking about, like about performance? No. It's interrupt based, and it's actually harder to optimize like using this node 5 for the preamble.
But actually, there was some. So before that, we did the optimization for return uprobes, right? And I remember somebody was actually trying that for the ARM. They did it, but they didn't see any speed up, like by using the uret probe syscall instead of the exception on ARM. And so I think it just died because we didn't.
Yeah. So or on ARM64, it seems like there is not so much penalty for like interrupt versus syscall. On x86, it's like 2x difference, right?
Yeah.
So.
I was just wondering, were there any other workflows you had in mind for the uprobe overriding stuff, aside from like fixing CVEs, I guess, in prod?
Yeah, so that's our main workflow now. The use case, like, yeah, we have like that environment that cannot be updated easily. So instead, until the next update, we need to like bypass the application, not to run into the CVE like scenario. So yeah, basically that you put the uprobe, you try to detect that it going through that security breach, and you override it.
Is it, I guess, mostly for like user space applications that you don't have like really tight control over? Like I'm thinking of like system D or stuff that's like tied to the distros themselves. Or is it just like, it's like lead time, right? Like you just don't want to have to like rebuild, redeploy your application service to patch the CVE. Like it's
Yes, but yeah, there are environments like where it's not as easy to upgrade. So meanwhile, that's the.
Hey, do you have a what's it that any plan to fix that the what's it the jump into the intermediate instruction for the what's it that the uprobe optimization?
You mean doing jump instead of the call, or?
Oh, you said that what's it that the second or third what's the instruction will be what's it that the jump target?
Do you mean in this case? Or?
No, the uprobe optimization. Yeah.
Sorry, I didn't get that.
So that do you have any what's the plan to solve with any tool or something like that for what's say that for ensuring that that there is no jump? Yeah, from.
I mean, I think you're talking about.
Oh yeah,
this thing.
Yeah.
Okay. Yeah, I don't think there's like good way to actually find out about that. It's because we, as a kernel, you have no idea what user space is doing. So yeah, that's bad.
Is there any concern to introduce uprobe override? For example, kprobe override will be restricted using LSM lockdown.
Yes, so kprobe override is limited to the small set of functions, right? So, and for user space, yeah, basically you need to know what you are doing. So and I don't think there's like way to actually reasonably limit it, if that's your question. That's like.
Okay. Kprobe override has to maintain like kernel integrity. That's why the functions are limited, right? Like it's the functions where we know that like if you don't enter them and just like exit with error code, like the kernel logic will be fine. That's usually like syscall entry and all that stuff, right? For user space, like I mean, it can be like any random assembly. And so you have like no idea about the structure of the code. But also, if something goes wrong, the worst thing that happens, the process crashes. You know, like kernel will maintain integrity. So I think that's like a big difference between all the, even like the user uprobe override, right? Like if you get it wrong, like what happens? Like crash maybe, you know, or corruption. Who cares? Like user's problem. But like if kernel crashes, then it's a little bit more.
True.
Yeah. Protect kernel, no matter what. That's not kernel, who cares? All right, I think we are out of time, and thank you very much. Let's have a break and come back in 30 minutes, right? Yeah, okay.
Should you care? Because we're trying to get rid of it.
Friendly, and people love to talk about what they're doing.
We all have found this space here because we all want to better technology and we want to do it out in the open.
Without community, it doesn't grow.
That actually they added.
All right, we are continuing our day with Yong Kong's talk. Alan is online. No? He's here.
Oh yeah, he's here.
He's online.
I will join later. Wait for.
Try to stay close to the mic. So that
Okay, I will do that. Wait for a few seconds for people coming. Okay, let's get started. And so today, and Alan and myself, and we'll talk about how to supply or get true signature to VM-Linux BTF. So get next one. So this is basically the current VM-Linux BTF and encoded the source level signature. And just for example, in this particular case, right? And there's a function and map create. And it has two parameters, the attribute and the U attribute. The second one actually is a struct. And it becomes a socket pointer, and it has two fields. One is union, another is Boolean. So this is the true, basically the source level signature. And we'll encode the VM-Linux BTF. And there's a bunch of functions and in source level, but if these functions are fully inline, basically there's no leftovers. And in such cases, and the function itself will not be appear in the VM-Linux BTF and at the basically the case symbols. That's obvious, right? And for the rest of functions, and PAHO actually see all of them and do some processing. And in some cases, and there's some static function which has the same name but in different files. In such cases, and the PAHO will fill out these functions and at this point. And in the future, and it could be differentiate this function by address, but not now. But actually, and a compiler and could do compilation optimizations, right? And so in this particular case, for example, the map create original signature is something like two parameters, attribute and U attribute, and in LLVM, and it could be optimized something on the right, and so the top LLVM IR is after optimization, and it has two parameters. One is a pointer, another is a I8, basically is a unsigned character. And so this is quite different from the previous one. You have a BPF pointer type. And eventually, and through later on I will explain, and eventually, and the true signature for this mem create will be the first attribute will be the same as source. The second actually is a Boolean. And just because, well, the kernel or user thing is not used. So compiler actually just get rid of that and make it simple. And before we go to details, and I want to share some basically signature change difference between GCC and LLVM. And LLVM try to maintain the same function name, even the signature changed. So you will have no clue and whether and your signature changed or not, and just based on the name. And the GCC, on the other hand, actually has various suffix to identify and a signature change. For example, I list a bunch of functions, and the GCC has a suffix I, SRA, or has a constant propagation. Sometimes can have both of them, or even three of them. And so GCC functions, and this is in case symbol, and they will identify a different signature compared to the source. And I will focus on the LLVM right now, and the Alan later on, and we'll have some detailed information about the GCC. And let's look at the LLVM side. And how do we really get the true signature or modify the signature in LLVM? And the LLVM in this particular case, and the function parameter has this pointer and I8, basically the unsigned character. And to get the true signature, and basically we actually need a type, right? And precise type and the name, parameter name. And what we do here is in LLVM has the debug, because dbgj value here, and it provides information about how to get the value, basically how to get the parameter and through the debug info, or you can consider it's a DORF. And for example, basically there's a percentage 0 or 1 and this parameter, and corresponding to 2 dbj value and 0 and 1. And this 14906 and 14907 and is a pointer to basically you can consider a debug info. And the debug info is similar to the DORF, some variable thing. I will see the next slides. So there's a DI expression here, and basically means for this specific debug info, you try to take a fragment of that. And the fragment is 64 is a bit offset, and the 8 is the size. Basically, you shift by the long type, and then you take basically the unsigned character. So let's go to the next one, and it will be much more clear and what it looks like. So the attribute itself, so basically it is the first argument, and the second argument is a U attribute and the debug info, and we'll go down to the BPF pointer type, and then go to the socket pointer type, and then become a struct type. Struct type has 2 members. One is union, and this one, and another is basically is in the Boolean. In this case, is kernel. And in this way, the offset is 64 and the size is 1. And the compiler somehow internally, and we can conclude the second argument is the one we try to use, which is kernel. And this will go back to the final signature is like this, is the attribute, and the Boolean is the kernel. We try to reuse the name and in the debug info. And to be a summary, and to get the true signature in LLVM, for everything it changed, and then we will use the LLVM DBG, and there's different flavors, value, declare, assign thing, and we try to use this information to get the semantics and name of the parameter. And the return value is also and can be modified. And for example, the function itself, and it has a return type, but it is never used. And then the LLVM will change its type to the void. And there's the LLVM implementation link here. And this process has some drawbacks, and the reason is it's not clear in the future, and all this LLVM DBG thing is changed or not. Sometimes it could change, or something they may modify, or some additional patterns. And so in the LLVM side, we implemented remarks. Remarks you can consider is a debug thing. And the functions can enable remarks. The remarks can give you information about what's wrong. And it will provide a path, and it will provide basically the function name, and also what happens here. You can in the remarks, like a debug thing, you can have some string, and you can consider, okay, this is string for what purpose? In this case, is create a new int type like this, and the basically argument index is 0, means the first argument, something like that. They give you some information you can trace back, and to basically find what's going on and make LLVM better by fix it. And the make LLVM equal to 1 and V equal to 1, and we'll be able to dump all these remarks, all the debug info. And now we have a true signature, right? And then we want to encode all these true signatures to the IR debug info. IR debug info essentially will be generated for DORF. And in this particular case, we create a special compilation unit, CU. And this special compilation unit has a file. It's called string signature. It's quite different from other files. core.c, syscall.c, we just create basically a file here. It is a compilation unit. And then it will encode all the signatures in this CU. But it will link to the original source, basically original source, and which will have a same name. And like in the DI subprogram 1, 2, in the syscall.c, or in the core.c, there's others, and we try to link. We try to link. The reason is later on we will be able to know the relationship. So we may try to overwrite.
Question? So if I iterate CUs, right, in Dwarf, how do I know that this CU is CU with the original signatures? Like, is there some flag or just naming convention?
Yes, this is the original one, source level.
Mm-hmm.
And this is a new signature.
Oh, like new, but like this in the middle, right?
Yeah.
What's the name of the CU then?
Yeah, the name will be the same. That's why we cannot really put it here.
No, you have file change signatures, right?
Yes. This file you can consider is artificial. It can be anything. It's just an artificial compilation unit. A typical compilation unit is based on the file, right? You have a file, and then the whole file will be a compilation unit. You have a bunch of stuff. And this is just create a basically artificial compilation unit, and we put it there.
So is there some naming pattern that you're using?
Oh, this is just arbitrary. I mean, you can be anything. And the naming is here, and for the function itself.
Okay.
Yeah, just to make things easier, and we do not want to pollute and for the original CU. So we create a new one. And once we have the debug info, and then we will try to generate the DORF. And currently, there's no DORF specification about how to encode these new signatures. And we tried 3 or 4 different approaches, and eventually we come up with this approach. Basically, the compilation unit, and under compilation unit, you have a bunch of sub-program or other stuff. And then we also have an inline subroutine. And this inline subroutine currently isn't really not conform to the DORF standard, but it works as its purpose, because this one, since it is not really DORF standard, so people will not pay attention to this one. This one will be ignored in most cases. And we can use this inline subroutine, and we have a true signature encoded below that. So in this case, in Panho, and we will be able to find this inline subroutine and get a true signature. We can overwrite the original source one. I will discuss later and about alternatives, but not now. And let's go back to some examples about the map create. And the true signature in here, and it will be, this is a link to the original map create. And so the artificial typically means the function is generated by compiler, is not by source. So just, and then the formal parameter is like this. And the first one is not changed, the second one actually is changed. And LTO and has a little bit more complexity here, and because LTO at LLVM, they may try to promote some static function to global, and in order to prevent a clash, basically it's some kind of like a symbol clash, and then they use this function.c. Give me a second here. Function, oops, the curve. basically it will use a name like enable step.llvm.hash. And there's some discussion here in yesterday's live patch as well. But in this particular case, we will just mark these names. And all other actually will be the same. Other parameters will be identical. And when, in most cases, and once this enable step is promoted to with LLVM suffix, this function itself is gone from K symbols. It is completely gone. And why we want to have this basically the symbol, complete LLVM and suffix symbol, and in the BTF, there's a couple of reasons. And first, with give a summary about the new functions. This what kind of new function we will import to the PAHO. And if a function does not have a dot, that means that this function absolutely has a signature change, absolutely. And the second one is if a function does has a dot, and then it may or may not have source function change, so source level signature change. And we don't really care whether it's changed or not because the current VM links doesn't really have this entry. So we just give an entry to that. So all new functions exist in K symbols. So we do not have an artificial function which is not eventually in the symbol table. And just a couple examples here and how this will be handled in PAHO. And for the map create, there's no suffix in this case, and basically we just overwrite and the previous one in VMLinks BTF. And for function with dot, right? And in currently, and if you look at the KO symbols and all these symbols like enable step.llvm dot something something, so is the symbol itself actually has a dot something. Basically, that is a true function name. And if you look at the available filters functions or available filter function address, they are the same actually. They have also has a dot. So the idea is we want to consistent and in VM Linux BTF and corresponding to the K symbol and all these available function filters. So you can have exactly name here, and the name here, they are the same. So it makes things simpler. And how to handle the new function with dot, and basically in this case, and in the PAHO, and the current PAHO is filled out all the suffix. And in PAHO, we should avoid such removing the suffix. That way we can generate a VMLinks properly. So this is a little bit of details, but just mention that. And we need a new feature in PAHO, and this one will be off by default. The new feature, I name it as a true signature, but it can be changed. And if this is true signature is on, and LLVM and path is on, and then we will be able to generate the true signatures in VMLinks BTF. And how to build these things, right? In kernel, you need a build thing. Currently, and because the feature and we implemented in LLVM is off by default, and so we need to have this LLVM enable changed function, basically debug info, and so this thing need to be enabled. And this is for the LTO version, and basically LD flex for LTO. This is for the non-LTO version. And we need to add this feature and for the PAHO script, and all this and with all these things and the PAHO and LLVM and the kernel, and then we will be able to build the VMLinks BTF, and which has true signatures, and also including functions with dot. And there's a little bit of statistics about basically what's the overhead and basically how many functions, and we will add it and to the VMLinks BTF. And currently you can see we have quite some, and 66K and a little bit more than 66K, 66227 functions, and for LTO and 66051 functions. And this is for the current one. There's no LLVM involved, involved here. And if we enable the change the function debug info, and then we will get additional, basically this is in the inline subroutine thing, and we will get additional basically changes. And for non-LTO, we will have like 894 functions, the signature get changed. And for LTO, there's a much more. But LTO is special because they have a dot. Some of the signature actually not changed. They just change it from full dot, change it to the full dot LLVM dot something. Signature may not change. For the size is not a concern either. And for example, and with new signatures and for non-LTO, we just added the 14K bytes. It's not too much. And if for the LTO mode, and we get like 64K, rough like that. So it's not a big deal actually. And to add these new signatures and add the signatures with dot, functions with dot. And previously, and for tracing, and we cannot really trace function like func.llvm.hash functions. We cannot do that because the Paho actually filter out all the names suffix here, and they just encode the function C. But in the kernel, and the actual function name comparison, you are compared to this with the suffix, basically full.llvm.something, and that will fail. So you cannot really do fng. And if we have this function name, and then you are able to do the basically fng, fexit, things like that. So typically, I mentioned that we can have a function somewhere, either libpf or could be the self-test or somewhere, and it has this function name, and then you can go through the key symbols and try to find out whether it's this guy or this guy plus .llvm.hash. And then you use this set target, and then you will be able to successfully do the tracing. And the true signature is not just used and basically for the function and the existing function, it can also used in the inline functions, because inline function, once you're inline, and then you also need to have some kind of like parameter there. And so the Alan is actually working on this, and so the most thing and try to do is probably use the locations and at this point, and try to find out the parameters. But I will focus on the LLVM side, and Alan will explain a bit more on the GCC side. And for the LLVM side and the non-LTO mode, and the inlining is always happens between any signature change. That's what the LLVM designed. So at the inline pass, the debug info will amend it, and so the DORF generation will represent it with the inline properly. And they will use the original source code, or original source signature. It's just like this. You're doing something, optimization, and then you have an inliner, and the inliner use a source level signature. After that, you may do some optimization, like dead argument elimination or argument promotion, things like that. So you will use the source signature. So this is an example. And for example, you have a full bar and a bar called full, and inside the full, you call external function tar. And in this particular case, at this point, inline pass, and you will find actually there's a bunch of stuff here. But the most interesting stuff we want to mention is the parameters and for this full, and actually is the debug info 28, 33, and 34, corresponding to the argument A, B, and D. So in this case, and the DORF will generate things like this. It will be the 3 parameters, and for the inline function. Oh, okay, sorry. Yeah. And for the thin LTO, for the thin LTO, it's a little bit more complicated, and because you do an inliner, and then you do a signature change, go to LTO mode, and you do another inliner inside the LTO. In this particular case, it is possible the signature changed signature will be used for inlining. And this is another example, and we will basically do the signature change first and do the inlining. In this case, you will see the second parameter become a poison. The poison means, well, it's poison, it cannot be used anymore. So in this case, and it become 2 parameters. They use a different signature. But this only happens in LTO mode. And a little bit of caveats is an inline function may have a different signature than final signature. Basically, it is only for the LTO mode. And some optimized inline function may disappear from DORF. And just a simple example like here, right? And you have this Collie, and they just do some arithmetic, and you know the 100. And after this, it become a 1010, basically 10100, right? There's nothing you can do basically the inline basically function tracing because it's not there basically. This stuff is not there. So basically, it is possible in some cases the inline function actually may not be available for you. The rest of the next will be the Alan, and we'll present for the GCC side.
Hi, folks. Can you hear me okay in the room?
Yes, Alan, but like we are kind of short on time, so try to like speed it up a little bit, okay?
No problem. No problem. So there's 2 things I'm going to talk about quickly, which is the problem that Young-Hong has been speaking about, which is the true signature problem, and then the general problem of representing inlines so we can trace them. So in both cases, we use the dwarf representation, which consists of an abstract representation for the function, which is basically just a description of the source level function. And then you have the concrete representation, which is either the inline or the optimized version of the function. In both cases, we have abstract origin references from the concrete function to the abstract, which basically kind of link them in the dwarf representation. And for each parameter, we have those linkages as well. But the important thing is, and this is something that PL didn't used to do, is we have to pay attention to the ordering of those parameters because it can change in the concrete representation. Parameters can be left out. So we need to be a bit more careful than we are today. And actually, this is where we can sort of get some low-hanging fruit from the true signature work. It's not as complicated as the cases Young-Hong's talking about where parameters change, but we can actually spot where parameters are dropped when we have our optimizations in GCC. Young-Hong, could you move to the next slide, please? So this is just you can kind of see how it is here. But each of these formal parameters, there's an order, and each one, if it has a location, essentially in the concrete representation, it means it's actually a function parameter still. Now it could still be on the stack, or it could be a constant, but it's there. So we need to be a bit more careful in PL about how we interpret these. And if we actually interpret this stuff properly, we can get true signatures for those .isra and .constprop functions. And we'll do the same thing as Young-Hong was talking about, where we'll keep those dotted suffixes, because that gives us a way of the user way of knowing that there's something to trace there. And the important thing is, in those cases, you can use F entry, but for the inline case, obviously you can't, because it's not actually a function entry site. But we use the same process where we have this concrete abstract relationship, and again we pull out all the information from those sites, from those locations, and we actually manage to put together a representation of the locations of those sites. So if you could go on to the next slide, actually quickly, we'll just rush through this.
Next slide.
Next slide, yeah, thank you. So you can see an example here. This is just with the true signature stuff. Parameters are reordered. Most of the time, parameters are just dropped because we don't have location information. But we're going to end up with BTF in the same way as Young-Hong is generating it for LLVM, which actually reflects what the code is. So that's much better from an F entry perspective. Now, again, as Young-Hong said, we probably have to come up with some ways to make it easier for the user, because handling these sort of changes and having a tracing program that's stable makes life a bit more difficult. We'll move on to the next one quickly. So again, we use a similar approach for inlines. We can find the site address using the low program counter, and we have a reference to the function and perhaps all the parameters. then we collate all that information into location representations, which give us the name of the function, the address where the inline site is, the function prototype as it would be at the source level, and then we actually have a location site for each of those function parameters, which can be the function parameter is gone, or it's in a register, or it's on the stack, or it's a constant. So that inline encoding, for about 400,000 inline sites, this is something Edward discovered, which was kind of a nice surprise, that we actually have location information for the majority. So about 70%, we have all the function parameters. About 17% we have incomplete, but for the vast majority of them, we're only missing one parameter. And then for 11%, we have no location information at all. But in fact, it's sometimes useful to know when a function fires, so particularly when it's inline. So even if it's an inline site, we don't have any access to function parameters, it can be useful to know that too. Because otherwise we can be blind to these kind of function executions. And when a function is partially inline, where in one compilation unit it's inline and another one it isn't, then you think you're seeing everything when you're seeing that non-inline function, and you're not. So with all of this, we can use kprobe tracing for those inline sites. So using the supplementary information about locations where things are in the stack or registers, in a similar way to what USDT tracing does for the BPF, we can retrieve all that information. And there's a sample implementation in the RFC series towards the end. So I think that's pretty much it. So yeah, I can hand back to you, Young.
Okay, so for the next step, and in the beginning I mentioned the format and is not great and a little bit against the DORF standard, and so I sent a list actually to the DORF discussion, and actually there's no resolution and no recommendations what to do next. So that's why I listed a few solutions here and how to move things forward. And the first one is what I currently try to do, and the inline subroutine. The second one is actually dump the true signature to somewhere in ELF binary, but not to pollute the DORF, basically. And like a BTF true signature or something like that. Will be the combination and with Alan's work, but probably need a LLVM and the GCC side as well. And the location sometimes can get some signature, but sometimes is missing. And see the Alan's previous presentation, there's still like 10 or 20%, and they're not able to get the signature. So we need to do LLVM GCC, do something for that. And another choice is we directly generate the VMLix BTF and by the compiler. And in this way, we will be able to encode the true signatures. And then we may amend that through additional things. And in the result, BTF ID or the PAHO. So this is a few approaches. And of course, we need to do actually the existing stuff as well. And in the LLVM, and currently is off by default. Obviously, nobody reviews that. So I need to push a little bit. And but that format, if we decide to change it to a different format, so I will need a new implementation. And for the GCC side, and again, and we need to work with Jose and Alan and David Frost, and try to define a plan and a timeline for the implementation and the design choice. Yeah, that's.
When you try to find the true signature, when the function signature is changed, you will rely on the fact that the code is changed, signature changed, but the debug info is not changed, right?
Yes, we use debugging info.
But I think this seems to be a compiler bug. Like they should change the DORF information because this is gonna break the debugger.
Yeah, eventually these things, and eventually some of them actually, and will go to the debug and the location. Yes, that's correct.
But what I mean is that the LVM, they should, when they do the transformation, the complete work they should change the debug information also.
Yes, it is. I know.
So I think probably the right way to do this, to track this, you use a metadata. You add a metadata to the IR.
Yeah, the key thing is we want to recover the signature and
use the metadata to track to the
the
original.
precise type and the name. That's a thing.
Yeah.
That's LLVM is the best place to achieve this information. Yeah.
More questions?
Just briefly, from the perspective of a debugger, like Dragon is a debugger that's kind of sometimes using BTF for understanding types as well. This is not fully upstreamed yet, but I don't necessarily care whether you have concrete or source level function signatures in the BTF. It would be really helpful to know which one is which, because right now they're source level. So if there's a flag or something that can be included to indicate this is a source level declaration versus this is a concrete declaration, or whatever we're calling the actual final signature for a function, especially in the Clang case where the function name stays the same. It would be really helpful to know what we're dealing with.
Yeah, I think the main goal we want to the source level signature is for the F engine and things like that, right? You really need a signature there.
Yeah.
Once. All right. Thank you.
Thank you.
Thank you. Go ahead. Okay. Hi, everyone. I'm Tal Zussman. I'm a PhD student at Columbia. Today, I'll be talking about our work on the Linux page cache. As it turns out, the page cache doesn't work that well for some workloads. We introduced a new framework, CacheEXD, which allows applications to use custom page cache policies implemented in eBPF. So as some background, the page cache has a significant effect on the performance of IO-intensive applications. By caching commonly used pages, it reduces disk accesses significantly, improving performance. In Linux, it uses an LRU, least recently used approximation eviction policy, which unfortunately doesn't work so well for some workloads, is fairly inflexible, leading to worse performance. One example of such a workload is a financial database, which handles many small performance-sensitive queries. For example, getting an account balance, while simultaneously dealing with a few much larger analytical tasks that aren't as urgent because they're not user-facing. This workload is known as HTAP-like. It's been studied pretty extensively in the academic literature before, and we can replicate it using a mix of GET requests and SCAN requests in a database. As this database handles the small GET requests, we see that the page cache fills up. The GET queries make up about 99% of incoming requests, but they use only small amounts of data because their access pattern is skewed and the request sizes are small. When a SCAN request comes in, it leads to the eviction of most of the GET data, since the SCAN reads so much more data from disk than the GETs do. Even though scans are only about 1% of all our requests, they end up being about 99% of data in the page cache. Now, why does this actually matter? Well, when we have another GET request, which has a skewed access pattern, it needs to bring in recently evicted data back from the disk down here. Effectively, we've been thrashed, right? We're bringing in data that we previously had. It got evicted from the page cache, and now we need to bring it back at a performance cost. Now, this is clearly a problem since the page cache isn't really flexible enough to do something about this at the moment, which means that if we care specifically about the performance of this workload, we're currently leaving performance on the table. So let's take a quick look at how we could currently try to fix this. You could either change the policy, you could use user space hints, or you can do application level caching. Changing the policy is hard. It's not something that you can easily do. The new MGLRU eviction policy was merged as an experimental policy a few years ago in v6.1. However, it took many years of effort to actually be upstreamed, and it's still not the default policy upstream as far as I'm aware. Additionally, changing the policy modifies the policy for all applications running on the system, and you can't really do application-specific optimizations in this way. In terms of hints, there's fadvise, which is an interface that allows user space to inform the kernel how it's going to use a file. Unfortunately, this interface isn't super powerful, and it's still subject to the kernel's underlying LRU policy. For example, we tested the mixed get scan workload that I previously mentioned with a few different fadvise options. With fadvise no reuse, we saw no performance difference. With fadvise don't need, we also saw no performance difference. And with fadvise sequential, we also saw no performance difference, right? So this is far from ideal. This interface, which claims to be able to, improve performance and provide hints in some ways, sometimes for some workloads just doesn't really work that well. We also tested with MGLRU, the new policy, which actually for some reason made things worse. And essentially what we realized is that these existing interfaces just don't always work enough to be a viable solution. So to summarize, we also looked at application level caching, which has its own downsides, one of them being that you need to kind of re-implement all of this logic in user space for each application that wants to do some kind of custom optimizations. I won't go into more details on the rest of this right now, but none of these options are really ideal. So our conclusion is that in order to actually fix this, we need to be able to change the underlying policy. This has been possible for scheduling and other Linux subsystems, which provide a modular extensible interface. As such, we propose CacheEXD, a framework for applications to use custom page cache policies. It's simple. User space developers can just load a policy without making any kernel changes, and it's isolated. CacheEXD uses per cgroup policies to ensure that each application can actually use its own policy that best matches its workload. In terms of customizability, we use Surprise, eBPF. eBPF, of course, allows verified user code to be safely executed in the kernel, and similar approaches have already been taken for scheduling and other subsystems, which again expose a modular interface for user space to define and run policies within the kernel. So how does CacheEXD actually work? In a technical sense, CacheEXD is a struct ops-based interface where we add hooks in the page cache for page eviction, page insertion, page access, and a few more operations. You can see these here. We have an evict folios callback where the kernel, when it wants to evict folios, it basically asks the BPF policy what folios it would want to evict. When folios are added, we call the folio added, and similarly for access callbacks to maintain all sorts of policy metadata. This turned out to be about 200 lines of code within just the page cache code. This was mostly to batch eviction operations. In total, we had about 2,000 lines of code to support additional operations and various other optimizations that we had. CacheEXD policies operate on what we call eviction lists, which are linked lists containing folios that are managed by the policy. Policies can have a variable number of multiple numbers of lists, which can be variable sized. And these policies execute on page cache events. Like I said, when something happens in the page cache, it'll then execute the customs policy eBPF functions. For example, when a folio is about to be inserted into the page cache, the kernel will execute the BPF insertion policy function, which will determine which list to add the page to. Right, so in this case, we add it to list number 2. When the kernel needs to evict pages, the eviction policy function will choose pages to evict from the eviction list and provide them to the kernel for eviction. So for example, we can specify that we want to evict from list number 1 and then get rid of whichever pages we so choose from that list. This is a fairly minimalistic API. But what we realized is that most policies, even complex modern ones, can be implemented either exactly or approximately using linked lists. CacheXD operates on these eviction lists with a set of k-functs that we implemented. These eviction lists are very similar to DSQs in SkedGXD for those who are familiar. They're effectively managed by the kernel, and BPF programs then interact with them. So we have a whole bunch of interfaces for creating a new list, adding pages to a list, moving pages between lists or within a list, deleting from a list, and iterating. So what can we actually do with CacheXD? What policies can we create? Well, let's take another look at this mixed get scan workload that we previously discussed, where we want to prevent the scan data from taking over the page cache. And we can use what we call an application-informed policy. The application, in this case LevelDB, which is a key value store, informs the kernel which threads are issuing scans by storing their PIDs in an eBPF map. And with CacheXD, we can actually have separate eviction lists for get data and scan data. When a page is inserted, the BPF policy checks to see if the thread adding it is a scan thread, and if so, adds it to the scan list. Otherwise, it adds it to the get list. Then when the kernel tries to evict pages, we prioritize evicting from the scan list. And in this way, we're actually able to preserve the get data and prevent the scan data from evicting it. And in doing so, we actually get a 70% throughput increase for GET requests over the baseline and a corresponding reduction in tail latency. So we actually see that, in contrast to the existing interfaces, by providing much more granular control and much more customizability, we actually can improve performance for this workload. We can also implement generic and modern policies with CacheXD. For example, just for the sake of illustration, this is what a least frequently used policy would look like. We omitted error checking and all sorts of other things. But very simply, we just maintain a BPF map with frequency data for each folio managed by the policy. We increment it on access, and we select the folios with low frequency for eviction when the kernel requests for eviction to happen. We ran some modern policies, for example, S3FIFO and LHD, which are recently published policies from academia, with real-world traces like the Twitter cache traces and YCSB. We see that in one cluster, MGLRU, the existing new kernel policy, was best. In another, the default policy was, we saw out-of-memory issues with MGLRU, which is why it has a 0 operations per second. And this just really goes to show how complex changing the page cache is, right? Even MGLRU, with all the effort behind it, there are still issues existing in the implementation. This isn't something that you want, you're an average user space developer deciding to go into the kernel and change the policy to get a few more operations per second for some reason. In the third cluster, we see that the LHD policy won, and in the fourth, LFU was actually the best. So while we can get really nice performance improvements, our point is that there isn't any one policy that really performs best in all cases. And that's really why we think that we kind of need this experimentation in order to not just improve performance, but also experiment with novel policy techniques. Small pivot, CacheXD uses per C group policies. By running workloads in a C group with a policy that best matches it, we can actually get better overall performance. For example, what we do here, we have one C group running a YCSB workload where it uses the LFU, least frequently used policy, and another C group running a file search workload in a loop, just searching over a bunch of files. And that one uses an MRU, most recently used policy. When we set the, let me correct myself. They're running workloads that best match those access patterns. And in our experiment, what we did, we set both C groups to use LFU, both C groups to use MRU, and then both C groups to use policies that best match their workloads, one using LFU and one using MRU. And while we see improvements, by simulating a global policy change, by having both C groups run the same policy, but a different one than the default, we do ultimately see best overall performance when each C group runs a policy that best matches it. And while that's expected, we think that that's significant to show that, yeah, you really do need this kind of per C group component. It's not just sufficient to globally change the policy to a different policy. You want something that you want to be able to have each application run what's best for it rather than some global policy change. From a technical sense, how did we implement this? We hacked together per C group struct ops by adding a new libbpf BPF map attach API, which takes both map and C group file descriptors. Behind the scenes in the kernel, we added a new BPF link type, which contains a struct ops map and a struct C group star. We then added the cache.ext struct ops data to struct C group BPF. It's a little bit of a hack. But really, it would be nice if there were a more generic way to do this. It seems like this is something like this or something similar is desired for other use cases in the BPF world. I believe something similar has been discussed on list for SCED-GXT and BPF out-of-memory policies. So we're just throwing our voice out there to say that, yeah, this is also something that we would benefit from and we think is a good use case for this. Another challenge is ensuring memory safety. When eBPF provides eviction candidates to the kernel, we need to ensure that these candidates are actually valid pointers. In our initial implementation, we had the kernel maintain what we call a valid folios hash table. When an eviction candidate is proposed, the kernel uses that hash table to check that it's actually a real page before trying to evict it. And if it isn't valid, the kernel ignores the page and chooses a page to evict on its own as a fallback. This solution was probably not the right way to do this. We were kind of reinventing the wheel. What we should have done was actually reference count the folios properly and use trusted pointers so that then we can use the verifier to ensure that these are actual valid folios that we're interacting with. Why didn't we do this initially? It's a great question, but really we kind of made our lives more difficult by having folios be placed on two lists, both the kernel's existing LRU policy list and also our cache.ext lists. And this was a mistake because that's significantly complicated reference counting because all of a sudden we have cases where folios have two reference counts when previously they should only have had one. We believe that the solution to this should be that folios should just be on one list. We should just be reusing folio LRU and kind of have folios either be on the default kernel list or on a cache.ext list. And then we can kind of drop this valid folios hash table entirely. What we're not sure about is if there are issues with the folios kind of losing this fallback of being on the kernel's list, but we don't think so. And we think if there are, that's probably solvable. To summarize, before moving on to further discussion, we really believe that cache.ext enables modern page cache usage. We can actually maximize performance by experimenting with different policies and choosing one that best matches the application's workload. No one-size-fits-all policy can really work best for everything. We also believe that this will enable new policy and innovations. This will allow developers to really experiment with caching policies in a real setting. Policies can also be reused across applications. This previously wasn't very simple to do with user space-based caching. We expect that most developers would select from a library of pre-written policies. So we've made about 8 of them available already online. More sophisticated users can, of course, write their own policies. And finally, as mentioned, each application can have its own per C group policy that best matches it, which enables multi-tenancy. So I've put together a few questions that we kind of had for the community. The first of which is the memory management subsystem really open to BPF and or custom page cache policies? Is there interest for something like this from the community? We've gotten a lot of enthusiasm about this project from academia, where people were immediately like, oh yes, great, I can run like machine learning caching policies in the kernel now. The question is industry also interested in this? We really do believe that this can improve performance and have a dedicated community behind it, kind of like SCED-GXT has created. And finally, I believe previously there was a discussion at LSFMM 2022 and LPC 2024 about MGLRU introducing BPF extensions. these were discussed, but we haven't been able to find any evidence of these actually existing publicly. So if anyone here has any more information about that, maybe someone from Google, that would be great. Thank you.
Can these policies have noisy neighbor effects? So if like my process's performance improves, but the other processes in the system slow down?
Yeah, so that's kind of what we tried to investigate with this per C group policy. We actually saw that because both policies kind of had better caching, we saw reduced discontention overall in the system. So even when, let's say one application has a policy that matches it and gets better performance and another application doesn't, we did see slightly improved performance for that other application because of that reduced discontention. I'm sure it's possible that there are some workloads where you will see some negative effects because maybe that other application was using pages that have been evicted by that initial application, but we weren't able to kind of find something like that. And also typically what will happen, that second application will bring in that page that was evicted and then we'll manage it under its own C group, kind of preventing its eviction from the initial C group.
Yeah, thank you.
Thank you for the great talk. Looks like you did a lot of great homework. So it seems that the next step should be obvious, post the patches and see how discussion goes. So you ask in this room what this room thinks, but in any, whether this room or upstream, there will be multiple different opinions. Some people will love it, some people will hate it. So you just need to be prepared and have a thick skin to get it through. But at the end, it will be, I think, your determination to see it land. But I think that from my point of view, so far, looks like the performance results are good and the chances of it succeeding and landing and being adopted is high.
Thank you. Yeah, all opinions are welcome.
Thanks. I'd just like to say, as a practitioner, I am excited by this work. I think there'll be a bunch of workloads where this has a much bigger impact than Shed EXT. So improving the page cache algorithm. I'd also like to see a read-ahead EXT, so we can tackle the issue of pollution. A couple of things that come to mind. I would like to see a layer so that we almost need a caching scheduling layer so that it can instrument workloads. And because we can see if a workload has frequency of access or recency of access or other attributes, and that layer can then choose which caching algorithms for each different application. Because a lot of workloads, people aren't going to tune this in the real world, and it'd be nice if it could tune itself, and so it could dynamically pick the right algorithm. Following from that, a different approach that has been done in the past is to have shadow lists or shadow caches where you spend memory to pretend as though you were honoring different caching algorithms. And then you can see over time, if I was doing MRU or if I was doing MFU, then who had the best cache hit ratio for different workloads, and then you can select it. This is another avenue where we could approach that as well. I would like it if we could just dynamically pick the right algorithm based on metrics, because this other approach using shadow caches can be a little memory expensive because you have to keep all the memory to track how different algorithms would perform. But I think it's exciting that we can even think about doing this kind of stuff. So I like it.
Thank you. So just to respond to that point by point. So on the point of read ahead, I believe there was a paper in ATC about a year or so ago called Fetch BPF that experimented with read ahead BPF policies. That's something that we were thinking about integrating as well. It should be entirely doable to do that. Secondly, in terms of the auto tuning, we were debating whether that should be something in user space. For example, some user space daemon that kind of tracks those metrics and then has some daemon that switches policies out in and out based on performance. The tricky part is that calculating cache hit rate or page cache hit rate from the user space. The BPF tools out there at the moment seem a little broken. It seems a little tricky to actually calculate that page cache hit rate metric. I don't know if the MM developers in the room have more opinions about that. Yes. So we looked at that tool a little bit, and it seems like some of the trace points that are needed or something is a little missing there. So I think that's a separate conversation. How can we actually get those metrics in an accurate way? And finally, remind me what your last point was?
The idea of doing shadow.
Yes. Yeah. So what we've done slightly similarly, we implemented a tracing tool to actually collect all of page cache events for specific pages. And then we can kind of, based on that access pattern, really simulate different cache policies on that and kind of post-mortem calculate those different hit rates and performance. Doing that live, I think, is a bit more challenging, like you said, but definitely something that we're interested in doing.
Like, very nice talk, like very impressive. I'm a big supporter, like as the MM person in this room, or one of the MM persons in this room, I'm a big supporter for eBPF when it comes to prototyping, playing with new ideas, and then like using what we learned from these experiments to trying to make the kernel a better place, right? Do you maybe see like a path forward where we could use some of what you learned to make the kernel better even without eBPF? For example, we could also implement like 2 or 3 strategies you have here, like fixed in the kernel, and like make some auto tuning based on that without all of the nice eBPF stuff, and then still have eBPF, for example, for advanced experiments playing with workloads. Like, do you see a path forward with that as well?
Yeah, I think that's possible for sure. So just as a brief history aside, I think when we were looking into this in the first place, we saw a mailing list posting from 2006, where I think someone proposed kind of doing exactly that, having a few different page cache policies in the kernel. And I think Linus responded saying that like no workload actually hits like the page replacement. And this smells like university research to me. So I don't know if we proved him right or we proved him wrong, but yeah, I think there definitely is a kind of path forward to having a few different policies within the kernel. For doing this, I'm sure there are sort of kind of generic policy deficiencies that can be identified based on this and then improved. I think, yeah, the benefit of BPF, the primary benefit of BPF that we see is really this application-informed kind of policies, right? Where applications can really give hints to the kernel in specific ways and really do kind of live updates to the policy. Because yeah, any like fixed policy you could implement in C or Rust or whatever and just throw it in the kernel.
Right to that point, I was wondering, like, do we actually envision like having thousands of different policies here, like you could envision with SCADX, or is it more like 3 or 4 policies that are common, and like having an application-specific thing is actually just selecting one of these, right? Like that you only need like a mechanism to select the policy at a given time for process.
Yeah, I don't know about thousands. I know that, you know, in the literature out there, there are many of different caching policies. I do think that if we get to the point of saying we just want a fixed set of policies within the kernel, there are just going to be more and more kind of people trying to optimize for their specific use case. I do think having this kind of generic-ish interface where, you know, some random company out there can just say, oh, I just can implement this in BPF without having to actually get my specific policy that works well for my specific workload up into the kernel is probably easier for them. I don't know if, you know, that optimization that's specific for them really makes sense to upstream for everyone, because it really might be just focused on that niche workload.
So let me go like give the other perspective, the negative. Let me say. So first thing, like I'm kind of not really liking focusing on the page cache. It doesn't have anything to do with the page cache, but more of a LRU, letting you do the LRU manipulations, right? So and somehow I feel like you're not really touching the anonymous, the heap memory and those things, because it will gonna do the same thing there as well. And one overall, like I think I would like here definitely is where the actual things are, the touch point. I think you added the add and there, and then the thing missing is on the mapped memory, how the accessing of the mapped memory will get and change the LRU, those things. So I think it can be done, but I'm kind of like, why just looking at these smalls that you're looking?
Yeah, so yes, that's a good point. This at the moment is focused on file-backed memory. The reason for that being is we focused initially on kind of database and key value store workloads where they primarily use this file-backed memory. I don't think there's any kind of structural or kind of technical reason not to extend the same thing to anonymous memory or mapped memory. We just haven't got into that yet.
Actually, I want to add like some answer. Right? I think like eventually you'll probably have to live with like there is always some complicated use case where you want like application hints, like I'm going through this phase of my lifetime, right? And then like you do one policy, and then like later on maybe it will be a different phase where like the different policy makes sense within the same application, right? And doing that with BPF it's hard logistically but doable. But doing that like in kernel without BPF is going to be like a nightmare of like API definition. Like thread local variable, for example, I was given talking in the morning, right? Like you can use thread local variable to like very cheaply signal like what sort of phase I'm going through, right? And like with BPF, you can fetch that and like modify your decisions. While like doing that like kernel proper is hard. So I think like it will have to be both, if that makes sense. All right, cool. Thank you very much.
Thank you.
Lots of discussion.
All right, last talk before the lunch.
Go ahead.
Hey. Hey, hello, folks. So yeah, today I would be presenting about like RDMA Tracer. It's an in-house application which we build for us to like understand the failures which we were seeing in the AI jobs due to like the RDMA syscalls, and how we use this tool for like providing observability and monitoring and alerting ecosystem to identify these failures in real time and solve a lot of business use cases with eBPF. So I'm Prankar. I'm a software engineer at Meta. My partners are like Maxim, who is a production engineer. He is doing some awesome cool things in the network infra. And Theo is a professor from like CMU. He actually motivated us to actually submit this talk into LPC and helped us prepare this entire presentation. Okay, so before I go a little bit deep into like our solution or like the challenges and stuff, first I would like to a little bit explain about like the training infrastructure at Meta. So here the few things which I want to highlight is it's like early on while building up like the whole ecosystem of like how do we do the training, we decided to actually separate the front end and the back end networks. The reasons for that was like early on we identified the requirements for like all these non-AI workloads and the AI workloads are like totally independent and mostly generally conflicting. And we had this hinge of like these networks will evolve independently. So we actually started early on in like separating it so that we can build in like some acceleration and like move really fast to like design new routing or the network topology for the backends. So the front ends network are mostly used for like logging, out-of-band exchange, checkpointing, observability, and the backend are mostly used for like the backend next the AI workloads and stuff. Here is a picture of a Grand Teton platform, which is like an AI machine. So just to highlight it over here, the CPUs are connected with the front-end NICs, and we have like the GPUs connected to the backend NICs via the PCI Express switch, providing like ultra low latency and high bandwidth and stuff. So the backend composed of like all the NICs connected in like a non-blocking architecture so that they can provide like low latency, high bandwidth to like all the GPUs irrespective of their physical location. And just to also highlight, like, so let's break up the training process into like 3 parts, basically. The step 1 is mostly like more like of a TCP handshake. We are exchanging like the queue pairs and the Git information. This happens on like the L2 path or through the front end stuff. The step 2, which is the most important thing for this presentation, is about like the control path ecosystem, in which the kernel driver really plays a huge part in like programming the registers programming the CSRs of the NICs, or like allocating the memories or the memory regions, RQs, CQs, SQs, and like I'm mapping it to the user space so that in the step 3, the user space application can actually directly post the cookies into the NIC hardware, entirely bypassing the kernel. Okay, so here's a case study of the impact of like the syscall errors we have been seeing in the meta. But before I go here, one thing also I wanted to explain like the few of the terminologies which I will be using. So assume like whenever you are doing a training model, maybe it's an LLM, a Llama XYZ, or like a general purpose or purpose-built generative hurdle, it can be broken up into like multiple jobs which operates on like a bunch of GPUs, and each job is again broken up into like various tasks which mostly executes on its own host or a particular GPU. So whenever a task actually fails due to like any of the issues, or it generally results in like the job being restarted or actually job abort. And when a job actually aborts, it halts the entire training of the model itself. The reason being, so like we know, I mean, like the jobs has to like synchronize together based on the communicative libraries and stuff. So so if a job actually stops and we have to restart a job, so as part of that, I mean, like we waste a lot of GPU hours as well as energy, because I mean, like the initialization has to be done again, and then we have to do the rendezvous against like all the jobs, how that training model to like, so that they can start at like the last checkpoints. But the checkpointing are also done not very frequently, so it has to do a lot of computation. So here was like few of the stats which we wanted to like share across like all the job failures which we were seeing in the meta scale. The 10 to 20% of these job crashes were due to like RDMA related syscall errors. And if I am to collect the stats from like the last 6 months, out of like the 32K plus GPU hours wasted, 5K plus was from the RDMA subsystem. Like I explained, I mean, like when you are training a flagship model, and if the model actually fails, you have to like involve a lot of on-calls to like get together and like actually figure it out. It involves like people from like the model team, the AI team, as well as the server platform infrastructure, the network infrastructure. All the teams actually work together to like mitigate and like root cause the issue. And when these issues are like really, really hard to triage, it just adds up. Okay, so here's an example of a particular RDMA stack, the control path. So as you can see, we have like so many layers in this, and the failure can happen at like any layer. So for example, the application layer, it can be due to like misconfiguration of like by the application, or it can be at the NIC layer, some hardware bug or head of line blocking or whatever in the NIC layer. Okay, and so since the scope of the RDMA control path is huge, debugging an issue is not really, really trivial and not really, really easy in like limited time. So we wanted to like focus on like the kernel layer and the driver layer to like build up some kind of like observability on like when does a system call actually fails, what things we can extract it like really, really easily and provide it for like the other teams to like build their observability on. So what does an RDMA syscall error actually looks like, right, in production? So think about okay, before I go again, so let me first explain the difference between like the async and the syscall errors. For this talk, I think we can like decouple, we can categorize or bucket all the errors which we have seen into like async as well as the syscall error. Async errors are mostly like due to like asynchronous events happening at like a distributed job level. These are mostly generally related to like system level failures or like the network, the transient network issues, port flaps and stuff, the GID table corruptions, and all these things. So, and we already have, and the easy part with these failures are like most of the information is already present through the logs, the job level logs. So you can build an automated tooling of like scanning the logs from the jobs and like build your understanding of like how to mitigate it or classify this thing. Okay, now we will talking about purely for the syscall errors, for which it is not really easy to understand why the error actually happened without actually going deeper into like the entire call graph or like the stack trace and stuff. So yeah, earlier when we used to like see an error, for example, we just used to like in the logs, the IB modify Q pair actually errored out with like the error code of like eno data. Okay, but what to do with that, right? I mean, like somebody has to like go and like try to reproduce, run the F trace, and like figure out, okay, what was the call stack graph. Earlier, we were not actually doing it on the return value, so it was like really hard. And then we were being like comparing the bad traces versus like the good traces to identify, okay, where is the bifurcation point happening and how to like local identify the issue and like actually figure out what was the actual root cause of the issue. So it required a lot of work. So it resulted in a motivation for us to like build some kind of like a tooling infrastructure or observability tool to process all the Nicker failures in the production and being able to like compare all the traces dynamically and localize the root cause and like quickly fix it up. Okay, so why did we build our RDMA tracer with eBPF, right? Like I explained, Linux is still very crucial for RDMA subsystems, right? It takes care of like all the control and the resource accounting, and it actually processes all the IB verbs ioctls through RDMA core, which is like a shim layer between like the IB and the user space. But it doesn't have any retries. The nickel also doesn't have any retries, right? So if anything fails, it's just blown up to the application, resulting in an immediate communication abort or like application crash and all these things. So yeah, so if any error happens, it blocks the jobs and stuff. And one thing, like if the crash is like sticky to a host, like something like even after retry, the job will keep on actually crashing. So yeah, it was really hard for us to like debug what was happening. With eBPF, like we know, yeah, it provides a lot of various, when we're talking about like the kernel, right? So eBPF provides a lot of trace points for us to like start learning about like the call stack graphs and understand the return values and stuff, and extract all the states for the kernel internal variables and stuff. And also like in Meta, we have already built a lot of expertise in like managing a bunch of eBPF program at huge scale. So why not use that expertise also in this area? And also since it's eBPF, it's portable plug and play without really needing to change the kernel, which we really like. Okay, so now I explained about like, okay, we have a problem, we have a motivation to like solve something, and we have an expertise into like eBPF. Okay, so now when we like head together on to like try to like build a solution, these are like few of the challenges which we faced, and we would like go across it right now. So if you think about like an IB call, right? Example like IB modify a Q pair. If you look at its entire call graph, you will see like 20 to 40 functions internally being called. You can't just put like trace on every function and stuff, irrespective of whether it's an AI job or no. It's computationally expensive, right? So we wanted to like build some kind of like heuristics on like, okay, which functions are really crucial for us to like apply the trace points, and why do we want to like choose only these functions? The first idea which we had was like we wanted to like apply trace points to only those functions which are resulting in like the hardware state modification or change, which we can like totally convert it into like the kernel data structures or like the kernel internal variable state changes and stuff. So like I said, IB modify Q pair such a huge call graph, right? So based on that, we had like few static analysis to like create some rules on like, okay, which calls are like really useful for us. We decided to avoid all the read calls, decided to avoid any internal pure kernel functions, avoid the cleanup and the reference counter functions, and depending on the hardware vendors, focus on the driver system calls only. So after doing all these heuristics and stuff, we were able to identify, okay, out of these like 40 functions, we are mostly interested in these like 8 functions and stuff. Looks good, right? But again, it was done for like only one IB modify Q pair. We have another functions, create CQs, MRs, and all those functions. So we have to like, it was a painful process at the start, but once we got used to it, it got relatively easy for us here. Okay, so now we talked about, okay, so now we have identified, okay, these are the functions which we are interested in on like applying the trace points. Okay, so now what? So eBPF also provides a lot of options, although we all know like what is the recommended eBPF trace, but we still have to like do our own qualification apart from like the kernel benchmarking tools to make sure the recommendation holds, because we would be running it into production, so we have to redo that exercise always. So yeah, so whenever we are talking about like which trace point to use, we talk about like the K-pros versus like F functions. So first we have to like talk about like, okay, what is the probe location? I mean, like, do we want like any line in the life cycle of the function, or are we just interested in like the entry or the exit point? We identified, yeah, mostly we are interested in the exit point, but if the input arguments are also available, we can expose it and it could help us into the future. So it was a decision between like the K-red probes or F-exit. So we went, of course, we know the F-exits are really good because of the trampoline, but still we wanted to like understand and do the benchmarking again with like the kernel benchmarking tool and with the nickel tool, because these could be applied on like the AI systems, and we wanted as much low overhead as much as possible. So the performance comparison, it was the same thing again. So I will quickly go over through it. The kernel benchmarking tool and the nickel benchmarking tool both proved for us to use F-exit, because those were like roughly 72% of the K probes. So here is the solution design which we went through. We have a bunch of F-exit probes applied onto like the various trace point functions. What these BPA programs are like are doing is like they are checking the return value of a function. If it's non-zero, we would just save the context into a BPF ring buffer map. BPF ring buffer map are like 256 KB, which can hold up to like 8K records at a time. And then we have a control plane, which is like polling onto like the ring buffer map, extracting all these like records, which it has identified into the buffer, decodes it, pretty prints it into like the nice data structures, up levels it, stores it into like the storage or like other teams to actually use the information and build the monitoring and alerting tools based on this information which we are providing. Another thing apart from the ring buffer map, which I explained, we also have a per CPU array counter, which is generally used to actually identify further things, like, for example, how many syscalls have we executed as part of this trace? How many of those syscalls have actually failed? How many of those syscalls failed with a particular error and stuff? Because those are also very important metrics we need to like look on, which I will explain in like a later slide later on. So in the bottom, I have like few samples recently taken of like what the data are we exposing. We are exposing the timestamp, the GPU driver, the kernel versions, the syscall failures, error numbers, and other things over here. Again, we have to do some of the performance comparisons because we will be rolling it out into production. Now this time with and without our changes, basically. So we tried to like do some testing in our RC dog food tier. We took a lot of backend hosts, run the nickel tests as well as the AI training models, and like try to like compare the metrics using like the BPF tags. We tried to compare like the difference or the so we try to compare the difference between like when our BPF programs are running, what kind of impact are they having as compared to already existing BPF programs on AI nodes. So we identified like our BPF programs which we are adding at a P50, they are like 88% less taxing onto the host, and on P99 it was like 99%. So it was really fine. And we also checked like few of the metrics like the CPU and memory and the network utilization, all were like really fine before and after the enablement and stuff. And the workflow QPS was not impacted at all, which was the most important metric for any AI system. Okay, so now we talked about like few of the heuristics based approach, and we have identified, okay, this is the eBPF trace points we want to like use. So now we have a way of like collecting the data. Let's talk about like, okay, how do we use this data and when we should actually use it. So always on probes are relatively always expensive. So we need probably a sweet spot between like the proactive and reactive approach of like this data collection. So apart from our RDMA tracer, we also have an auditing systems workflow. What it does, it's like it tries to like get all the stack traces or like the code traces periodically on like various jobs running onto the a fleet. So it gives us a good data set for building our knowledge on like what are the call graphs being used and what error codes we should actually ignore. For example, ideally we would want all our return values to be success. If not, is it a failure which we want to like debug and stuff? So all this information are being learned from the good trace collection ecosystem. So for example, we identified like few of the system calls are actually returning no end for like few of the disabled functionality in the older drivers and stuff. But we don't need to like spend our time actually debugging all these things. So all this information and the learning actually came from our good traces collection and stuff. And once when we have a job failure, although RDMA tracer provides a good understanding of like the call stack of like from where we are getting the errors, but sometimes, as we know, we have built it from heuristics, it may not be accurate all the time. So we still need to like collect traces on like the failed jobs and actually sometimes actually compare against like the good and the bad traces to understand, okay, where is the actual error coming from, and based on that we can amend our RDMA tracer, add more calls and stuff. Another thing which we had in the back of our plan is like, so right now we have like pretty good understanding of like the RDMA call graphs, right? I mean, like, but in future with every company having its own RDMA ecosystem, there will be eventually cases of like the divergence of like the IB call stack will actually change. I mean, like they might amend like few more things into like few of the IB calls and stuff. So we wanted to like build a system which would actually understand from the good traces the RDMA call stack is changing, and it could help us like in developing our initial data set with that good traces again, so that we can be a little bit proactive in this area. So RDMA tracer in production today, I mean, like what we were able to achieve with this was like we were able to significantly reduce a diagnostic time from like the high tens of minutes to like few of the seconds. We were able to like easily catch a lot of issues and classify them accordingly and save a lot of time, either by retrieving, by not having to retrieve and like parse through GBs of logs and stuff, and we were able to like easily correlate an issue with like a proper timestamp so that we can correlate with demessage logs and stuff, and it helped us actually identify a lot of driver bugs in like the vendor logged ecosystem, right? So here's another use case study which I want to like share. So we started actually seeing a lot of our AI jobs started failing on like a newly deployed pandemic driver, and the issue was from the logs, it was like, okay, registration of a DMA buffer for a memory region actually failed with operation not permitted. Okay, then what to do? So we hooked on our RDMA tracer, tried to understand the call stack of like where it is failing, and then once we identified, okay, this function is actually failing, then we had to like do a little bit of manual triaging of like why, and we were able to understand, okay, it's a standard buffer overflow problem. It's expecting a long and you are returning a in, so it was being rejected or like resulting in some errors. We asked the vendors to actually fix it, and they upstreamed a fix, and then we were able to like solve this thing. So basically, the summary over here is like RDMA system error calls are very expensive in terms of like power, GPU hours and stuff, and also in terms of like human resources when we are able to have to like triage it to unblock the business needs. We were able to like identify an area of the section of these like failures to like strictly focus for like the kernel stuff, and we were able to use eBPF to actually solve it, and which helped us actually reduce the time to like triaging and improve the work-life balance of our engineers a little bit better. One thing I wanted to highlight over here are like normally whenever the monitoring tools are built, it's using the it's being built with an idea of like, okay, we know the problem, we have a solution, let's build it. So we could have also gone through and applied like a lot of traces eventually and then figure out which to actually remove. But we took a different approach in which like we first identified which functions are like really, really important for us to like trace and build on top of it or rather than the other way around. So it was a different thing which we did. Yeah, I think that's it from my side. Yeah. Any questions?
Just a note that there is an option for ftrace these days for it to capture return values, and they will show up in your function graph. So you just might be on an older kernel.
Oh yeah, we learned through our experience later.
Great job, first of all. And were there any bugs found? Because I haven't seen any patches on my list. Kernel bugs? Were you able to find any kernel bugs?
Few of the bugs we found were in the vendor log drivers, so they have upstreamed their fixes into their.
Due to the use of this tool?
Yes, I mean like, so we were able to help them identify these issues because they were just releasing us the drivers as it like it's like fully qualified, but we were able to like find these bugs into our.
Which takes me to my next question. Can this be used as a regression tool? Like,
yeah, sure, yeah.
Okay, I'll talk to you after.
Sure.
Share some patches. Any public patches for this or?
Not yet. Yeah.
Okay. I'll talk to you after. Thank you.
Sure.
Are you streaming all of the events from the kernel to user space to the ring buffer, or do you pull it?
Yes, so we have a control plane which is like polling onto the ringer buffer, extracting all the records and like putting it for the user space applications to like build on. One thing we did was like we wanted the ring buffer to be like overridden because we were only interested in like the latest failures in case our control plane actually goes down and is dead. But we want that data plane to be always be running and like being overriding if those records are not exhausted.
You're constantly pulling them.
Oh yeah, yes, we are not constantly at a regular interval, but yeah, 30 seconds is also pretty decent.
Were you aware of RedSnoop? Did you use RedSnoop at any point?
Yes, we did try RedSnoop D, yeah, during like the initial triaging and all this stuff, and built our understanding based on all these awesome eBPF tools.
Yeah, because it feels like a special case RedSnoop for your use case.
Yeah.
Does that mean the
fixes for the vendor drivers, were you then able to reduce like the 10 to 20% of the restarts of the AI jobs because of?
Yeah, so if we are able to identify the issue to be like a vendor driver issue, of course they will fix it. It will result in like the reduction of the failure rates and stuff. But there are like other things also happening, which doesn't actually takes it too much down. But we have like a proper understanding of like, okay, if this is the error code which is returning, it's okay to ignore, not to waste time actually triaging it and stuff. So we build this ecosystem so people can take all these like decisions with like a higher probability of like being right.
Hello. You said here is for the RDM tracer there. So this is only the RDMA layer, like for InfiniBand, Rocky, or any specific?
So internally in the meta, we are only using the IB RDMA layers and stuff.
I see.
But this space is constantly evolving. You never know what comes in like the next half, after 6 months.
How do you set the trace point here? Like you mentioned the FX there, like how many to get?
Yeah, exactly. So,
okay.
Yeah, so we have to like build some logic of like pruning out few of the functions which we don't want to like add the traces on. So it was actually done like based on like all the tooling, the EBP tooling, like the RedNoops D and all those things to like build all those knowledge and information and expertise to narrow it down with like the 40 call stacks to like only 8.
Okay. Also, it's all kind of RDMA layer.
Oh yeah, these are like IB calls. It's a shim layer, right, between the
Thank you.
All right, then let's go have some lunch and come back in 90 minutes. 85. Lunch. Bar. Oh, go without. Optimus nice.
We're going to the meta office. Meta office? Yeah, it's just like a building next to us. Join?
Yeah, I want to go back to take a lap. Actually, test. Doesn't have battery anymore. Hey, could it be that this doesn't have any battery left? Because I don't think it works anymore.
Check. Yes.
Like last few people, it was like very quiet. All right.
Yeah.
All right. Cool. Good. Thank you.
Get a photo of the three of us. When people finished eating.
Oh, really? Okay. I'm not going to do it.
It's photo time. This probably first slide. Three, two, one. 3, 2, 1. Thank you. You don't have a good one out of that. Take out picture. Take out picture. Yeah. Thanks.
4 minutes.
Okay, I hope you guys enjoyed the bento box at lunch. So we will start the afternoon session. Get ready. Let's go. Should I speak to the mic?
Can I walk around with it?
Yeah, sure.
I'll stay in frame. G'day and welcome. I'm Brendan, this is Ben Olsen. We're here to talk about AI flame graphs. And I should make a lot of conference sounds for the people who are outside. The conference has begun. It has begun. Exciting things are being discussed right now. You are missing out if you are standing there. I'm looking at you. You. Okay, hopefully they'll get the message. I'll start by describing what we've built, how it's different to other approaches. In fact, there are 3 talks back-to-back at Plumbers that show 3 different approaches for understanding GPU or AI performance. But Ben still is. That uses hardware sampling and marries it with eBPF, information for context. There is another way of doing analysis of AI workloads and GPU workloads where you're pulling in trace point information, everything from the CPUs. The talk following this one, we'll talk about that for NVIDIA. It's a different approach. And then the third talk is more about this style. The way I put it on the slide was this old Intel technology GT pin, which is still useful, which does instrumentation of the binary program before it's sent to the GPU. And the third talk today, we're going to hear about Eunomia and what they've done in a similar space as well, but for GPU. So in a way, this is like the 3 talks. You're going to hear about this one, Intel AI Profiler, then you'll hear about one of these style eBPF tools, and then finally, actually instrumenting the GPU program, which is exciting. They're all useful. So as a performance analyst, I'll take as many as I can get and use them in different situations. In this slide, I've got a little bit more information on that was the Intel GT pin method. Because when I began work on AI flame graphs, I wanted to profile what's going on the GPU or AI accelerator. This was the state of the art. And so that added the instrumentation to the GPU machine code before it was sent to the GPU. That does inflate the program, and the documentation on GTPin showed it could slow down programs by a substantial amount, something like 2-fold. So that's a little difficult to do in production, but if that's all you've got, then that's what I'd use. The AI profiler that we came up with is modeled more on Linux perf. I just want to be able to run perf record and then capture time samples like I do for the CPU. And so we used a hardware feature on Intel called Intel EU stalls for execution unit stalls, which gives us an instruction pointer. And that's nice because we don't have to run things through an interposer. Oh, this is so slow. There we go. Just to jump to the chase, what does it look like? Here's a AI full stack flame graph. I know at Plumbers and LSFM and BPF, we've seen AI flame graphs before built on the CPU side that shows the CPU stacks that led to issuing a program on the GPU. That's going up to where I've drawn the ioctl here. What we've done, we've put these extra frames at the top in aqua and green. And in aqua, it's showing the GPU program. So we've got file names, there'll be function names. And then in green, it's got the instruction type, the stall reason, and the instruction offset. So you get these extra frames on the flame graph. That's really exciting. Over time, this will get deeper as GPU programs get more complicated. And so we've tried it on all the workloads we can find, And the GPU frames aren't that deep, like maybe 2 frames deep or 3 frames deep, at most 6 frames deep, very different to CPU stack traces that get very deep. And so sometimes when people see the AI plane graphs, they think it's not super useful. And I agree that over time it will become more useful, because I would expect that GPU workloads, just like CPU workloads, there'll be more layers added, there'll be schedulers added, all sorts of things will go onto the GPU, and that those frames will get deeper and deeper, and it'll become more important to see what they're doing, what's going on. How you read them, I've just drawn it backwards. So it's this application uses this GPU, uses the GPU for this reason via this driver. It runs this GPU application from this source file. It runs this function, which runs this instruction, and it's slow for this reason for these exact instructions. So you get the full picture, all the way from the CPU into the GPU. So you've got the full context. I know which CPU coparts are doing it and what actual GPU code is doing it. Now the requirements. So when we started, I just wanted it to be like Linux perf. There are a lot of profilers out there, and Intel makes one called vTune that likes to do interposers. The interposing. So you have to run the application from the profiler. Now, it's not always the case. vTune has a mode of doing it outside of it. But some of the others we looked at had this as well. And so that's something I didn't want. It has to just work. So the first, to list out the requirements, the first is near zero overhead. And I've said FANG's target a less than 0.1% overhead for profiling and monitoring. We can do that because we can do these plane graphs using hardware store samples, so that's effectively free. Easy to deploy. Like I said, you should just be able to run perf record or our version IA prof record, and then it samples it just like with Linux perf. Nowadays, this is becoming exciting. We see there's these startups who are selling eBPF things. They're calling it zero instrumentation. And by that, they mean you're not having to edit your program and insert monitoring calls. You just run it. So I guess by that terminology, Linux perf was always zero instrumentation. So is ftrace. But it's important to highlight. That's what we're calling it these days, zero instrumentation. You just run it and it works. It should be easy to understand. And one of the nice things about flame graphs is they're in the language of the developer. So I did look at a lot of other GPU profiling and monitoring tools, and it's like I needed a PhD in GPU internals to understand this output. Here it's like, well, this is your code, and if it's not your code, it's often some open source code. Intel liked this in particular because Intel had an approach called the Open AI ecosystem. And so in other talks, I was able to put the GitHub URLs for all of Intel's GPU stack and show how the flame graph showed where all the internals are. But developers like it. It's their language. Actual hardware profiling. So this approach was, we had Intel EU stalls, so we wanted to use that. That gives us instruction pointer samples. The difficulty then is you just have a bunch of instruction pointer samples. You need the stack trace and symbols. And then complete. CPU and GPU, I wanted to see them both. And now Ben will dive into how.
So this is how. So that's the dream, is that we have combined CPU and GPU profiling, and we basically get GPU profiling kind of on par. We start to work to get it to be on par with CPUs as well. That's kind of the dream. And so this is kind of the crux of the problem, how. I wanted to show this slide, though, well, okay, yeah, let's talk about how. So basically, this is the information that we have to collect, and this is the information we have to correlate. So you can see here on the left, we've got a stall sample. So we've got some GPU addresses, but only some of the bits of it, which is not ideal. We've got some user space stacks, and then we've also got some ELFs. There's also a feature of the Intel kernel driver where you can get ELFs of the running GPU programs. So this is all very useful, but it's not particularly useful unless you can visualize it somehow or look at what can actually tell you about your program. So you need to correlate all of this information together. You need to get their GPU address, figure out what user space stack led up to the execution of that GPU program that that GPU address is pointing at, and you need to associate it with some sort of else. So you can do disassembly, and you can actually show source code. So this is kind of the crux of the problem. This is kind of how. So now we come to a tale of two methods. We have here on the left the first version, our prototype of using K-probes. I wanted to use K-probes because it's kind of the least common denominator. It's everything that's running on the GPU is going to have to go through the kernel driver. So it makes sense you should probably start there and start probing there. And so we did that. And please don't read all of that. But this is all the junk we have to do to be able to associate those GPU addresses in the stall samples, so where the execution units are getting stalled, with a particular GPU program. And the reason for this is that in many cases, the GPU kernel driver doesn't actually know about, obviously, the individual programs which are getting run on the GPU. And so what can you do? Well, you can write a full GPU batch buffer simulator, essentially, like Brandon did in BPF, and parse every single batch buffer command that's being sent to the GPU, and basically simulate this command streamer, and then ensure that you don't ever page fault. Of course, you can't do that, although new BPF features will mean that we actually can. So that'll be extremely useful. And you do that association. Later, we kind of decided, okay, well, we should probably use uprobes and try to do this a bit simpler. And so you can see here on the left, it's obviously much simpler. You can look at where the GPU, the runtime library, it's called Neo for Intel. You can look at where it's going to write that command to run that GPU program. It's called a compute walker command. And then you can just look at the GPU address that it's about to write to memory. And then you don't have to deal with all this. So, okay. And also in that code, obviously, you can extract from the structures of the runtime the names of the individual GPU kernels. Now, there are caveats. As with everything, this is kind of the dream, is that we have this unified CPU and GPU profiling is very easy to collect and all this. There are lots of caveats, right? First of all, you have to collect all those else. You have to parse them. It's somewhat expensive to do that, but you need it for your GPU source file and to disassemble the instructions, for example, for those stack frames. You have to have that information. Also, the underlying hardware feature called EU stalls, if you want to look it up for Intel hardware, it doesn't include all of the bits of the GPU address necessarily. And so if you're running multiple different contexts, it's difficult to differentiate the two. And so we have to do some workarounds in software to be able to account for that and determine which context the stall went to. And that's very complicated as well. But kind of one of the main problems we've encountered, maybe you can tell us how to solve this much more cleanly, but essentially getting CPU call stacks that led up to the execution of that GPU program, we have to have frame pointers. And so you can see here, I put this slide. If you have a PyTorch workload, this is the simplest possible workload I could come up with that calls PyTorch. You can see there's a lot of things you have to recompile. And you already have to compile, for the Intel graphics stack, you already have to compile 2 versions of LLVM, for example. And so you're gonna spend a lot of time waiting on your computer to recompile the entire world. And so that would be very nice if we could collect CPU call stacks without having to recompile some of these absurdly complicated software stacks. And then also another complication is that it's just very kind of complicated. There's a lot of components, a lot of software components that go into actually running something on the GPU. You're not intended to read all of this. And we made this when we were still on Ponte Vecchio and using the Einerman 5 driver. So it's a little bit out of date. But there's a lot going on here. And this is kind of the reason we didn't want to initially use uprobes. One of the disadvantages of uprobes is you have to specify the absolute path of the library that you want to trace. But another problem, so that's a problem from the usability perspective. But the other problem is that there's a lot of runtimes that could potentially call your kernel driver. And so this kind of demonstrates that a little bit. There's a lot going on here. And so this is then after we came up with these flame graphs for GPU workloads, we said, we can actually go a bit further here, and we can do what Brendan calls flame scopes. And these flame scopes, kind of how you read them, are both axes are actually time. So here on the x-axis here is seconds, and on the y-axis is, I think in this particular case, they're 20 millisecond little time slices, each of these cells. And this is the version of Flamescope that you can run in your browser, but we also have a CLI version that you'll see here in a second. And you can see here, this is me actually running Doom. I forgot to put the Doom screenshot in my slides. That would be cool. But I was running GZ Doom because it's open source. And you can see here, you can click on any subset of these cells, and you can generate a flame graph for that small period of time. And so on the CPU side, obviously there, it's going to be CPU time. On this here, it's actually GPU stalls. And so you can see here, if you generate flame graphs of these individual patterns that you see that immediately stand out to your eyeballs, you can see exactly what the CPU is doing at any given time. And more importantly, you can actually go over to the GPU and generate a flame graph of it as well, or at least the EU stalls. And so that's really the huge advantage of having this hardware feature and having hardware sampling features on the GPU, is you can actually start to come up with these CPU style visualizations that you wouldn't otherwise be able to generate. We also came up with a CLI version. We've decided, okay, it's a little bit annoying maybe to copy it to your machine or to open a port or something like that and use your browser to do the visualizations. And so we decided we can actually do this in the CLI. So here's what we call ProViz. There's going to be a link on one of the later slides if you want to use it. It also supports perf. So you can actually see here, we've got perf cycles, just parses the output of perf script. And you can see here we're using PEBs. And on the CPU side, and you can, they're kind of synced up, so you can click and generate flame graphs of the CPU side, and then separately generate flame graphs of the GPU side. And you can do that same kind of visual correlation between CPU and GPU. It's pretty interesting. And of course, this is just kind of the start. We kind of wanted to build a proof of concept. We wanted to get it all working and get to the very end of the race, and then there's a lot of work to do to make it easy and to make it fast. And then you can see here in ProViz, this is a screenshot of if you were to select one of these intervals or some subset of intervals, then you can see flame graphs in the CLI as well. Here's the current release if you want to give it a try. Running IAProf itself, that's what we call it, the Intel Accelerator Profiler. It's a bit tricky. I've been testing it on the B580, the Intel graphics card on my desktop, and it works pretty well. By default, I think it uses the Kprobe version that you saw on the right side of the slide, but you can also switch it to the uprobe version and hard code the absolute paths of those libraries. I hope we can fix that. But yeah, so you can give it a spin. And then also ProViz also supports per script output, so you can go there to download ProViz if you just want to. You can even just use it to view normal CPU flame graphs as well in your CLI. And that's it.
Yeah, so some final points, and then we'll take questions. Final points. A lot of things had to be instrumented to get that context out, whether it was Kprobes or uprobes from the Intel graphics stack. There are many teams at Intel that work on these layers. We could have gone around to each of the teams and said, here's our requirements. We need this symbol stuff. We need debug stuff. That could have taken months or years to get all of those APIs out. eBPF was essential for doing fast AI analysis and innovative AI performance analysis work. And we'll see this in the follow-on 2 talks as well. So that's one of the greatest points we have is eBPF was great because we were able to do this as a very small team in a very short amount of time instead of waiting years. And with the rise of AI data centers and the costs to the planet, we need to be able to iterate and come up with tools in a hurry. And the other thing to mention is this is all open source, so we did get this all on GitHub so people can play with it. It won't be the only eBPF analysis tool. There's going to be lots. It's just this. It was the first thing I thought I should build because flame graphs we know for CPU land are very useful. You see them in so many. I've seen them in many talks. Andre had one earlier today, and I see them in GitHub tickets all over the place. In the future, we may see that for some GPU workloads as well when they get more complicated, but it's not the only thing. There's going to be lots of tools. We need tools to trace the GPU internals. I don't know, Andre's already helped write some. We need tools to look at latency histograms, workload characterizations, error rates from inside the drivers. There's going to be lots and lots and lots. This is just one tool out of what should be a very large eBPF AI ecosystem. Okay, so thank you, and we will take questions.
Hey, so can the flame graphs take into account asynchronous execution, and can they take into account exposed CPU time? Sorry. So let's say you have a tensor processing on the critical path that blocks the GPU; it doesn't execute anything. Can you show that in the flame graphs, given the asynchronous execution?
So I think so to answer your question, if I look at this GPU 1, these are synced at the same time. So those red stripes where it looks to be about 100 milliseconds are blocking the GPU. So I've got the white, it's the shoe that fits, like that fits here, obviously. So these times when the CPUs are busy, they're blocking the GPU. If I'm a performance engineer and this is my UI, I just click on it, I get a flame graph, I know what the CPU was doing, problem solved. And these are wall clock time. Yeah, the way Flamescope is drawn is wall clock time. So you can match, it's visual. As a performance engineer, I'll write tools that walk around the stack and say, this is blocked on this, and I'm looking at the wake ups, and I know for sure that it's blocked. That can be a lot of work. So here I'm cheating. I'm doing a visual thing because it's so much easier, and I'm just letting my eyes do the correlation.
But can you put in the flame graph some CPU stacks that don't result in a GPU kernel?
So sorry,
So in this flame graph, for example, you want to have some CPU stacks that don't result in executing a GPU kernel. That would have basically some grayed out, not green on top.
Okay, so we can do that. So we did do that and showed it to management. So you could have perf record, do both GPU and CPU and anything else, and then put it as one great big flame graph. This is like all your resources you can. We actually I threw the samples together and did one. So you had CPU stacks, which did not have the aqua and green stuff, and then the GPU stacks, which did have the aqua and green stuff, and you could see them both on one screen. I showed it to people, and they're like, yeah, but why? AI is more important. But I liked it because I could see everything.
I mean, on the CPU, you're latency bound, while on the GPU, you're throughput bound. So you want to see the phases where you're starving the GPU. So that's why it would be useful.
Yes, yeah. I mean, to see phases, Flamescope is particularly useful for phases because you see the time down to a 20 millisecond granularity. And if you're doing something that has phases or steps, you can see the visual pattern and then analyze it.
Thanks.
Thanks. Question over there. It's going to require a big throw.
So Systing actually will give you a little bit more detail on being able to visualize time-based data, and it pulls it all from eBPF as well. So adding the capabilities to that would make it extensible in a way that we would be able to see where things are being blocked in time.
Yes, did you say Systig?
Systing, Systing.
sys-TNG. Okay. Yes, so we can add this capability. I mean, in a way, this was a prototype in that we built it and we expected it to go into Intel vTune and into lots of other products. Same as the CPU flame graphs I created in 2014, there's been over 100 implementations. So they kind of get re-implemented everywhere. But yeah, for sure. Thanks. Check my time.
I have a question for like, for example, in CUDA SIMP model, we have maybe multiple kernels can run on GPU at the same time, where each kernel can have like hundreds and thousands of threads. And your CPU also has multiple threads and multiple cores. So is it possible, have you consider how to like map like GPU thread blocks information to like CPU thread block information or something like that? What's the connection between like if granularity is not a whole kernel and a whole threads?
Okay, if the question is the way we're mapping things, there is a boundary on the flame graph, on the other flame graph, not flame graph. So at that gray line, we instrument when things are sent to the GPU, the exact buffer calls, and then capture the CPU stack at that point, and then record it with a context, and then we're getting the information out of the driver to stitch them together. And so that's how we're able to do the association of the CPU stacks to the GPU stacks just by remembering which stack trace launched the GPU program, and then you associate the samples together, if that answers your question. Yes, there can be a lot of different GPU programs running.
But if you have some other metric that tells you that a particular CPU thread is blocked as a result maybe of the GPU running something, you could do something like what we've done here. It may not necessarily work that you could combine them into the same flame graph because it's probably not the same metric, right? What you're given on the GPU side is EU stalls by time. And you know, how can you correlate that necessarily with a CPU metric? But what you could do is how do you correspond that to an exact CPU metric? I'm not sure if you can, but what you can do is you can correlate them by, you know, the time of collection. So you can just use wall clock time on the flame scope side to just kind of see about which 20 millisecond interval it happened. And then you could, you know, if perf can record whatever metric that is, you can just have that in the perf script output. This tool will parse it, and then you can see them side by side just like this. Instead of cycles, you would do, you know, some other metric of blocking on the CPU. And you could probably see that. It'd probably light up red, which would be nice.
Okay, thank you.
Would you consider this way of visualization to have advantages over a Kineto trace, for example? A GPU trace collected with
So there's a lot of tools that do GPU traces, and they're great. Like as a performance engineer, I want to use all the different tools. This is a little different in that it's a resource-oriented perspective. I'm starting with the resource, I'm starting with the samples of what it's doing, and then I'm determining it. A lot of these other tools, they'll show you that timeline view, Perfetto and others. Yeah, that's great too. In my systems performance book, in like chapter 1, I have a system stack diagram and I've got 2 arrows. And like a lot of the existing tools are going application layer down towards the kernel. But this is different in that we're starting with the device and going up. Because that's also what CPU flame graphs do. I mean, this comes back to why do we even build this? It's because CPU flame graphs are very useful. And CPU flame graphs don't start with the latency that your application has on the CPU at all. It's all about just doing time sampling. And so super useful, so that's why we built it, but it's a different perspective, very different. What should happen with AI flame graphs? Well, they'll probably end up in all of these tools anyway. And this prototype that Ben and I and Brandon built will disappear, maybe, because it will be in other Intel stuff and other tools as well. But I'm not too concerned about that because like with CPU flame graphs, there's like 100 implementations. I counted them, it took me forever. You know, the work lives on and people like it in different languages and they like it in different UIs, and so that's bound to happen.
Thanks.
Okay, that will be the last one.
Not sure if I missed about the overhead. You mentioned like the fund there is 0.1%, and then your AI profiler is high by default.
Yeah.
What's that? What's the number? Do you have some?
Right. So that goes back to the tale of two cities. I didn't go into enough detail there, so I will now. So on the Kprobe side, the overhead is unlimited. It's just infinite. So it's huge. It's ridiculous. And so you can draw some maybe conclusions from the profile generated by this driver thing, and it will be greatly alleviated if we can actually page fault, and some of the implementation details of the patch buffer parser will be fixed and things like this. But the devil's in the details with that in that respect, and so the overhead becomes quite bad. UProbe version is much better.
Yeah, I said 0.1%, but that was when I drew up requirements. That's not what we accomplished. I don't know what we accomplished, but it's more than 0.1%.
The UProbe version, I can't tell if I'm running the profiler or not. If I'm running again a workload on my consumer GPU, right? So take that with about an entire satchel worth of salt. So yeah.
Thank you very much.
Oh, yeah.
Okay, good afternoon, everyone. Okay, just a quick intro. I'm Ishiko Ga, working for Trend Micro. I have to give a personal notice here. I'm not a Linux bomber, much less I'm a CUDA expert. So I will present from a standpoint of security engineer. I'm more working in a detection engineering, so trying to look for patterns and signatures in all possible things. So that's what was driving this small research, or rather naive experiment I'm going to present today. So what was the driver for this, or the initial trigger? The question we got was, can we do any detections for containers running in GPU workloads? And actually, what we've been using previously was Falco from SysDic. Not sure all of you are aware of that open source product. It's something that traces syscalls in Linux, and based on some basic syscalls records, it gives you an opportunity to detect some system situations like writing to sensitive files and similar. So that's, of course, not applicable for anything related to GPU, but the goal was to come at least a little bit close, to find a way that would give us a chance to do at least some detections related to GPU. So question was, can we have something like Falco for GPU workloads? here I stolen a picture from NVIDIA materials that shows how the containers are usually organized when accessing or using NVIDIA devices. So there's something called a CUDA toolkit and CUDA driver. And of course, then you have underlying device. So the idea was to hook into this common point, the CUDA driver that's usually part of the kernel. So that's why all the detections were based on K-probes. The question was how we can identify the proper points, the proper functions to hook into. So if you try to do something like get the available filter functions in debug tracing, you got over, I think it's something close to 3,000 functions that seems to be somehow related to NVIDIA, which is obviously too much for any tracing. So how we can eliminate some of them? That was actually a pretty naive approach here. So the way was just to split that amount of functions into several batches, run several testing containers and observe what functions are quite common and appear in most of the use cases I was testing. So at the end, I came to some like 41 functions that are listed below, and attempted to hook K-probes to those functions. As I mentioned before, I'm not CUDA programmer, so I won't tell you what exactly those functions do. So that was very basic mechanism for recording data or collecting data. It was just a BP trace using K-probes for all those 41 functions, and it was recording basically what's needed. At least it can be probably done in more detailed way, but for this experiment, what I was using was just a timestamp when the function was called and the name of the function, of course. So the resulting file down there is just a command line example, was a record of functions from the NVIDIA driver called by a specific container. What I have probably to mention here, the good thing with the container approach is that there is exclusivity, so only one container can use GPU at a time, so you don't have to deal with some conflicting calls here. So what was the initial proof of concept? There were 4 workloads, 3 of them kind of legitimate: TensorFlow, Llama inference, NVIDIA inference machine, and then as an example of something malicious, it was a container with Xameric conminer. So that's probably something I should have mentioned earlier, but from the cybersecurity perspective, conminer is probably one of the major threats when it comes to container security, because whenever someone gets into your containers, they usually try to monetize it in some way, and one of the easy ways to monetize a breach container is to run some kind of coin miner. The results were interpreted as a NumPy matrix. So we get those 41 functions. So we measured the output for 60 seconds. And the values in the matrix were basically number of specific function calls in 1 second intervals. And it was tested on 2 different GPUs, both in AWS environment. So one was A10, one was V100. And this is, I was promising fingerprints at the beginning. So this is how the fingerprints actually look like. The visualization of the NumPy matrix On the horizontal line, you can see those 60 seconds. And on the vertical lines, vertical axis, there is those 41 functions. So from this, you can see that the top line, the top three are the Llama inference. The first one is on a V100 GPU. The other two are on A10. The line below belongs to CoinMiner. So even from this brief look, you can tell that it doesn't look the same. That there's certain visual difference between whatever is Llama inference and what is the CoinMiner mining. What is more important, those graphs are not the same on the GPUs. It turned out that once you run it on a specific GPU, you get pretty consistent results with the multiple runs of the specific container. But when you switch from V100 to A10, it looks slightly different. So it seems that whoever will want to do kind of fingerprinting like that will probably need to consider what is the hardware platform behind what the GPU it is actually running on. And now the question was, is there a way to compare and decide what's going on the GPU in some other way than just visually checking how does it look like and if it's similar to something else. So I was thinking about some metrics here. The problem here is something I might call dilatation of time. So whenever you get a CPU that is more stressed, the function calls are probably a little bit coming in a longer intervals. It's slower, right? So you try to run your program, and once the CPU is loaded, it will be executed slowly. So you observe the eBPF hits or the K-probes in a longer interval, so it won't look the same. Fortunately, there is a method that helps to compare compares time series that are dilated or shifted. I have to give credits to my son, who was just through his college data science class and who suggested to look at this function. And it really helped. So it's called dynamic time warping, and I won't go into details. It's pretty clever stuff that makes some metrics and tries to find the similarities within two time series. So what the total metric looked like was the DTW was computed for each of those 41 function calls within 60 seconds, and then there was just size of the resulting vector just as a norm. And this is the comparison of the metrics. So using the simple algorithm shown on the previous slide, each of the fingerprint was calculated into a single value, and the values, or actually the comparison between two fingerprints was calculated as a single value, the difference, the distance between two fingerprints. And this is how it looks like. So you can see that, of course, all the runs of Llama stressed or non-stressed, there are in total 6 samples, was pretty close each other. It's the top left green field, so they were something between 5 or 6 and 40 something. If you look at the similarities between NIM, his NVIDIA inference framework, versus Llama, it was quite different. On contrary, TensorFlow, that's this TF, was TensorFlow basic training versus Llama. There are some similarities, though in average, it's something like 30 to 40 points away. What's good sign is that this coin miner, the last set of samples, is pretty far away from all the rest. So it's pretty far away from Llama, like 400, very different from NIM, and very different from TensorFlow. So using this with certain hope, you can tell whether the fingerprint you measured at the very beginning and you set it for, let's say, your TensorFlow application is something different from what's actually running in your cluster. So that should help you to identify other payloads. Especially seems to be very good in detecting the coin mining payloads. They apparently use a different way of working with the GPU device. And this is my last slide, actually. A small caveat is that my employer might have filled a patent application for a device that might be based on this. I'm not sure how far that really went. My thoughts around it was that perhaps a similar approach might be also applied to other drivers for different devices. But I still didn't have enough time to explore that a little bit. So I think that's all from my side. If there are any questions.
Hey, so have you considered using BPF to dive into the CUDA stack and look for matrix multiplications? Because I know crypto mining applications don't typically use matrix multiplication; they use hash functions and stuff. While AI applications that typically run on GPUs are very matrix multiplication intensive. So for that, you can just hook into functions inside the CUDA API and look for those. Do you think that's an option?
I'm not sure I got it completely. Maybe I go closer. Sorry.
Okay. So AI applications, right, that would typically run on the GPU would be running a lot of matrix multiplications. That's what the AI models do. So you can identify when the GPU application uses a matrix multiplication by using BPF to hook into the CUDA API.
Yeah.
And you read the kernel information, thread blocks, and so on. So I'm just suggesting that would be a far more useful signature to determine if there's a malicious actor on the system.
Yeah, fully agree. I said this was kind of a naive experiment just to see whether there are any chances. You're right. There are K-probes. We don't look for any arguments. We don't have K-ret probes to see what's coming back from GPU. So definitely there's way more possibilities to improve it. And of course, with deeper understanding of the functionality, this was pretty much blind experiment, as I shown. So with deeper understanding of the functionality, you can get way better results than this one.
Well, I have two questions. Actually, I've done similar things before. The first is like, have you enabled UVM oversubscribe?
I think I'm closer.
Oh, sorry.
I'm sorry, I don't hear well.
Have you enabled the UVM oversubscription when you are testing a work loss?
Oversubscription?
Yes, because I show you list a lot of functions there in UVM driver.
Okay.
NVIDIA has like 5 drivers, right?
Yep. So no, this was tested just with this basic setup, because in the default setup, usually you can run just one container with the GPU. So you, if you mean this by oversubscription, you with this basic container setup, you won't be able to attach more containers to a single GPU.
Well, I mean, you can like put some memories on CPU.
Okay.
So it's like you can over subtraction that your kernel has more memory than GPU memory.
Okay. Yeah, I think that might be possible as well.
Okay, because a lot of UVM functions only called when UVM subscription is enabled.
Okay.
Another thing is like, have you looked at other kernel modules like NVIDIA.ko? Because when I look at them, it seems a lot of functions not traceable.
Yeah.
I'm not sure why.
So those, you mean why I use those 40 functions, or?
Yeah, and because a lot of other functions is not like.
As I said, was quite primitive way, just running the kprobes of all the available symbols and choosing those that appear in all the tested applications, and those are just those.
Okay, yeah, I've seen that before. Maybe you can also try like recompare or some other approaches to get simple from other kernels, so you can trace more functions. There's like, you can only trace like 10% of functions or for all UVM functions. Yeah.
Okay, thank you. Wait, I go closer again.
That's okay, I'll speak loud as well. So one problem I see with your approach is, just to follow on what you were saying there, so none of the functions you are looking at there are actually watching work submission to the GPU. Like
fully agree.
You're only seeing like memory management, because all of the work submission is done from user space straight to the hardware. There's no kernel involvement in that. So there's no way for you to intercept that in the kernel. You would need to figure out how to trap inside the CUDA runtime somewhere, or get a probe into somewhere in user space to see that. But when NVIDIA is into the steady state, once you set your application and all your memory is set up, you're just hitting a register saying from user space, going execute. That would be a profile you would see.
Is it valid also for container environment?
Yes, it just maps a page called,
it goes straight.
UserD. If you look in the NVIDIA code, it's called UserD page, and it's a page that gets mapped into the process of into the CUDA runtime, and that's got the register that it hits to execute the context. And if you get that, you would get a very good profile of work submission, which would be a lot more probably application specific than memory management structure.
Yep. Thank you.
Any more questions? Okay, thank you. The next.
Hello, everyone. Good afternoon. And my name is Yu Xianzhen, and I'm also talking about extending like eBPF to. Here we have both GPU device and GPU driver. So what we are doing is not only for observability, but we also want to target some like resource management, maybe some like memory or some kind of scheduling. We have jobs for this kind of tasks. And we also have like a device-side eBPF runtime, which is we built on top of BPF time or previous to work. We are trying to offload eBPF to GPU, which is mainly for profiling. It has a bunch of observability tools, and it can insert props like dynamic binary instrumentation. And maybe it can also work for like prefetch and schedule. And we also talk about how we're going to build these runtimes and the background problems, and like why we want to build this kind of two things. The first is the background of GPU stacks. We've seen there's multiple user space applications, and each application might have it's in NVIDIA stack. Each application might have a user space runtime in them as library. Then we will have a kernel driver, which we have like memory management, maybe UVM, and like channels for and like TSG for scheduling. Then on device, we have maybe a firmware and a bunch of hardware features like hardware schedulers, and we have user kernels running on them. So the kernel driver is like an operating system component of GPUs. You can do like memory and schedule some kind of things. Although a lot of them are bypassed, but so we also do a bunch of like tracing for work loss. We want to say there's the work loss is very diverse. They have different results and behaviors. They have different requirements. For example, the first two phase is a vector database. Then we have LLM decoding and LLM prefill, which some of them are like random access, some of them are like straight-based access or sparse access. And we have like PyTorch training. So these graphs are traced via page 4 in the UVM driver. So they need to be like when you have over subscription, you can easily trace the memory access patterns of page 4 patterns of them and draw these figures. Why I want to say there's oversubscription, because here, today we are facing a large memory placement and offloading problems because the GPU memory is very expensive and limited. A lot of models today, like MOE models, and when you do inference, you also need KV cache for transformers. This will exceed the GPU memory. So you want to oversubscription and put a lot of memory into onto CPU and migrate them or like prefetch them between GPU and CPU. There's also some cases in vector database or training when the access is like sparse and database is big, datasets big, you need to put them on CPU memory, or even like file memory like RDMA. So when you do multi-tenant scheduling, because NVIDIA CUDA runtime don't give you API to do like cross-process scheduler, but sometimes you might have different kind of tasks, have different requirements running on the same machine. Some is like LLM inference in latency, some of them like training in throughput. They also have like complete memory and compute interference. However, it's the same problem as the cache 10 in the morning, but it's like more because the user-based runtime is typically closed sourced for NVIDIA, and GPU driver is the only thing open source here, but it still has a lot of one-size-fits-all policies. Means the policy they have like the memory is like LRU evasion and tree-based prefetcher. The scheduling is simple like round robin and FIFO. The memory LRU is very, very slow. So it's also a black box policy. So people typically, this policy is very bad. So make people want to do kernel bypassing. So they manage their memory and transfer overlap memory placement in their frameworks. It's similar to DPDK. And because the kernel is like one size fits all, and we want to do extensibility to adapt to different kinds of workloads to meet different requirements. Typically, people do use-based schemes like some LD preload approaches, or maybe BPF time approaches, or people can do some like embed some, doing some logic into GPU driver because it's recently open sourced. So we have existing approaches. Some of them like doing this extensibility in user space runtime, like VRM, SGLang, all the inference frameworks manage their own memory and scheduling. So, but this management is specified for each application. You cannot reuse the policy across applications. You cannot like have global control across multi-tenants. You also cannot access like low-level driver mechanisms like replayable page force or like scheduling TSG configuration or firmware configuration. We also sometimes have some device profilers like BPF10, eGPU before, and MVBit and Neutrino and Kubernetes, but they are designed for read-only tasks. And some people have already begun to do like driver modification to meet their requirements, but it's hard code into a driver. It has a lot of safety and deployment risk. Host EBP, you can also use like eBPF to do that, but it's limited for tracing, right? It's not for policies. And also the GPU device, which have complex behavior, still remain a black box. So our insight here is like GPU resource management policies need to have an extensible OS interface like eBPF. We think the driver is the right place because it has global visibility and control. Although a lot of things are bypass them, they still have this very critical control. And it has privileged access to a lot of hardware mechanism. It's transparent, so typically doesn't need to modify the application, or because UVM is nearly transparent, you only need to modify one line of them, or yeah. But host eBPF is not enough. The driver side has a lot of complex logic. You need to have observability into them. And also, you cannot have some logic enforcement inside the GPU kernel. So here, we also do extend eBPF to GPU device context. So we have like, one thing is like do policies for UVM memory management in driver, for like moving data from CPU to GPU, GPU to CPU, and doing some scheduling control. It's not a complete new schedule. It's like some control with time slice group. It's implemented with StraOps. Another thing is like device eBPF. So we can run eBPF on GPU device with our BPF time to realize this vision. We compare eBPF to PKS, and we do a bunch of binary instrumentation. We have device side hooks and helpers compile and run on GPU. And it's also necessary to connect them to, because some policies require both of them, or sometimes you need to like some hooks into driver runtime, some hooks into GPU. So you need to have cross-layer eBPF maps. So the first part is like you want to extend driver policies. So I will introduce some basic concepts here. For example, the GPU scheduler is has multiple abstractions. Some of them is like channels where user space CUDA runtime send commands to GPU driver, and then they have like schedule units groups and time slice group inside the GPU, and they have hardware since they have hardware since like run list for the GPU side firmware. Web we can only schedule TSP because the CUDA runtime is largely kernel bypass. The kernel launch doesn't require driver invocation, so user space write some ring doorbell and push the buffers, and driver cannot see. Driver can only see the TSP life cycle, which you create like hardware queue and bind it to the run list and destroy it. But we still have some parameters we can control, like time slice and interleaf levels, so we can do priority scheduling here. And the memory is like the major benefits. We can leverage the unified virtual memory, which we can transparently move memory between CPU and GPU. And they have shared VA blocks, which is 2 megabytes, and they have less virtual memory. And they have trunks, which is physical memory. They have replayable ports, which is similar to, which is something like page fault. So when doing page fault, So when doing page fault, the driver will first start to like try to allocate some memory on GPU, And if there's no enough space, you will need to migrate some memory from GPU to CPU. And then you also need to do prefetch here. Prefetch is very important because you cannot only rely on page 4. Page 4 is very, very slow. And so the list is managed like a cache. So they have a life cycle of binding VA blocks, which is virtual address, and with the chunks. So we can do one challenge here is like driver was not designed to expose a programmable interface. So we need to carefully consider how can we expose low-level mechanisms while keep it safe. So we only design a narrow, safe interface, which is very similar to cache extend people describe all the morning. It's just like cache idea. We treat the GPU as GPU memory as cache, and the CPU memory as something behind cache. So we have like activate and assess and prepare, which the default algorithm is LRU. So we can build like LRFU, MRU, FFIFO, and based on these 3 interface. And policies can only reorder evasion list. We also have the double linked list evasion list here, but policy can only reorder them. They cannot remove any item from the list. So kernel will always pick the first item in the list and evict them. And kernel will automatically add the chunks into the list. So and call our callbacks in the shops when a prefetch. So we can set a bunch of regions to at each page 4. So we can decide what kind of page I can continue to fetch as our next step. So we can like implement some like sequential stripe-based prefetch, and because we can get more information with k-props, we can have per process memory priority, and we can have application specific contents put into maps to control and access by these hooks to enable control. The default algorithm doesn't consider anything about application specific or priority or process. And for scheduling, we do it at like bind the TSG, and policy can set like some time slice and interleave levels, and you can accept or reject some test binds. So we cannot change the algorithm role. So, but we can still have like priority and latency, critical or bandwidth, or some like bad and bandwidth differentiation by process names or PID, so we can achieve some of multi-tandem fairness things. There was a research paper discussed that, but they didn't use eBPF. So our proof of concept was doing on the NVIDIA Open GPU model, and it has like only 100 lines of instrumentation, because a lot of information we get is through k-props. We are not doing like direct instrumentation. For example, the PID or like virtual address space. And so the instrumentation is in the page 4 handlers and like prefetch hooks and the lifecycle management and like bind. When the virtual address is bind and unbind from the GPU physical address. We also have like 1,000 lines of driver independence codes, which is interact with Linux eBPF to register the stops. It can be extracted as a standalone kernel module. We typically just put it inside a driver, and it can be optimized. And so it's very interesting that we get a lot of speed up on these test cases, even if we don't compare to UVM, we compare to the framework level of loading. UVM is much worse than the framework level offloading. So we can get like 4 times decoding speed up and like 1.5 speed up on VRM, and which is very close to the state of KB cache offloading LM cache. So it's our where we can achieve speed up, I think is like 2 reasons. One thing is hardware become much faster, especially PCIe bandwidth is much faster compared to a few years ago maybe. But software algorithms still also software algorithm become the bottleneck. We can use more algorithms, save prefetch, and typically can get better results. And sometimes key-based prefetch that's not optimal for ML workloads, so maybe you can use like string-based approaches or sequential approaches get better. And for multi-process, in compute-bound applications, we can use like TSP scheduling to control them. For memory-bound applications, we can use like what we say is prefetch and evasion to control them, so we can still get a lot of benefits. I've also testing on like GN, which is Griffith network, neutral network, and vector database. We can also get speed up. And the second part is device-side eBPF. So to remind you why we need this one, because we want to have fine-grained control and observability into the device, because a lot of things remain black box when you are doing host side policies, and you also want to use the device side information to improve your host side policies, or you maybe just want to do profiling. So the GPU execution model is a SIMT model, which means same instructions execute on multiple thread parallel, and they are organized into wraps, and same wraps threads execute the same instructions at the same time, and sometimes different benches will cause divergence, which means slow down a lot of slowdown. And it's all the scheduling is also very different on GPU. You cannot before Blackwell, you cannot have control onto the schedule, but on Blackwell, you can have cluster launch control schedule, which we'll discuss later. And the schedule unit is a bunch of threads instead of single threads. And the memory is also complex. It has like L1, L2, and HBM, and the CPU memory. So each thread has different thread memory access patterns will cause very different performance behaviors. So for example, what we can do by offloading eBPF to GPU is that, for example, we can get which GPU thread is get scheduled on which SM. SM is like a CPU core with stream processor, which can process some GPU threads. So we can see it's very low imbalance. So we can get instruction level observability, we can get per thread metric like that, and we can get memory access patterns by doing binary instrumentation. Sometimes we can also like have runtime adaptations to which is some prefetch hooks and work styles API. And this kind of information can also help host side policies to do the decision. For example, this is a bunch of attached types and maps we are currently support with the cluster launch control API. We've demonstrated some of the GPU side schedulers, which we can control at least some behaviors of GPU threads. But it's only a demo. So, and we also can put some maps into GPU and put a lot of helpers onto GPU And you can also access other helpers on CPU, but access helpers and maps on CPU is very slow because you need to access them with PCIe or other things. You need to have synchronization. So built on BPF time, we do a new CUDA injection mode and offloading the eBPF bytecode into GPU. So BPF time is like a collection of comparers. Here we use it mainly as a comparers because we didn't execute things on CPU, on user space. So when a CUDA application is starting, and it can contain some fat bin, which is a binary representation, and we can get the PKS from the fat bins. And we also, at the same time, we also compare our eBPF programs with our LLVM comparer. We compare them to PKS and put them, merge them together to do the injection, and we run the kernels on GPU device and get the information. It's like that. So it's like manually insert some trampolines here. We first decompile the PTS instruction into text, and so we can easily use some paths or some regs to do the implementation, although it's not very stable, but it can still work. So for example, we can also let the host side kernel eBPF program working together with device side eBPF program to capture some fine-grained behaviors, like when a GPU thread is getting scheduled inside one kernel, so it's more fine-grained at kubectl, because kubectl only see some timestamps with kernel start and kernel end, but we can see the per thread blocks. And one kernel has hundreds and thousands of threads, maybe. So we can have GPU side props. Maybe we can translate with a better name. I'm going to translate with jobs. And we have CPU side U props hooked into a runtime to do the recording, and we can analyze the data together. We also need to do some optimization to make it faster, because if we are just naively put the eBPF instruction into the GPU, it will become very, very slow. So the first thing is sometimes we don't need to have per thread eBPF programs. We only want eBPF program to run once per WAP or once per thread blocks. So we can choose a WAP leader to do the execution and broadcast the results or just update the maps. It can reduce a lot of overhead. And it's not only due to the execution, it's also due to memory pressure, because memory bandwidth is very important on your GPU. And it's also important where we place our maps. If we place it on CPU, you will have PCIe latency and synchronized issues. So it will become 1,000 times slower in our previous version. So here we are trying to get a maps logically verified once and try to do the placement at runtime based on what kind of things is going to, is it configuration or some host states? And this is some numbers with some small tools. You can get much faster than NVBig because of the optimization and map placement. And also because of our tool is working on the PTS level and the NVB is working on the SASS level. NVIDIA has much better optimization on the PTS level. So for the driver side, people might ask why we were not going to expand HS or DIM. That's because NVIDIA CUDA computing seems is completely bypassing them. And HMM is maybe like an interface and more aspect, but it seems like all mechanism is still inside a driver. So our design is more portable. AIM also has similar features and abstractions, and we also prove concept of making it run on SPIRV, but still need to do a lot of engineering work to make it work on other device. And we don't have C group support yet. Maybe we can have some later. I'm not sure if people are going to make standard IPF or GPU drivers for their eBPF extensible because it's vendor-specific things. Driver is not maintained by the community. Any questions?
This injection, so the BPF on GPU side, right? Like you're saying, you're injecting some PTX code or whatever. What are the limitations? Like at which point you can inject? Like if the application already started and it's using GPU, like it's launching CUDA kernels, can you attach your like BPF program after the process start, or the process has to be started like with some special settings?
We have some people or original proof of concept is like you need to do LD preload before application starting. Some people also prototype, so it can be like use ptrace to inject the binary implementation library at runtime, but it still need to do the binary rewriting before a GPU kernel is launched on the device. So the application can be running. It doesn't need to restart, but you cannot inject to a running GPU kernel. Even if you can do it, you need a lot of like record and replay. You will have much more cost and make it hard to maintain.
I'm not sure I followed. So like you're saying you can inject after the process starts, but it has to, no, you cannot?
I can inject when the process is start, but this framework cannot inject when the GPU kernel is starting running on the device. Because, for example, you have some persistent kernels, or maybe your kernel takes a lot of time.
Okay, so in practice, how does this work? Like you specify something before you start the GPU using process? Like what's the workflow here? Like it's not clear from the slides like how you actually inject the BPF onto GPU.
So the process is very similar to the original BPF time process, and you can also do the same thing as original BPF time did. You need to run the libBPF programs with LD preload and get some information to store it on the shared memory, or you can use the kernel verifier as well. And when a process is started, it can read from the shared memory and get a compiled eBPF PKX and do the injection at runtime, or like this BPF time agents can be injected at runtime. So yeah, but you still need to inject a library to the target process.
Okay, so but it basically does similar stuff to NVBit, is it right?
Yes,
okay.
Exactly. It's just we work at different assembly level.
I kind of interested, like when you inject the information there, like it's good to the process. How do you like maintain cross different process there, like a per process application A running? Like in the CPU side, we know which process is application A and which process is application B, right?
Yeah.
So how do you do the things in the GPU side, inside? Like that, is it the same, or do they also have the same information from the eBPF code there, or?
Yutong, do you have answer for that? one approach is like we get the information with our U props and store the information in a BPF map so the GPU kernel can access that. Yeah, another approach is you can call some like CPUs. You can still call CPU code from your GPU kernel, but it's very expensive.
That would be super slow, right?
Yeah, but so I'm still like besides these two operations, I'm still trying to figure out is there any better practice, or maybe you can inject some like metadata when you are doing binary writing. So yeah, I think it's not a technical challenge.
So one of the problems that we have with GPU workflows is that we cannot attach to a running very large-scale training workflow and do profiling, proper profiling of a kernel. Let's say you want to compute warp divergence, band conflicts, and so on. So with eBPF and Eunomia, would you be able to replay a kernel and collect multiple groups of profiling events?
Could you say again a little slower?
Oh, okay, sorry. So basically, let's say I want to profile a kernel, right? I want to collect a bunch of metrics that describe how the kernel is using the internal resources of the GPU. Warp divergence, bank conflicts, shared memory accesses, and so on.
Yeah.
This requires multiple event groups to be collected. And currently inside compute, just replace the kernel a couple of times to be able to collect these event groups. Would you be able to support this scenario? Because if you do, then we could actually attach to a running process and profile a production kernel instead of having to restart the job and create a simple application and so on. It would be amazing.
Yeah, we are planning to support attached to the running process. Some of them are making a proof of concept. We are sure it can work. Yeah, but yeah. I'm not sure if you are saying like inject to a running kernel because kernel typically, GPU kernel typically is not very long. Yeah, it only has, maybe you mean persistent kernel?
Yeah, but the idea would be to be able to replay the kernel. And every time we replay it, you collect a set of event groups.
Yeah.
So that at the end of all the replays, you have a comprehensive image of how that kernel is executing.
Yeah.
So would that be possible?
I think so. Maybe we can try to make a proof of concept. Thank you.
Yeah, I'm definitely rooting for you guys on this one. Thank you.
Yeah.
Last call. Okay, thank you.
Thank you.
We'll have a little more than 30 minute breaks. We'll see you at 5. Yeah.
Yes, I was asking you yeah, I think it multiplies. Well, I mean, sorry, you know this slice which cause certain details so you have to yeah, how are you going to That's right. That's why. How many does have So a couple of things. I was talking to the feature about a little bit. So first of all, inside you can look at your. So there's some sort of hardware standard that you know that I didn't show on the show hardware. I don't know how to do it. So that's essentially what I'm doing. Yeah, that's like the B2. Yeah, that's like and so anyway, I sent an email that like future bookies. That's what we're yeah, I know. I only expected you right now. Yeah, but here I have like just hardware enablement, like all this information is coming from NVIDIA's library. It's all closed source. Stuff I did was you know, obviously, and there's already stuff. So you were saying we want more. So basically, and so, obviously here we can do flame scopes and we can do that by but in the construct you can if you does it give you exactly it's a visual hack. Yeah, so it's like that's why if you have something like it's actually the visual hack's really good. Then you tend to you actually could Artificially, GPU side. That's the way. Or like the cloud, you show the front stuff on two separate, basically. Two separate two separate timelines. Yeah, it doesn't. But the next kernel might be shit. And it's not designed. No, what I suggest basically is paper is text like that. Yeah, no, he just presented super useful yes, Andre's version of existing. No, internally, no, he's gonna post it next week. So, no, this is great. Just so otherwise you can post it.
Stuff, really?
Yeah.
It's not like you're not a no response. What were they trying to do with that?
So what do you like to do?
The data site person would really need you.
Of course, but
It's not really a team that's going and let's say it's more mindless. But doing
Oh, yeah.
I like it. It's just great. My favorite parts of why the heart is very, very far away.
So all we're allowed to do is inside is enable some hardware sampling feature, right? So that we get those samples of the buffer and all the GPU addresses installed. And the CPU side, we have to just be, so we can't touch the GPU portion at all. We have to leave it unmodified. And so, yeah, even though we have the source code, which will make that easier, even though we have the source code for the runtime and the compiler and the GPU driver and all that stuff, but yeah, you're right, we did the exact same. And so, yeah, that's why we can use the new roads, so we can cheat and just, bypass all that. But like she was saying, she had a graph which is where you had the first execution of the GPU. And then the GPU just, the command string or whatever you call it, just, cycles over that workload. And the kernel driver doesn't do anything. And so, and so it's kind of a similar problem. Running.
Yeah, I think you can get connection.
You can do it through shell. You can inject code just to leave it out, or you can try to stitch it together later. For production, we're so limited in terms of what you can get away with, right? And so, right. Since we get the networks and the structures of install, we can push yeah, the time that we know. Yeah, within a time window is the main thing, and so because you don't get the full from the hardware sampling, like I said, we're limited by the hardware sampling because if we do anything else, then we've overcome that the overhead threshold, and so the hardware sampling feature in each of the samples. It's only like 24 bits. The full GPU address is like, depending on your hardware, 36 or 48 bits, right? And where the upper bits are like a context ID. So basically the GPU, basically like the process ID for GPUs, right? So the context ID is the upper bits. We don't count. And so we can only tell within a subset if there are multiple context codes all running at the same time. And if they share the same lower 24 bits of GPU addresses, which happens sometimes and could happen, then within a given, and if they share those 24 bits of GPU addresses within a 20 millisecond time slice or whatever, then we can tell because. So then we just have to give up. We have to give up and we have to say, well, those stalls. Yeah. Right. Right. It's so heavily paralyzed. You can't do that. You're very limited.
Some of them
yeah, right. Maybe. Well, it's just now thought. So actually, in the hardware feature, I slide a little bit. You get the 24 bits of GPU address, and you get the stall reason, and you get a count. The count of the installs that happen. But you also get a subslice length. And, I think we don't have very many subslices on the consumer card, so I kind of abandoned that area of research. But we could probably, if we can parse the command that's executing the program, we can probably tell what subslices it's meant to run on. Maybe if it's more. Yeah. Okay. Yeah. And they're probably not specifying the subslices they're going to run the program. Yeah. Okay. Maybe that would. I don't think you can. I don't think it's possible without the hardware sampling feature just being fixed and just giving you all the 36 bits.
We don't get that from the hardware. No, we have, basically what we rely on now is the fact that address space, probably different. And so the address like the kernels, so you can get the same kernel, that has different. We know that the kernel JPX,
Yeah.
that's one way to do it.
And we found it's extremely low dynamic. It's extremely uncommon within a given system. It's like, you know, we always measure like the percent catch, the percent of stalls that we're successfully catch what we call a collision. And it's, you know, it's always 99.9 something percent in our yeah. Yeah. Yeah, you could, yeah. You could get the runtime to do it because the run, it's weird. The user space runtime, at least for Intel, they implement basically a memory manager, you know, just like it's user space runtime, and so we could just make sure not have collisions ever, unless you're running out of memory, and then you have to have collisions within a given time slice. I mean, that would almost be so. Because the vast majority of memory that you're putting in there is not the GPU code itself, which is where the stall goes. The vast majority of the memory is going to be a big buffer objects that you're allocating that weights in whatever you actually working on. So it's low likelihood, but we could. I think the ideal solution would either be to keep the hardware features so that it includes all these, so it includes the context, or you can just tell the user space runtime that it needs to minimize costs so that it's lower 36 lower performance as much as possible. It would help. That would help. A time series would help too, because then you have a common metric correlated with this, which we can't. Okay. That's in addition to all the other random hacks that we have to do. So, you know, maybe we should fix that first.
Of course.
Yeah, it should be useful. Yeah. It was a nice project to work on. I learned a lot. I thought it wouldn't, yeah, I thought we were going to build like a concept that just basically, like we're just going to have to hack it together. We're going to have to like dump everything in text files, and then we're going to write a hacky Perl script that eventually produces some sort of autograph looking thing, but it's not actually real. You know what I mean? But actually, thank you. But it actually ended up being a real, like it actually works, right? It only took us forever. Thank you. It's a long process.
You could come here. So.
Oh, it's capital Y, I suppose, the last one.
You're the next talk, right?
Video UI is not supported. So.
Oh, it's youtube.be. Yeah, like the short internet.
Maybe it's not supported. I'm not sure.
Like we tried it out.
Oh, okay.
Oh yeah, this one.
So you can pause and go. Pause.
It's visible.
Okay. Yeah. So then you can switch back to the default. It is this one. Oh, we need to stop sharing video. And go back.
All right. So
you need to
will
share.
it be there? Oh.
So
let's just keep it open in another.
Yeah. That's.
youtube.be.
Okay, you figure out. You know how.
Yeah, I'll do
copy
that.
paste there. Okay.
Sure.
Okay.
Yes, thank you. I mean, really sorry for this confusion.
Yeah, I got it.
Yep, that seems. That should be enough.
Maybe you need your presentation, right?
Yeah.
Yeah.
Should I keep it open? Our
No,
presentation?
I think you started when you did it. So up to you. So you want to do it at the end, right?
Yeah, the videos at the end, like in the
Right.
middle somehow.
Right. So I think
Yeah, we'll just open the slides.
that's your slide,
Yes,
right? So open your slide. Yeah. So when you're this one, right?
You share an external video and just
Yeah,
copy it out.
yeah. When you're ready, just use that. Yes.
Thank you.
Yeah, so. It makes some gimmicks. So I. Yeah, and then we have That's when if you have yeah, so I think this is why is it? How do you choose to have the we have, yes, yeah, I think that's it. We have. I think the issue So if you have some sort of exclude it, but then yeah, so I hope that's there was something wrong. Yeah. Okay, so let me just at least like make sure that this would it make sense to I was looking for that actually. Okay, yeah, so.
You guys have it? You guys have it?
Yeah.
Okay.
Okay, let's get started so that we won't get into your dinner plan later tonight. I should speak into the mic.
Hi, I am Pragyansh, and I'm from Canonical, and he's Varun, and engineering undergrad, and we are presenting Python BPF, a way to write eBPF programs in pure Python. This is a side project we have been working on for a little less than 3 months. And a quick disclaimer, if you feel we stated something wrong about an external project, please feel free to correct us. And we'll keep this talk a bit high level so that you are not too bored by the end. And you can ask us about any implementation details during the questioning. So we started with this problem statement of what are the popular ways to write eBPF programs. There's C and Rust with the IR project. Then you can use Python and Lua with BCC, and domain-specific language BPF trace, which is right now built on top of BCC and libbpf. If we focus on the quick and easy ways to write eBPF programs, earlier it was BCC. Most of the examples in the Learning eBPF book are using it, but the problem with BCC is that the eBPF part is not Python, and that means mingling the eBPF logic and user space logic in the same file creates a Frankenstein code. BPF trace is a high-level DSL similar to dtrace but for Linux, and it has its own problems with extensibility as it only supported text and JSON output and had like very old ASCII histograms. It's good for quick results with one-liners, but not the most savvy use of eBPF, because the whole premise of eBPF is extending the kernel, and BPF trace is far too restrictive in that, but they are extending it now. So, yep. This highlights the problem, the byte hist example from BCC, which was enough to fit in this slide. You need to rewrite the eBPF part in C, and I believe if the code is small enough, like less than 150 lines, why would someone bother to write it in Python at all? They would just write it in C. This is not ideal in terms of dev tooling, user experience, and it kind of violates the Python language guidelines as well. So we are building Python BPF to solve these problems by allowing users to write eBPF logic and user space code in pure Python using a reduced Python grammar for the eBPF chunks. This allows for a better dev experience, quick and easy prototyping, and all the extensibility of Python and its modules. I hope this is legible to everyone. This is the hello perf output example of BCC. Left side is in BCC and right side is the same thing ported in Python BPF. And yep, this is the current structure of a basic Python BPF program. The @bpf decorator is used to mark a function or a class as a BPF chunk. And within these chunks, we can further decorate if a chunk is a map or a user-defined type like a struct, or is a function that needs to be attached to a hook. And we can write the corresponding user space code is as close to the BCC user space code as we could get. And so now Varun will explain how it works under the hood.
So I'll be talking about how we wrote Python BPF and how it works under the hood. As a one-time step, right here, we generate vmlinux.py for that particular kernel using a helper script that we wrote. We use clang2py underneath with some tweaks. We wrote some regex to replace some things, and that's how we do the compilation. The structs and enums needed from vmlinux can now be imported into a Python BPF program. The compilation process first collects the chunks decorated with the @bpf decorator. First, it generates the debug info in the IR for any vmlinux structs being used in the code. Then user-defined structs are processed, followed by any maps declared, and they are stored in their respective symbol tables. Then the functions are processed in two passes, first for memory allocations, and the next for populating the logic in LLVMIR. This is then compiled with LLC into an eBPF object file, which is then loaded and attached with pylibbpf, which is our Python library for libbpf bindings. So this is our development workflow for Python BPF, like how we construct our grammar and stuff. We take a program in BCC and we look at some new features that we want in Python BPF to port into it. We write an equivalent C program and generate its IR. We then isolate the IR required for that particular feature along with its debug information and cross-check it with other similar examples so we can generalize it a bit. We then think of the best Python syntax that can be used to represent this, and then write the logic required to generate that IR along with the debug info. It's time for some demos now. Okay, so you can see that this is a container monitor that's written in Python BPF that can find and monitor C groups and graph their statistics, like the number of syscalls, their network throughput, and their file IO throughput. This is pretty clean code, as you see. I'll just show the code right now. Written with pure Python with structs, maps, and multiple eBPF programs. Let me just forward it to where you can see the code a bit. Okay, you can see the different user-defined structs as Python classes and maps used to keep track of data here. There's also some simple logic implemented for multiple trace points, as you can see here. And this is the user space code needed to load programs and access maps. There is a Docker container that I'll be running on the side, where I'll be running some commands and showing their statistics on the TUI on the side. Let me just run ls multiple times. You can see the file IO statistics changing right there in the TUI. Similarly, if I run ping, it causes the network throughput to show up as well. Web UI can then be opened up in the same TUI if I just click W there, click that in the video. Yeah, so you can also have things like this. And this is the power of the Python ecosystem, where you can have multiple libraries like Rich that was used to make the TUI, and Plotly and Dash that were used to make the web interface. And we can move on to the next example.
So this is an example where we try to detect anomalous behavior in issuing syscalls by a process using a neural net. It is taken from this blog post by Evil Socket. So if there's anything weird about it, it's the original poster, not me. So the idea is to keep track of what syscalls are being issued by a given process in a map and how the number of issued syscalls changes with time, and train a neural net on that. We will do it all in a single Python notebook. So we have some constants in the first cell, and we are trying it on the Spotify snap. So I have already put in the PID for that. And we have some util functions. And after that, this is the Python BPF code, where we are taking a PID from the target PID map and checking if we are having the correct PID or not, and then taking in the syscall we have, and then incrementing the count of the syscall in the histogram map. So, yep. And below that, yes, with a 2 or 3 seconds. There's this wrapper class for our BPF object that has been compiled and attached. And there's a get histograms function to basically poll the map every 100 milliseconds. And this is the neural net class for training and predictions. So what we ideally are doing is that I just ran Spotify for an hour and changed songs and moved back and forth and toggled the play and pause occasionally for an hour. And we collected all of those events in the CSV. There's a function for that in, I guess, cell number 8, and ran 200 epochs on that. So that's the trained model on that. Now, if we do something that I have not done in the training stage, then it should show up as anomalous behavior. And something that people usually don't do with Spotify is buying tickets for a live event. So I try doing that first. I run the inference to check for anomalous behavior, and then I try to buy the tickets for a Metallica event in London. The original poster tried to log in via Facebook OAuth. And the thing is, Spotify opens up a new browser tab here, which is weird because this was never done in the training stage. And that anomaly shows up because the error is out of the bounds. And in the end, it shows that there were 116 total events that it tried to evaluate, and out of that, one was anomalous, where we were trying to buy a ticket. And this is the next example, where we are using Python BPF with BlazeSim, a symbolization library for raw addresses. The BPF part would be in Python, but the object file will be loaded, and all the BlazeSim stuff will be in Rust. And we loosely follow this tutorial for that. So this is the Python BPF part, where we have the exec event class, which is populated by the raw addresses. And we stream it to the user space using a ring buffer. And I was a bit lazy here. I didn't implement reserve and submit, and output just runs fine because this is just an example. So, and this is the Rust code that we took up from eunomia.dev's tutorial. And we just hard-coded stacktrace.o here because that's what compiling our Python BPF code will give us. And if we compile it, First the Python part and the Rust part. So yeah, we got the object file, and so this example basically shows that you don't need to do everything in Python if you don't want to do it. You can just write the eBPF part in Python and use any user space library, and you can load the object file. Yep, it's like a very bare bones example, but it shows that it works for example. And then we move on to our last demo. Yep, the VFS read latency demo. This is our last demo, which is meant to show how the Python ecosystem brings extensibility to eBPF. We have ported the VFS read latency example from BCC to Python BPF and tried to visualize it better. First, we have the Python notebook and matplotlib, where we see that our BPF logic is pretty straightforward. It stores the start timestamp in a hash map, and at the end of the kprobe, it streams the delta between the start and end to the user space using a perf event array. And then we can store it in logarithmic buckets, or then we can plot both a linear graph of it and a logarithmic histogram of it. And here print some statistics as like P95, P99 min, max, mean. So we'll collect like 5,000 samples and then stop it, and then the graph, which, yep, yeah, it's nice, but we can probably do it a bit better. And for that, we have to go like 10 seconds ahead. So yeah, now we move on to an enhancement of the same example where we run a live dashboard for this in a TUI. Same BPF code, but in the user space part, we use the rich module to create a TUI. And yep, we'll see it running. And you see a lot of emojis here. So yeah, it's because making TOIs and web UIs is something that LLMs can one shot, and we shouldn't be spending our effort on that. Oops. So yeah, this is kind of neat. We can also go a step further here, where we can make an interactive live web dashboard for VFS read latency using Plotly and Dash modules, as we did in the first example. And this does it pretty much the same thing, same BPF code, just the user space is different. And the end result looks something like this. Like you can hover around, get the exact values. It also shows the live latencies of the past, most recent 10,000 events if we scroll down. So yep, that's kind of neat and all, but we should move back to our slides now. Yep. How do I stop? Yep. Okay. Yeah, there are more PCC tutorial examples ported over to Python BPF on this link, which you can try out with both Python BPF, Python notebooks and Python files. The next slide was, yep, for you.
Currently, we have a bunch of BCC examples ported over to Python BPF, which can be viewed. Wait, it's this slide. This slide, which can be viewed right here. We support these map types of hash, perf event array, and ring buff, as they enable us to write a lot of examples. But we can add support for more map types when we encounter a need for them. This is the open issue that's used for tracking what helpers are supported by us.
Oh. Yeah, so I think I just skipped over some slides. Why use Python BPF? So with Python BPF, someone writing a simple BPF program in Python doesn't need to fight the verifier on day one. They can write kernel space and user space code in Python, which makes this more compelling over BPF trace and BCC. It focuses on accessibility and abstraction. The idea is to lower the barriers so people can get real eBPF programs running and they can iterate quicker than they can using other methods. And the object file generated by Python BPF can be used with other user space libraries as well. So you have that option. It boils down to these 3 points. It fights the verifier for you by generating common patterns like null checks and bound checks. It is easier and less verbose, and it allows the usage of the Python ecosystem, one of the most extensible development ecosystems. So you can even write it in Python notebooks for interactive debugging and data analysis. And we ran into a bunch of challenges while making Python BPF, and we'll talk about the most prominent ones. First is a good typing system. So in Python, we don't have pointers, and with eBPF, we don't have dynamic memory allocation. So we need to design a good typing system that plays well with Python and is comprehensive enough to generate LLVM-IR from it. We need to keep the illusion of dynamic typing for the user. So we need to infer types of variables by tracking their usage and convert between types whenever an operation is done on them, or they are passed to helpers and kfuncs. We also need to generate temporary variables in cases like map return values where it's a pointer to a pointer. And we need to create scratch space for accommodating constant arguments or expression arguments to helpers and kfuncs. So for all of this, we have to do it in 2 passes and allocate everything in the first basic block first, and then write the logic.
So another challenge that we had was with VM Linux structs. They took a substantial amount of time to write. And we currently support simple structs in vmlinux.py, as well as enums and constants from it. We also provide pointer casting from int64s and int32s as well, in the case of XDP MD, in the fields of these structs. And all these structs are core enabled as well, as we generated the most minimal amount of debug info needed to make this happen. Moving forward, if we need users to embrace this, the most important things that we need to work on right now are error reporting and quick start guides. We also need to get over our difficulties around with VM Linux header support. While not a priority right now, we'd also like to reduce the amount of stack allocations and unnecessary instruction generation as well.
With the demos we presented to you, we are barely scratching the surface of what should be possible when this project is more mature. As a short-term goal, we focus on this announcement from Andrea Righi, who used a neural net with ShedX. And this seems like the perfect use case for Python BPF, where you can train a neural net using PyTorch or TensorFlow, and then plug it into your running kernel using the SCXK funcs, all in the same Python notebook. I think it would be a week's effort from now. And for a more long-term goal, we aim to make Python BPF one of the most popular choices for writing eBPF code. And for this, we need external support. As a first step, if this project appeals to you, tell us what are the most important features you would like to see in this. You can request for certain examples or tools, and please reach out to us if you or your organization has a formal interest or would have a formal interest in this project. We are planning a soft release by the end of Jan 2026, where we can showcase some of the requested features by people around, and would be able to open Python BPF for general or prod use, at least like a subset of features that we can enable for prod use. And thank you for listening to us. We would be more than happy to get your RFCs, ideas, and wish lists for this project. And questions?
I have 2 questions. So the first one is, how does your Python eBPF code pass the verifier checks?
Pass the verifier checks?
Yeah.
So we have like made a lot of programs so there is a tool which we use to check if the object file created passes the verifier check or not. So there are two ways of compiling a Python BPF project. You can either use the compile keyword, which creates an object file, and then it's the user's responsibility to check if it's passes the verifier or not. Or you can use it like BCC, where we have a BPF object, and you can call it, and it will run. It will try to load it in on your PC and tell if it has passed the verifier or not. And for the grammar we allow, it's more likely to pass than not, because we do those null checks and boundary checks that are most common pitfalls to have verifier errors. But we do run into verifier errors like once a week when we are trying something new, and then try to make a way around it in the compiler itself.
Okay, thank you. And another question is, I also trying to bring eBPF together with machine learning. However, I do the other approach. So I basically abstract all the BPF maps in Python, so that on the user space side, I could actually, plug the machine learning stuff with all the eBPF things together.
Yeah, so I think you can already use BCC for that. We also have a sister project to this, PyLibBPF, which is like Python bindings for libBPF, and that's how we are supporting the limited types of maps we showed. If we get more examples which we want to support, we'll add more map types. So our priority was to get some examples running and then focus on the iterative development by adding more k-functs and helpers and maps.
Thank you.
Hey, nice talk. Thanks. I was wondering, like one of the interesting things about trying to express BPF code in some new language is how can you make the writing of that BPF code look like you're just writing any other code in that language. So like in Python, it just all looks like Python. So this is definitely Python, right? But I noticed, like, for instance, in the license declaration, I think it was a function, maybe the map declaration was a function. I was wondering, do you see a possibility to use native types like dictionaries to express maps? Because maps are kind of a dictionary.
So for the license thing, I think we'll make it optional, first of all, because if you don't put in any license, we'll by default, this would be like reported very prominent on the README of the project, that will by default put in a GPL license if you don't specify a license yourself. On the second thing, where you say that map can be a dictionary, we actually do overload the get item and set item dunder methods in PyLibBPF. So once you have declared a hash map, you can kind of use it just like a dictionary syntax in your actual code that is being attached to a hook. But for declaring hash map, we do need to create at BPF, at map, and then perf event array or ring buffer or hash map and things like that.
Is that like, I guess because BPF maps have various different types, so you need to specify types and then size.
That is one place where we can't do any sort of type inference, and we have to force the user to give us the exact types there. We are using C types, which was like a very early decision because we were just throwing things, hacking things around. But we can use some more elegant way like I64 and U64, a better way of expressing types than writing C, uint, and other stuff.
Well, if you meant with the decorator thing, if you meant we could add dictionaries or something like that, that's because decorators accept functions, right, as arguments internally. So that's the reason we just made these into dictionaries, into functions. So you can express them as global variables, as separate blocks. So that was the intention behind that mostly. So.
So I see that in the example, you can do like print and with the Pythonic f string, which I think looks great. So could you go to a bit detail on how you made it work? Is it like just calling print k?
Yeah. So first of all, there's I think this requirement, no restriction on printk that you cannot have more than 3 arguments. On it's not like a variadic C function. It can only take 3 arguments. So as soon as it goes for first thing was if it goes for more than 3 arguments, we'll say that okay, we are not printing whatever you're trying to print. That would be a compilation warning sent there. It won't be an error because we are trying our best effort to give you something that works. But we'll surely warn you about some things that might not be as we wished. Then, yeah, because this whole thing is a subset of Python, we don't need to write our own parser. We just use AST module, and we get that format string AST from that, and we can just walk through it, and then so there can be like 2 or 3 yeah, 3 cases. Either the
So open up the architecture.
Nope.
Okay.
So either it can be like a constant integer. Okay. It can be a constant string. So now for strings, there's this thing that should it be a char array or should it be a pointer to char? Because both of the things are very different in LLVM-IR, and you cannot typecast into them in between them like C. You have to have something like memcopy there. And there is another scenario where you can have a pointer, and you don't know the depth of that pointer. That pointer can be a pointer to a struct, or a pointer to a pointer to a struct, or a pointer to an int, and things like that. So what we try to do is, if something has a struct at some level, at some depth, then we mark every depth level as this thing is a struct. So make sure you don't interpret it as a pointer to a char, because pointer to a char would try to print a byte array. If it's not marked as such, then we try to get to the most primitive type we can go to. And if it's an integer, it's treated as an integer. And if it's not an integer, it's a byte, then it's treated like a byte string. Then there is another case where you can have struct members, right? So for that, we just use get element pointer, but then that struct can be not a struct, can be a pointer to a struct, or a pointer to a pointer to a struct. So in that case, we have to we look at the annotation that we are giving to that local symbol and try to get to the required depth, and then do the gap on it by doing a bit cast. It's hell. Trying to work with it was somewhat difficult. So yeah, so the printing logic is different, and expression handling is different. And for printing, we had to do these shenanigans. And the thing with printing is, thing with strings is that if you have, so there is this command helper that you can, there's a helper that will give you the command that that will fill in the command that was called in a char array. And for that char array, you have to pass a struct member. So struct members, if they hold something that can be displayed as a byte array, has to be a char array. But normal variables would be pointer to a char. So whenever I'm and I allow, like, the Python BPF allows you to like move objects around, instruct objects and named variables as well. So at every step, we are doing that helper call to, what was that, kernel str? I don't remember the helper. But yeah, there's a helper call that basically copies that specific byte array to pointer to a byte array, and then if we want to convert that array to a pointer, we just take the first element. Yeah, it's weird.
Thank you.
G'day. As someone who's written a lot of BCC tools and BPF trace tools and whatnot, I thought I should provide my opinion, although it won't be comfortable. My opinion is the biggest problems I have is, what do I do with BPF? What kernel functions should I trace? What application functions should I trace? Next biggest problem is the overhead. Is it going to be safe to use in production? Then it's teaching other people how to use the tools. The language that I actually write the tool in is not in my top. It's not something I worry about. If the community decided to do it in Golang or Python or libc. I just don't care. It feels like you're putting a lot of effort into something that tool authors like myself don't care about. I don't really care what the language is. It's like, what do we do with eBPF that's new, that hasn't been done before? I was scratching my head about who would actually use this, and maybe if I was a startup wanting to build a BPF UI and I knew Python, maybe that would be the people who would use it, because they're building something based on what they know. But someone who's coming up with new tools, we have a lot of issues, but the actual language isn't really top.
Yep. Yep. So I think that's that. If you have any more questions, just catch us around. And yep.
Thank you.
Thank you.
What's your topic, right? Okay, ensure you speak into the mic.
So, okay, hello everyone. Thank you for joining this session. And first of all, I'd like to explain today's standpoint. I need to change my standpoint. Today, I speak as an individual, so not my company, but individual. So I'm sorry, but I just only explain the general and the published information I have already shared. And so if you have any questions, please email me after LPC. Sorry, I'm sorry for inconvenience. Okay, today I'd like to talk about the practical reality of using BPF in long-term supported systems, especially the embedded industrial devices and kernel performing areas. This talk is based on real issues I've observed through community work, yes, and discussion inside the BPF Japan community. Okay, first I'd like to introduce myself. I'm a member of the CNCF and Desert Technical Advisory Board and organizer of the Cloud Native Community Japan. And so I manage for run for BPF Japan community. It is a Japanese local BPF community. And it focuses on sharing deep dive knowledge about kernel internals and real-world BPF use cases. I've spoken at Quebec OSS Summit and this year. Okay. Okay, I'd like to introduce our local community. We see many great developers who want to use BPF, but also many who struggled. So we try to make kernel internals and BPF technology easier to understand. But the reality is that the tools and documentation evolve extremely fast. So this creates a widening gap between upstream innovation and real-world product requirements. So I've launched this community. Okay. So today I'd like to introduce today's goal. Today, the goal of today's talk is to surface the pain points experienced by vendors maintaining long-lived products, and to explore a structured proposal I call the BPF embedded profile. This is meant to help bridge the gap between rapidly moving upstream development and the slow-moving world of long-term supported systems. Okay. While BPF has become a powerful foundation for observability, networking and security tooling and its usability. But when it comes to long-lived systems, it's difficult because there are a lot of kernel version divergence and verifier regressions and user space tooling versus legacy kernel gaps. And when it comes to embedded systems, we need to consider security policies. I don't know. Some companies may ban BPF score. Okay. And this situation is becoming more serious. BPF is no longer just for tools. With features like ScaText, we are entering a world where BPF becomes a core mechanism for kernel extensibility. That means that pressure to solve long-term stability problems become much stronger. If we don't address these issues now, BPF adoption in embedded and regulated industries will remain limited. Okay, just general requirements for embedded systems. I want to introduce it. The system requirements for embedded devices vary widely, ranging from industrial equipment to automotive applications. Commonly anticipated requirements include maximizing resource efficiency, deterministic real-time communication, low power consumption, high security, longevity and maintainability, and high availability, and so on. The system requirements for embedded devices vary widely, and ranging from industrial equipment to automotive applications. So there are a lot of requirements. In addition to those requirements, I want to share the interesting paper. We need to lower the barrier of entry in eBPF ecosystem. The BPF ecosystem is rapidly expanding, but documentation has not kept pace with that. This much has led to increasing developer configuration, reflecting in the rising number of BPF tools related questions on Stack Overflow. As a result, BPF development remains challenging for newcomers, highlighting the need for structured education and up-to-date learning resources. Okay, I'd like to explain the challenges of eBPF to adapt eBPF in embedded system. Today, I'd like to introduce these items. Configuration for embedded systems, stable APIs, verifier compatibility, and security for embedded systems. At first, I'd like to explain why configurations are difficult for end users. This is a commit 4 or 5 years ago. I committed to BCC repository. And I made a list of kernel configuration and sent it to request to the BCC repository because we wanted to share what kernel configs are actually needed for each use cases. Before creating this document, we don't know what is actually needed. And just a general experiences, real world experiences. So when it comes to some selective feature, BPF features like config BPF filter, we can disable that. But most of users don't know what is actually needed or not. For example, BPF capable override to use BPF override return. I think it is one of the use case of this facility is chaos engineering, but we don't know from the perspective of end users. Another example, when you want to restrict BPF provide user using LSM lockdown, how to use it and how to set up. So it is difficult for end users. So additionally, I want the configuration list for embedded systems. We already have a kernel guide, config guide for BPF in BCC, and it's resolve real-world pain. Engineers who configure kernels often don't fully understand BPF features. For the embedded profile, we can extend this idea by mapping embedded requirements and security constraints onto the BPF feature set. This provides a practical checklist for vendors and dramatically reduce integration costs across the industry. Okay, next, I'd like to explain stable APIs. Stable APIs are needed for embedded systems. For example, tracing facilities. Kernel internals depending on BPF programs are not stable APIs, even if trace points. So sometimes regressions occur in BPF tools. And next, KFAX. KFAX are explicitly known to be subject to change. However, it's difficult for BPF program developers in the field to keep up with the small changes. For example, developers must track capability change per kernel version to use specific KFAX. It's difficult. Next, I'd like to explain verifier incompatibility. Verifiers are very great. There are a lot of excellent kernel engineers to use to develop this verifier. However, the kernel version increases the implementation changes cause compatibility issues for BPF programs. And so backporting is difficult. Should we modularize the verifier? So I have no idea, and I have no idea. Next, security more concerns. Some organizations may disable BPF fiscal entirely due to policy. So signed BPF could significantly help address these organizational security policies. And software supply chain is important. So we need to consider compliance. Every part of it is compliance license policies and traceable in bill of materials. And when it comes to the industrial systems, the debug information like BTF should be removed. And for example, just one idea, I use Mincore BPF to reduce both attack surface and size. Okay, this comes from AGL documentation about the system hardening. Yes. AGL documentation explains how to harden system to disable some features. For example, disable K probes, BPFG, and so on. And even if debug symbols, it is dangerous to expose it. So it's important, actually important. And for security, it is essential. But these policies directly conflict with BPF requirements. So I'd like to into this proposed concept. I think BPF is an embedded profile. This is a defined subset of BPF features, APIs, and tooling practices tailored for long-term use in embedded and LTS systems. This profile may include appropriate kernel configs for each use case, and version and stable KFAX set, verifier constraints, and tool chain recommendations. It is just idea, but even need certification or conformance tests like LTP. And I think it is expected benefits significantly reduce backporting burden and greatly improved predictive behavior across LTS kernels, and accelerated cross-vendor collaboration, and sustainably enhanced developer confidence for long-term use and leading to wider adoption. So this is just a sample example format. For example, when it comes to the embedded system, we considering our power and statistical efficiency is important. So we don't need the embedded system should not cause busy loops. So we may think powerful event output. And security is also important. BPF provide user has been abused in a real-world experience. So we need to consider how to set up to restrict these dangerous APIs. Okay. Okay. To get the real-world requirements, of course, I need to talk with the person of automotive people and the developers. In addition to that, I think we need collaboration to another foundations. To get the real-world requirements, I've already talked with this idea, CIP and automotive AGL, and I'm a member of CNCF. I'm a member of CNCF end user, so I just want to explain my idea with CNCF. Okay, next action. As I said, I'd like to collect real-world production requirements and talk with related foundations, BPF Foundation, CNCF, AGL, CIP, and so on. For example, I'd like to explain BPF embedded profile with BPF Foundation. And I think that CNCF has a lot of use cases and knowledge about the edge native application. And so CIP has knowledge about long-term support and upstream contribution. So I'd like to I'd like to discuss with my idea them. And so after that, I'd like to make my proposed concept great. And I want to make my proposed concept first draft. I'd like to make a first draft. Okay, key takeaways. Upstream innovation of BPF is very amazing, but not enough for long-lived embedded systems. To ensure BPF becomes a stable foundation for the next decade, we need structured collaboration. And a standardized embedded profile could be one approach. Okay, that's all. Thank you.
Now it's on. Okay, last talk for the eBPF track. And this isn't exactly a talk. It's going to be more of a discussion. So how successful this is going to be is dependent on your engagement and interaction as much as it is on me. Because my goal right now is to get feedback from the community on what we as the eBPF Foundation can do to improve the ecosystem. So I'll be having points to listen to your feedback throughout the presentation and also time at the end. And I see this as just the start of the conversation about how we can make eBPF great. So with that, who has heard of the eBPF Foundation? Okay, that's not too bad. So, right, eBPF, what are we trying to do? We're trying to innovate and enable others to innovate as a technology. And that's the upstream project. But what is the foundation actually doing? And what's the purpose of a foundation, right? Linux Foundation has hundreds of foundations, but what are they all trying to do? Like looking at a lot of different foundations, I've previously worked on CNCF and a few other ones. What foundations are actually set up to do is to encourage the community, the code, and the ecosystem around a project. And so when I'm thinking about like what the eBPF Foundation can do, I always go back to these three principles. How can we grow the community? How can we make the code better? And how can we increase the ecosystem around the technology that we're working on? And with that, how I think about this for the eBPF Foundation, supporting those three pillars is one, the community. How can we bring people together to discuss things? How can we create a sense of community around the technology? Number two, how can we work on the upstream project to make the code better? And the third one is the ecosystem. How can we tell the story about the technology that we're working on? And so I'm going to walk through each of these three pillars and tell you about the things that the foundation is doing. But then I also want your feedback on what you think the foundation should be doing in the future. And that's where I want to hear your ideas. So the first one, right? How can we grow and encourage the community? And I think a really great way to do that is to bring people together face to face. So as you can see, eBPF Foundation is a sponsor of LPC, part of the reason why we're here today, also for BPF Conf. So it's paying to bring developers together to have all the conversations about what we're trying to do. And I think it's important to be able to give the space to have people to meet and interact and engage face to face. On top of just the conference sponsorships like that, we're also going to be launching a meetup program pretty soon. So in the last talk, you heard about eBPF Japan, but how can we encourage more people to have those smaller conversations all around the world? So CNCF had a lot of great success with this, growing to hundreds of meetups all around the globe. And I hope we can get kind of along that way with eBPF, encouraging people to gather people together in their local community to discuss the projects that they're working on, why they're excited about the technology, how they're using it in their company or in their application. This is very fresh. We haven't even written the launch blog post yet, so you're getting it straight from GitHub. The second thing is, right, we talked about the community. The next part is the code. How can we actually improve the upstream project? And I think if you've worked in open source long enough, one of the things that you realize is, everybody has their own motivations, whether that's a company is paying them to work to solve a specific problem that the company has or that their customers has, or it's an individual and they're motivated by their own use cases. Everybody has an interest in why they're engaged in the open source community. But between all of those different interests, there's also gaps that come up in the community. Maybe no one's interested, a company doesn't want to pay for something falls between the cracks. But it could be good for the ecosystem as a whole. And so what we try to do as the eBPF Foundation is look at what are the things that are falling between the cracks of company interests, of individual interests, but would actually be good for the ecosystem as a whole, and how can we pay people to improve that? And so what we've actually done, the BSC has gotten together and discussed, how can we improve the developer experience for BPF for everyone? And we've gone out and contracted with Bootlin to do some statements of work for BPF. So you can see some of the commits here. And what they're doing is both submitting things to the kernel and then writing blog posts for the eBPF Foundation. Some of the work that they've done so far is things like improving runtime type information with BTF, adding low overhead trampolines, working on ARM64 feature parity, doing test suite modernization, and expanding CI coverage, right? So maybe this isn't the thing that you're excited about, but it's probably improving your developer experience or your interaction with BPF, right? So we're paying to make eBPF better for everyone. So the first question that I have then is, what types of things would you like to see improve? What do you think the things that are missing that we could pay to improve for the eBPF Foundation?
So maybe better support in CI for the stable kernels. That's something that, at least for me and I guess for the company I work for, would be useful. Yeah, I think running soft test on the stable kernels would be
And I wanted to touch on this as well, because like it's maybe also relevant to the previous talk, right? Like that there's quite a need for making sure what goes into stable. Maybe there's also things that are not being picked by the stable team, which would be good to have, but right now there's not really anyone looking over that in more detail than self-test. But that's probably like a continuous effort that is needed, right? So it's not like typical SOW style, where you have like a project and once it's completed, and then so that, yeah, it's maybe that's maybe like a little bit of a challenge, but at least it's something that would be good where the foundation could look into.
Again, what was in the previous talk, documentation, like feels like especially like people not that familiar with the ecosystem have sometimes hard time, finding resources on how to start and how to, expand their applications from being just very basics to something actually usable.
So BPF's perfect for everyone else. Okay, great. The next thing that we do to improve the upstream code, also that was a joke, you can come back with ideas later. The next thing that we do is improving the security for everybody in the ecosystem. So a couple things that we've done is doing a third-party security audit of the eBPF verifier from NCC. And we also did an eBPF threat model talking about like how you should think about the security of BPF. And we also recently got funding from Alpha Omega, which is another Linux Foundation sub-foundation, to do some more security funding. So we have $225K grant from them to do two different things. So one is increasing the defensive runtime tooling. So once again, doing an SOW to enable sanitizers for JIT-compiled eBPF programs. And the second one is doing more auditing. So security reviews of the JIT compilers across the different platforms. Yeah, so if you have other ideas about how we can improve eBPF security, what would you like to see? Okay, I guess security is perfect too.
Well, I'll answer your question with another question, I guess. Like, so, I mean, security is kind of a big space, and I think maybe even some of the talks today kind of are exploring what can we do to improve security from a code perspective. So I think probably there's vested interest already in, how do we solve security problems by building stuff in BPF? But I wonder if the gaps might be somewhere else. Like, I guess the focus maybe previously was what? having people who are not the people working on every day look at the verifier and see, are there like some problems there? Or like, how do we teach people about how to write secure BPF-based applications? So I guess my question is there something kind of more out there that's maybe like, from an ecosystem perspective, how do we communicate the value of BPF, and could we find, maybe find people who could help write that content for the wider audience?
Yes, that's one of the other ideas that we had with Alpha Mega 2, to kind of what are best practices for writing secure BPF programs so people can use that as a reference guide. Once again, going back to also how can we have better documentation about writing BPF programs too.
There was a talk yesterday. It was my introduction to signed BPF programs, and there was seemed like the question of what kind of certificate chain is there was kind of an open question. Like, could the foundation sign a root certificate and like host the Let's Encrypt style thing to say like, you're sitting at home and I want my program to be signed, and maybe something like that.
That's also something that we have discussed too. I think it's still an open question in the community how we want to do program signing. I think there's a couple different proposals. Like if you were at KP's yesterday, he walked through like a couple different ideas that we have. So yes, the foundation could host some infrastructure, but then it'd be infrastructure for what? But yeah. Okay. Then the next thing that the foundation does is we award academic research grants. So the idea here is a couple-fold. So one, how can we push forward the state of eBPF? You're funding a PhD to look at eBPF for a year of their time, right? And it's encouraging not only that student, their professor, the people that they work with to engage in the ecosystem. I can tell you it's a lot less expensive than an SOW or any of the security stuff that we're doing. And I think the PhD students are pretty smart too. So far we've funded 7 different proposals. You actually saw one of them yesterday. ePass was funded by the eBPF Foundation. So if you found that interesting, some of that work is funded by the eBPF Foundation. And besides just like pushing forward the state of the art, it's also how can we encourage more people to get into the ecosystem to grow the community, right? If you spend a year or 4 years or 6 years looking at eBPF, like wherever you go after academia, or if you stay in it, you're probably going to use eBPF again. So once again, how can we encourage more people to get into the ecosystem, both for the technology and also be able to go into industry. So when you need to hire more people for your team, there's actually people that you can hire too. I don't know if anybody has been to any academic conferences or things like that. Like, what do you find interesting in academic research around BPF that you think the foundation should fund? Andrew, I think Paul wants it.
Okay, so there's different lines of research, I think, today in eBPF, in academic research. So one of them is around maybe I wouldn't call this security, but like is it working correctly side of things. I think that's very useful because some of the work is around like formal verification stuff that we are not so familiar with today, I guess, in the community. There's also another trend of work, which I'm not sure is as interesting to us, around like offloading some stuff from applications running in user space to the kernel, which seems to happen more in the industry. I don't know if it's important to fund or anything, but like I guess the 2 big trends that we have today in academia that I've seen.
Yeah, definitely. I think those were 2 of the ones that we funded this year. So one was like ePass, like how can we improve the verifier? And the other one was power management. So how can we make power management more efficient, especially in like low latency situations, with BPF? So moving the control of power management from user space back into the kernel.
So I also have a question on this. So like, I'm wondering a bit like how these research grants, like how the recipient for this are selected. Because you mentioned like 2 different objectives, and I'm not sure they always agree. So one of them was basically funding work, and it's way more efficient than SOW. And the other one was trying to get more people into eBPF, right? And in some cases, it does happen that like the researchers making work that ends up being useful to the community are the same that are training more students. I don't think that's always the case. So like, we also have like some teams that are not publishing in like the top conferences or anything, but they do train a lot of students because they have like classes actually on eBPF during some of their courses. So is there a need for like 2 different things, or I don't know, that felt a bit like maybe it's missing the target.
Yeah, so I think I was maybe talking about like 2 different outcomes that I could see. In terms of like how it's actually selected, it's actually up to the BSC, so like the BPF steering committee, on which proposals they find most interesting. But in terms of like funding, there's other mechanisms that the foundation is doing to invest into the ecosystem, and I'll get to those in a second too, in terms of how can we encourage people, but I was just saying things that I encourage.
Okay, so for the selection, it might be useful to look at the track record of publications for researchers. That's a big way to select, I guess.
That's exactly what I was going to ask. Like, what do you think would be a useful selection? What do you value?
So I think in academia, what's valued would be the publications. It's a bit hard to do this, like to know what is actually valued when you're outside of it, right? But usually you've got conferences that are way more valued than others. And if people have published in those conferences, yeah, they end up like having better work.
Yes, so I guess like if we're able to align the interests of academic institutions with like what this community needs in terms of whether it's like the functionality or whether it's research into something that we wouldn't otherwise research just because that's not what companies fund or something like that, I think maybe that's the kind of things that'd be interesting to see. I think with the nature of research is that you may fund a bunch of things and some of those don't go anywhere, and it may not be necessarily reflective of the researchers or the institution or the idea. Like it's just how it kind of works. So part of, I think, the strategy with funding so many different projects is also to sort of diversify the possible outcomes. So.
Yeah, exactly. So, and then the last part is educational material for the people that aren't going to come to LPC, that probably have a C somewhere in their title. How can we tell them how important eBPF is going to be to the future of their projects, their products, their companies, the technologies that they rely on? So some of the things that the eBPF Foundation has funded is the eBPF documentary. If you've seen that one, a State of eBPF report, kind of giving an introduction to someone like a CIO or a CTO about what eBPF is a technology and why they should start looking at it and why they should be interested when people on their team bring it to them. And then we also recently, last week, released another one, eBPF for the infrastructure platform. So kind of pitching eBPF as this technology for the next wave of infrastructure technology. So continuing to tell the story about why eBPF is important to people that will probably never come to LPC. Beyond kind of like this high-level material, we also publish a bunch of case studies from companies. So this past year, we've published 7 different case studies. So there is ByteDance talking about how they're using eBPF for container networking, Meta talking about how they're using it for profiling, Ant Group talking about how they're using it for security, Alibaba talking about how they're using it for L7 networking, Datadog also for networking. So these are also great ways to show like the actual benefits that people get out of it. And I think once you have these like real world production like case studies, people start to see the benefit of the technology and they start getting interested in it and start investing into it too. So I think if we want to continue to grow the ecosystem, part of that is telling the actual impact that it can have on a company, on a product, on a line of business. You know, what are the actual benefits to the bottom line? So when a kernel developer goes and say, hey, I want to do this in BPF, and they come back with the question, why would you do that? You can say, this is the benefit that ByteDance has gotten by doing this with BPF, or this is the benefit that Meta has gotten by doing this with eBPF. So it gives kind of the proof points to allow other people to start to investigate and invest into the technology too. These case studies are also liked a lot by the media. So for instance, like ByteDance went on the Software Engineering Daily podcast after the case study was published. So it's another way to drive interest into the technology by showing these real world proof points. And then Paul, getting back to what you said is like, how can we encourage other people that aren't just, doing things, but actually training other people to continue to do that and invest in building the ecosystem. So this year we launched a community building fellowship. So this is the first time that we're doing it. And so we had 2 people awarded for it this year. We hope to do this in the future too. So it's the people that aren't maybe pushing the technology forward, but they're encouraging a lot of other people to get into the technology too, to encourage the community building, getting more people into the technology. How can we have the getting started guides, the labs, the tutorials, the blog posts, the way, the on-ramps for people to get into the eBPF ecosystem. And then something else that I'm working on now too is a company landscape. So people can understand all the companies that are actually using BPF right now in their products. This is specifically focused on the products. And it was really interesting for me, putting together this landscape and realizing how many companies are actually starting to base all of their products on BPF. The most kind of shocking one for me is the largest bar chart right there. There's already 36 companies that are using BPF for security. And that's, as you can see, the largest use case. In terms of products, I think this is going to be the maybe biggest area for BPF in terms of vendor technologies that are being sold to end user customers. And then, so as we're putting together this landscape, what information would be interesting for you? Things that have been brought up before is that we want to integrate is which companies are contributing the most. So getting an overview of, which companies are going. This might be interesting if you're looking for your next role, which companies are actually allowing their employees to do the upstream work, talking about how people are investing into the ecosystem. Is there anything else that'd be helpful for the foundation to surface to you as someone developing in the ecosystem?
Yeah, thank you. So I have general suggestions, maybe not really too technical. I think there's the foundation already did something great, which is trying to put up documents and the case studies. But I think our audience varies from company to company and varies from person to person. And there may be something the tech giants, like what you mentioned there, Google or Alibaba or whatever other tech giants, they are probably good with the existing documents, but for those really newcomers to this ecosystem, that they might need different kind of material. So I think probably it was doing something like classifying all our documents into something like a newcomer friendly or to those startup companies and then other categories like tech giants, and you can do it more do VPF with more complex tasks, etc. So that might be helpful to attract more fresh person with basic level of whatever they want to join the community.
Yeah, so like kind of like in the last presentation, having different profiles.
Yeah.
So something executives like to see is how many billions of dollars is this market? And so I would like to see a executive level summary that said this security market is whatever, $18 billion projected by 2030 and is currently being disrupted by eBPF. The performance monitoring market is $9 billion projected by this date. And so those numbers do exist. Think organizations like Gartner do track them, but I don't have the glossy brochure to send to executives. They need to know these numbers because everyone asks executives of major companies to invest in their cool thing, and they speak numbers, billions of dollars, and that's a great way to get their attention.
That's actually a really good idea. Maybe that's a good one for a white paper for next year. As part of putting together the landscape, we're trying to like pull some of this data automatically from Crunchbase, because there you have a lot of the funding rounds, like market cap, that type of stuff. But it gets a little bit messy sometimes when you pull in companies like Google, right? Or Meta, they're doing a lot of other things besides just BPF. So I'm trying to figure out the right way to surface the information. But I actually think that's probably a good idea for like kind of a white paper for next year.
Have you also spoken to Gartner or other? Because they also like do all the surveys, right? So, yeah, I don't know. Maybe that can also be something.
Yeah.
Or we had like this Wall Street Journal article, which I think was pretty cool.
Cool. And then to round out the presentation, the foundation is always looking for more members. All this stuff isn't for free. If we want to continue being sponsors, it'd be great to have more member companies. These are our member companies right now. And yeah, I'd be happy to help talk to you if you want to join the foundation, or connect me with the right person in the company to join the foundation on behalf of your company. So with that, on this presentation, is there anything anyone else would like to bring up? This is the open discussion, or any questions that you might have about the presentation, the foundation, anything that didn't make sense.
So is there anything that the foundation is doing for regional communities? So for instance, I was thinking about like countries where English is maybe not as commonly spoken as other countries, and where any resources on eBPF are harder to get into, right?
Yeah, so I think there's kind of two things that we can do around that. One is like the meetup program, right? Because local people are going to do things in their language, like the eBPF Japan meetup is a great example of that. And then the other one, so the Community Building Fellowship is actually based off of something from the Rust Foundation, and they fund fellows to bring Rust into new languages or new areas or things like that. And I could see us in a future kind of like pool of foundation fellows to have someone like that once they apply. Any more questions or comments? Okay, thanks for coming.
I think he already got.
Huh? Like I think like some of my presenters but didn't get access. And like we got
Okay, I think tomorrow we still have conference, but BPF micro conference will be the last day today. So thanks for coming, and we hope to see you guys next year.
That's the way you get external internals. There are two ways. But the trade-off is that so there would be like right. I think the other trade-off is will change that way update or whatever. Okay.
You are currently the only person in this conference.